Hi, hello. Can you all hear me? Good evening. Hope you all can hear me.
ഒരു ലാഗുണ്ട് ലാഗുണ്ട് അതെപ്പോഴും ഉള്ളതാണ് എല്ലാവർക്കും എല്ലാ
Okay, today we are going to have a complete bullet revision of all the chapters from class 12 chemistry. So we are going to start with physical chemistry. Okay, that is starting from solutions, then electrochemistry, and then moving on to kinetics. And before that, you can see the previous year's toppers, and you can be the next. Okay. So we are going to start with the solutions chapter. Right. First of all, important formulas from solutions chapter. We have molarity, molality, mass percentage, mole fraction, ppm, etc. So we are going to have a quick revision of all those formulas. First of all, coming to molarity, we have four important formulas. Mass of solute by molar mass of solute into 1 by volume of the solution in liter. Next is mass of solute by molar mass of the solute. You know, this is the number of moles into 1000 by volume of the solution in milliliter. Then number of moles of the solute by volume of the solution in liter. That is, it is the same. Battery വല്ലതും കഴിയാൻ വഴിയില്ല. So, coming to the third formula for molarity, that is number of moles of the solute by volume of the solution in liter. The same mass of solute by molar mass of solute is replaced by number of moles, that's all. And then final one, mass of the solute by molar mass of the solution into just a second. Here there is a correction, that is instead of mass of solute by molar mass of solute, it is this is number of moles of the solute divided by volume of the solution in milliliter into 1000. So we can use any of these formulas to calculate molarity as how it is presented in the question paper. As per the question, you can use it. Next one is molality. what is molality? Number of moles of the solute divided by mass of the solvent in kilogram, or number of moles of the solute into mass of the into 1000 by mass of the solvent in gram. So that is molality is equal to mass of the solute by molar mass of the solute. This is number of moles into 1 by mass of the solvent in kg, or mass of the solute by molar mass of the solute into 1000 by mass of the solvent in gram. Any one of these we can use to calculate molality, right? Then coming to mole fraction, what is mole fraction of a component in a particular mixture or a solution? It is number of moles of that particular component divided by total number of moles of all the components in the solution. That is, it can be solute or solvent, whatever. Number of moles of that particular component by total number of moles of all the components in the solution. You all know about these things already. We are having a quick recap. Then mass percentage and ppm. What is mass percentage? It is mass of solute or solvent, that is mass of the component, divided by total mass of the solution into 100. That is mass percentage. And ppm, this part is the same thing, that is mass of the component divided by total mass of the solution, but in the place of 100, it will be 10 raised to 6. Clear? This represents 1 million. Now, coming to interconversion formulas. I am pretty sure that you might have already practiced these formulas. That is, we have molarity is equal to mass percentage into density of the solution in gram per ml into 10 by molar mass of the solute. Or molality is equal to 1000 into molarity divided by 1000 into density of the solution minus molarity into molar mass of the solute. These are all very important interconversion formulas. And then next one is chi solute, that is mole fraction of the solute, is equal to molality by molality plus 1000 by molar mass of the solvent. If you are not thorough with these interconversion formulas, it is high time to master these formulas and use them in the board paper. Clear? Now, coming to Henry's law. What is Henry's law? It is applicable for a gas dissolved in a liquid, right? So, we can say that when a gas is dissolved in a liquid, the solubility of gas in the liquid or mole fraction of the gas in the liquid is directly proportional to pressure exerted on the gas. That is, the more the pressure exerted on the gas, more will be its solubility in the solution. Okay, or mole will be its mole fraction in the solution. And its mathematical form is P gas, that is pressure of the gas, is equal to KH, that is Henry's constant, into chi gas, that is mole fraction of the gas in the solution. Now, there are some important proportionalities which you have to master to crack the board examination questions. First one is relationship between Henry's law constant and solubility. KH is inversely proportional to solubility, that is higher the KH, lesser the solubility. KH directly proportional to temperature, higher the KH, higher the temperature. Or higher the temperature, higher the KH. Then solubility of gas in liquid is inversely proportional to temperature, because you know KH is directly proportional to temperature and KH is inversely proportional to solubility. So KH, that is solubility of the gas in liquid, is inversely proportional to temperature. Solubility is inversely proportional to temperature. Now, this is a commonly asked question in papers based on this proportionality. And what it is? Gas A is more soluble in water than gas B at the same temperature. Which one of the two gases will have higher value of KH? You know KH is inversely proportional to solubility, right? So, if KH is inversely proportional to solubility, they are asking you which one of the two gases will have higher value of KH. Higher value of KH means lower solubility. And which one is lower solubility? It is written gas A is more soluble. That means gas B is less soluble. So, the answer will be gas B. Clear? Very, very important question. Then, this is another common question seen in recent papers. That is, aquatic species feel more comfortable in cold water than in warm water. What is the reason? Aquatic species, they depend on the oxygen dissolved in water, right? So, the more the oxygen dissolved in water, they feel more comfortable. But you know, solubility of gas in liquid is an exothermic process, right? Solubility of gas in liquid is an exothermic process. So, hot water or warm water will contain lesser amount of dissolved oxygen compared to cold water. So, they feel more comfortable in cold water. Practice it. Then coming to Raoult's law. You know, Raoult's law, we have Raoult's law when the solute is non-volatile, only the solvent is volatile, or for two volatile liquids also, two volatile components. So, what is Raoult's law? The partial vapor pressure of each volatile component is directly proportional to its mole fraction in the solution. So, if there are two components P1 and P2, then we can say P1 is directly proportional to chi1, that is P1 directly proportional to its mole fraction in the solution. So, P1 is equal to P01 into chi1. That P01 is, this is P1 is vapor pressure of component 1 in the solution. P01 is when that component is pure, that is of the pure solvent. Now, P2 directly proportional to chi2, or P2 is equal to P02 into chi2. Same thing, P02 is the vapor pressure of pure solvent, that is pure component 2. Now, we can say P total is equal to P solute plus P solvent. P total is the sum of P solute and P solvent if both are volatile. If one is not volatile, for example, if the solute is not volatile, then P total will be equal to P solvent, which was asked in 2022 Term 1 paper. This application was used. Then, this is another formula to calculate P total. P total is equal to P01 plus P02 minus P01 into chi2. Learn these formulas and you can do the numericals related to them. Then, this is when you come to the gas phase. When you come to gas phase, we can say P1 is equal to P total into Y1, where Y1 is the mole fraction of component Y in vapor phase, component 1 in vapor phase. And P2 is equal to P total into Y2, where Y2 is the mole fraction of component 2 in vapor phase. So, you have to understand chi1 is the mole fraction of component 1 in the solution, whereas Y1 is the vapor pressure or the mole fraction of component 1 in vapor phase. Similarly, chi2 is the mole fraction of component 2 in the solution, whereas Y2 is the mole fraction of component 2 in the vapor state, vapor phase. Clear? And you know, Raoult's law is a special case of Henry's law. It is highlighted in your textbook. Please go through that area and master that also. Raoult's law, what is Raoult's law? P1 is equal to P01 into chi1. What is Henry's law? It is P gas is equal to KH into chi gas. When you compare them, KH will become equal to P01. That is, when you come to a binary solution, one component is so volatile that it is equivalent to a gas. That is how they get related. So, just go through that area in the textbook. Now, coming to colligative properties. What are colligative properties? Colligative properties are those properties of a solution which depend on the number of solute particles only, not on their nature. That is, what is the number of solute particles in the solution? Doesn't matter what is its nature. Clear? And we have many colligative properties learned this year. What are they? Relative lowering of vapor pressure, elevation in boiling point, depression in freezing point, and osmotic pressure. These are the four colligative properties what we have learned. Now, let us revise them quickly. These are important formulas what we are discussing. First one is delta P1 by P01. Delta P1 means the change in vapor pressure or lowering in vapor pressure. P01 is the vapor pressure of pure component 1. P1 is the vapor pressure of component 1 in the solution. You know, when you add a non-volatile solute into a solvent, the surface will get occupied, a fraction of the surface will get occupied by the solute particles, and the number of solvent molecules escaping into vapor phase will become less. So, vapor pressure will become less. Automatically what will happen? P1 will be lesser than P01. So P01 minus P1, that is called lowering of vapor pressure, and divided by P01. So it is relative lowering, that is lowering with respect to the original, that is that with respect to that of the pure component. So this is called relative lowering, and it is equal to chi2. What is chi2? Mole fraction of the solute, which is W2 by MM2 into MM1 by W1, or N2 by N1 plus N2. If it is a very dilute solution, we can neglect N2 in the denominator. Just go through those areas. And coming to elevation in boiling point. I told you we are just discussing the formulas only in this session, but I am just explaining the theory also behind these formulas. Now, delta TB is equal to KB into M. You can see delta TB is equal to KB into M. Or delta TB is equal to KB into, sorry, KB is missing. You can see maybe some errors in typing because you can see I'm a bit handicapped for time being, so just bear with me, okay. So here there is KB also. Delta TB is equal to KB into, what is M? M is W solute by molar mass of the solute. That is, M is molality. So we are replacing it by molality, expanded formula. That is mass of solute by molar mass of solute into 1000 by mass of the solvent in gram. So this is the formula for calculating delta TB. So delta TB is equal to KB into M, where M is expanded, right. Now coming to depression in freezing point, the next colligative property, that is delta TF is equal to KF into M. Here also KF is missing in the second formula, so just write it. Delta TF is equal to KF, I am writing with my left hand, again bear with me, handwriting won't be that proper like how I write with my right hand. Just not to cancel the live, I am taking the live today, so please bear with me, okay. So delta TF is equal to KF into, what is M? Mass of solute by molar mass of solute into 1000 by mass of the solvent in gram. So this formula also you have to master. You already know it. Then next one is osmotic pressure. What is osmotic pressure? Pi. Pi is equal to CRT, where C is the molarity of the solution. T is the temperature in Kelvin. So pi is equal to CRT, and that C means what? Molarity is number of moles of the solute divided by volume of the solution in liter. So that C we are replacing by N2 by V. That is number of moles of the solute by volume of the solution in liter. This volume will be in liter when you use this formula. Clear? And R will be using different values based on the units of temperature, volume, etc. Clear? Temperature can be only in Kelvin here. We cannot use any other unit for temperature in this formula. But volume can be in liter or in meter cube, or accordingly we can use the value of R. So there is a modified formula again. Pi is equal to, this N2 is W2 by MM2. So mass of solute by molar mass of solute. So pi is equal to W2 by MM2 into RT by V. Any one of them we can use according to how the question is presented in the question paper. Then coming to Van Hoff factor. Where is this Van Hoff factor applicable? Van Hoff factor is required when it is a correction factor actually. It is required when the solute undergoes dissociation or association. It is not required when the solute is a normal solute. That is, it is not undergoing dissociation or association, right? That is just like urea, glucose, sucrose, all these they don't associate or dissociate. They are normal solute where I, the Van Hoff factor will be 1. But if you take ionic solutes, they undergo dissociation. You know, acetic acid will undergo dissociation to form acetate ion and H plus in water. But if it is acetic acid in benzene, it will undergo association to become 1. So in such cases, we need to correct the formulas what we have developed in the previous cases of colligative properties. So, 1/2 factor is like a correction factor. And when we ask you to define 1/2 factor, what you have to do? I is equal to, you can define with the help of the formulas itself. We can say I is the ratio of normal molar mass to abnormal molar mass. That means it will become abnormal molar mass if it undergoes dissociation or association. So, normal by abnormal. Or it is observed colligative property by calculated colligative property. Or it is total number of particles after dissociation or association divided by total number of particles before dissociation or association. So, any one of these we can use for calculating the 1/2 factor I. We can define also with respect to these ratios. Clear? Then we are modifying the formulas with the help of introduction of 1/2 factor if the solute undergoes dissociation or association. And that is delta P1 by P01 is equal to I into P01 minus P1. P01 minus P1 by P01, that is equal to I into Chi2. Delta TB is equal to I into KB into M, or delta TF is equal to I into KF into M, or pi is equal to I into CRT. So, these correction factors are introduced. And one more thing, there is a relationship between alpha. Alpha means the degree of dissociation, and 1/2 factor I. I'll tell you what it is. You know, if it is dissociation, then the formula is alpha is equal to I minus 1 by N minus 1. If you don't know this formula, learn it by heart. Alpha is equal to I minus 1 by N minus 1. This is number of particles after dissociation. That N is number of particles after dissociation, right? And if it is sodium chloride, for example, if it is sodium chloride will dissociate to form Na plus and Cl minus. So, number of particles after dissociation is 2. Assuming complete dissociation, we can say I is equal to N, which is 2 here. But if it is not complete dissociation, then I and N won't be equal. Then this is how you can relate it. Clear? Now, if it is association, how will you take it? Then alpha, in the case of association, what is the formula? Alpha is equal to 1 minus I divided by 1 minus 1 by N, where this N is how many particles undergo association. For example, if 2 become 1, then N will be 2. So, you might have done all these things already revised. We are just redoing it. Okay, that's all. Just try to recollect all these things. I have done many questions in my previous videos related to all these areas, applications. So, try to watch them too, if time permits. Now, next one, important proportionalities from colligative properties. You know, these proportionalities are very important when it comes to application questions. So, let us see some of these proportionalities. First one, colligative property is directly proportional to number of solute particles. More the number of solute particles, higher will be the value of colligative property. That is the meaning. Then, colligative property inversely proportional to molar mass of solute. Very, very important in many board questions. So, higher the value of colligative property, lower will be the molar mass of the solute, or vice versa. Clear? Then, boiling point elevation directly proportional to lowering of vapor pressure. Boiling point elevation means delta TB. This is commonly used in assertion reason application area. That is, boiling point elevation, that is delta TB, is directly proportional to lowering of vapor pressure. You can see, we are going to discuss the graphs later after this session. That time you can see the gap between the vapor pressure of the solvent and the solution. That difference between that gap will be maintained between T0B and delta TB also, indicating that they are directly proportional. Clear? When we discuss the graph, I'll tell you about that. Similarly, freezing point depression, that is delta TF, is also directly proportional to lowering of vapor pressure. Okay? Note down these proportionalities. And now, this is a trendy question in board papers, in recent board papers. And many students make a mistake in this, or that is why I selected this question actually. Many students do it in a very, very lengthy way. But we have a shortcut to do this question. So we are just going to revise this. Question is, how many ml of 0.1 molar HCl are required to react completely with 1 gram mixture of Na2CO3 and NaHCO3 containing equimolar amounts of both? We are given molar mass of sodium carbonate is 106 grams per mole and sodium bicarbonate is 84 grams per mole. How to do it? Let's see. Make sure to practice this question, and in some of the recent years papers, it is asked for 3 marks. So, better to practice. Sometimes it is 2, sometimes 3. So, here we are given a mixture. What is the mixture? NaHCO3, that is sodium bicarbonate, plus HCl. You get sodium chloride plus water plus carbon dioxide. This is how sodium bicarbonate react with H. That is, you have a mixture. When you add HCl into it, both the components of the mixture will react with HCl, right? So, the next component is sodium carbonate, that is Na2CO3 plus then HCl gives, it is the same thing, NaCl plus water plus carbon dioxide. Then what is the difference? Difference is the balancing coefficient. Here they are in the ratio 1:1. But here it is, this will become 2 HCl. You can see when you balance, it will become 2 HCl. So, it is 1:2. So, understand, this is the mixture given to you. So, to this, that is totally, it is 1 gram. 1 gram of the mixture. Okay. Now, to that we are adding the dilute HCl. Here 1 mole of HCl is required, here 2 moles of HCl are required. Now, how to do this question? They are asking you, what is the volume, how many ml of this acid is required? How many ml of HCl is required to neutralize this or react completely with this mixture? Let's see how to do it. You can see, you are given sodium bicarbonate molar mass is 84 gram, right? This is 106 gram. So, we are going to do it in a very simple way. What is the total mass of the mixture here? Total mass of the mixture is, that is, if I take 1 mole of Na2CO3 and 1 mole of NaHCO3, the total mass is 190 gram, because both of them 1 mole each. So, 190 gram mixture, 190 gram mixture requires how much HCl, how many moles of HCl? 1 mole plus 2 moles. So, you are getting 3 moles of HCl. That is, 190 gram mixture requires 3 moles of HCl. Clear? So, here you are given 1 gram mixture. If it is 1 gram mixture, then how many moles? You are getting 3 by 190 moles of HCl. So, we got the number of moles of HCl required to react with 1 gram of mixture. And what is that? 3 by 190 moles. Now, let us proceed. So, number of moles of HCl required. Number of moles of HCl required is 3 by 190. And you are given molarity of the acid is 0.1 molar. We are asked to calculate what is the volume of the solution required. Volume of HCl solution required. We know molarity is equal to number of moles of the solute. Here the solute is HCl by volume of the solution in liter. We have discussed the formulas in the very beginning. So, molarity is equal to number of moles of HCl by volume of the solution in liter. Now, substitute. Molarity is 0.1 is equal to number of moles of HCl is 3 by 190 divided by volume of the solution you will be getting in liter. And when you solve this, you will be getting volume of the solution as 0.1578 liters. You can check. But question is how many ml? That is a question asked. So just multiply this by 1000. So you are getting 157.8 ml. Approximately this will be your answer. Clear? Make sure to practice this question very well. I hope that is clear. Now, we will take a short break and we'll go to the next chapter. That's all about solutions. Try to revise. Now, we'll be passing on to electrochemistry. Okay? Just take a break of 5 minutes. Welcome back. You can see me, right, properly? Can you all see me properly? What about the lights? Is it okay? It would be great if you could respond. Right. So now we are moving on to electrochemistry. Okay? Electrochemistry, you know, the most important area, one of the most important areas is, okay, great. One of the most important areas is Nernst equation. So let's revise the Nernst equation quickly. Nernst equation, you know, there are two types what you have learned. One is for a single electrode and the other one is for the entire galvanic cell, right? I told you we are discussing the formulas, okay? So, what is the Nernst equation for electrode potential? It is Em plus bar, M raised to N plus bar M. This is the charge on the metal ion, you know that. So, M raised to N plus bar M is equal to E naught or E0, M raised to N plus bar M minus 2.303 RT by NF log 1 by M raised to N plus. For example, if you deal with zinc 2 plus 2 electrons gives zinc. For that, it will be E Zn 2 plus bar Zn. Just giving you an example, that's all. E Zn 2 plus bar Zn is equal to E0 Zn 2 plus bar Zn minus 2.303 RT by NF. N will be 2 here, so 2F log 1 by Zn raised to 2 plus. Okay, zinc 2 plus concentration. That's what you have to do. So that is Nernst equation for electrode potential. Now come to Nernst equation for cell potential. E cell is equal to E naught cell minus 2.303 RT by NF log product by reactant. Or if it is a 25 degrees centigrade, E cell is equal to E0 cell minus, it is 2.303 RT by F, that is 0.0591 by N log product by reactant. And later on, we can replace this product by reactant using equilibrium constant, okay, K. But this is the Nernst equation for a galvanic cell, right? Now, how to calculate equilibrium constant from Nernst equation? You have to make sure to practice all these formulas very well, okay? E0 cell is equal to 2.303 RT by NF log Kc. I told you that product by reactant we can replace by Kc. And at 25 degrees centigrade, E0 cell will be as usual 0.0591 by N log Kc. Okay? You have to revise these formulas well. And now Gibbs energy. What is Gibbs energy? Delta G. Or standard Gibbs energy is delta G0 R. Delta G0 of the reaction. And what are the formulas connecting them? Delta G0 of the reaction, that is standard Gibbs energy of the reaction, is equal to minus NF E0 cell. And there is one more formula which you may not be that much familiar, but you have studied this in 11th standard. I normally ask my students to learn that also well. And that is delta G0 is equal to minus 2.303 RT, then log Kc. So better to know this formula also. Just keep it in your mind. Suppose they ask you something related to it, you can use it. Clear? Now, we are going to see one numerical question. And this is a repeated board question, so I just selected it. A sample question. The standard electrode potential for Daniel cell is 1.1 volt. Calculate the standard Gibbs energy for the reaction. Zinc solid plus Cu2 plus aqueous gives zinc 2 plus aqueous plus Cu solid. I am not going to great detail, okay, of all the steps. You know what are the steps required in Nernst equation. You have to write oxidation, reaction, reduction, reaction, redox reaction or overall reaction. Find out what is the number of electrons transferred, that is N. And then just then calculate E0 cell. If it is not given, then put it into the formula, okay. So here, zinc is losing 2 electrons, Cu2 plus is gaining 2 electrons. So N is 2. Means you have to write Zn gives Zn2 plus 2 electrons, that is oxidation. Cu2 plus 2 electrons gives Cu, that is reduction. Then add them together, cancel 2 electrons, N is 2. Then you get this equation, right? So N is 2. Let's do this question. So here you know N is 2. Now what is the formula? Gibbs energy is to be calculated, and delta G0 R is equal to minus NF E0 cell. That is the formula. Here minus N is 2, and this is actually a solved example in your textbook, but still it is very important because it is repeatedly asked. Clear? So in your textbook 96487 is used, but most of the board papers they give you 96,500. That is the value of Faraday coulombs per mole. 96,500 into E0 cell is given to you 1.1 volt. Now when you do this, you will be getting this answer minus 212300, but make sure to write the unit. And what's the unit? It is joules per mole. Okay, so the answer is minus 212300 joules per mole. It is not compulsory to convert it into kilojoules per mole because it's not mandatory. Even if you leave it like this, you will get full credit. Okay, or if you would like to convert it into kilojoules per mole divided by 1000, so it will be minus 212.3 kilojoules per mole. It's okay. Then another commonly asked type. I just selected some types of the questions because it's not possible. It's impossible to do all the questions in a quick revision. Okay. So conductivity of 0.00241 molar acetic acid is 7.896 into 10 raised to minus 5 Siemens centimeter inverse. Calculate its molar conductivity. If lambda 0 for acetic acid is 390.5 Siemens centimeters per mole inverse, what is the dissociation constant? First of all, you have to calculate molar conductivity. It's molar conductivity. How will you calculate molar conductivity? We are just discussing the method. Lambda m is equal to kappa conductivity into 1000 by molarity. So kappa is equal to what? Conductivity is given as 7.896 into 10 raised to minus 5. So kappa that you will substitute here into 1000 by C is this one. So when you do that, you will get lambda m value. Okay. Once you got lambda m, what you have to calculate? Alpha. What is alpha? Degree of dissociation. Lambda m C, that is lambda m at a particular concentration by lambda m 0. That is lambda m C by lambda m0. That is limiting molar conductivity. So you will get a value here. Once you got alpha, you use Ka formula. What is Ka formula? Ka is equal to C alpha square by 1 minus alpha. C alpha square by 1 minus alpha. So you will put the value of alpha here. So C is the molarity and alpha square by 1 minus alpha. So when you do this calculation, you will be getting this answer. That is Ka is equal to 1.85 into 10 raised to minus 5. Okay, you can work it out. It is an exercise question. Clear? Important for 3 marks. Now, another type I have selected is from Faraday's first law. Another repeated board question. A solution of nickel nitrate is electrolyzed between platinum electrodes using a current of 5 amperes for 20 minutes. what mass of nickel is deposited at the cathode. Molar mass of nickel is given to you. So, you know the shortcut formula to calculate mass of metal deposited. Just a sec. So, what is mass of metal deposited? Mass of metal deposited is equal to molar mass of the metal involved, mm into I that is current in ampere, into T that is time in second, by mm into I into T by NF. What is this N? This N is the number of electrons received by the metal ion to get reduced. Basically, it is the charge on the metal ion. Nothing but charge on the metal ion. You know it is nickel nitrate, NiNO3 twice. That means nickel's valency is 2. So, it will be Ni2 plus. So, you have to present it like this. Ni2 plus aqueous plus 2 electrons will give you Ni. So, 2 electrons are gained. That means N is 2. Just substitute it. What is the molar mass? Molar mass of nickel is given 58.7. I have seen many students making a mistake here. They take the molar mass of nickel nitrate completely. Please don't do that. You take it only for the metal involved because the metal is getting deposited. Okay. So 58.7 into what is the current here? Current of 5 amperes. Right. Then time given here is 20 minutes. But I have told you, you have to convert it into seconds. Many students don't do this and they lose mark. So 20 into 60 you have to do. Divided by, what is N? N is 2 into, it is 96,500. So you have to calculate this. That is 58.7 into 5 into 20 into 60 divided by 2 into 96,500. And when you do that, you will be getting this answer. 1.825 gram of nickel is deposited. Clear? Practice. I know all of you would have practiced all these things, but redo. These are repeated board questions. If you haven't done it, high time to do it. Now, this is actually a question taken from the latest board paper. I think you can see me because there's a reflection from the white color. Using E0 values of X and Y given below, predict which one is better coating for coating the surface of iron to prevent corrosion and why. You know, when you coat the surface of the metal, iron, that coating metal should be more reactive than iron. Then only it can protect iron from corrosion, right? So, you just compare the reduction potential values. That is what we are going to do. Just compare the reduction potential values. Here the reduction potential is minus 2.36. Here it is minus 0.14. Here for iron it is minus 0.44. What is the meaning of, you know, when you compare this one has lesser reduction potential than iron, right? So, lesser the reduction potential, lesser the tendency to get reduced, right? Lesser the reduction potential, lesser the tendency to get reduced. So, lesser the tendency to get reduced means it has more tendency to get oxidized. That means it is more reactive. Metal is having more tendency to get oxidized means it is more reactive than iron. So, it will sacrifice its life to protect iron, right? So, basically, you know, this is magnesium actually if you know the values. This is tin, okay? Sometimes they will give you with respect to the original metals themselves. So, this is more reactive than iron. So, it can protect iron from corrosion. It will get oxidized and iron will be reduced. It will be in the reduced format. But if you look at this, this has more Rp, reduction potential, than iron. So this will be reduced, iron will get oxidized. So iron is getting oxidized means it will undergo corrosion, right? So which one is the correct answer? X will be a better coating. It will be offering a better coating to prevent iron getting corroded from corrosion of iron. Clear? So the correct answer is X. That will protect iron from corrosion. I think the application is very clear. This is from 2023 board paper. Now, the next one, another formula which is very important, maximum work done by a galvanic cell. What is the maximum work done by a galvanic cell? You know, a galvanic cell will do work by using its free energy. Energy free to do work, free energy. So, when the cell is doing work, there will be a decrease in free energy, right? So, W max will be nothing but decrease in free energy. You have studied delta G0R or delta G R is equal to minus NF E cell. Clear? So, what is W max? Maximum work done by a galvanic cell is minus of delta G. That is negative of delta G. Delta G is minus NF E cell. So, what is minus of that? It is NF E cell. So, maximum work done by a galvanic cell is NF E cell, where F is the same, 96,500. Clear? Just keep the formula in mind, though it is not that commonly asked in terms of numerical, but they have asked it in past, but not seen in latest board papers. Now, next one, coming to cell constant conductivity. What are the important formulas from that area? Cell constant is L by A, where L is the length of the conductor and A is the area of the conductor. Okay? Conductivity kappa is 1 by resistance into L by A. That is 1 by resistance into cell constant. So, you have done all these things in physics also, but make sure to practice. We never know. Okay? So, just practice the formulas. Now, coming to molar conductivity. Molar conductivity, there are two formulas actually. First one, this is the most commonly used formula in the exam. That is lambda, that is molar conductivity is equal to kappa into 1000 by C. That is conductivity into 1000 by C. But make sure to have an idea about the units of kappa and C when you use this formula. Otherwise, you will go wrong. Here, when you use this formula, kappa should be in Siemens centimeter inverse. It is compulsory. And C should be in moles per liter. That is a normal molarity. Then you can use this formula safely. Okay. Actually, I have told you about all these things while taking these topics in class. But I don't know how many of you remember these things. So, I have just made this clear and so that you will remember these things properly before your board examination. Okay. Next one is lambda is equal to kappa by C. You can see there is no 1000 here. So, if you use this formula, when will you use this formula? When kappa is in Siemens meter inverse and the concentration is not molarity, it is not moles per liter, it is moles per meter cube. Okay. So, be very careful when you use this formula. Clear? Okay. Now, next one is resistivity, that is rho. What is resistivity formula? R into A by L. Resistance into area by length of the conductor. Simple. Now, Kohlrausch's law of independent migration of ions. It is also very important, simple questions. They might ask you what is the lambda m value of sodium sulfate. Sodium ion, small lambda will be given, sulfate will be given. Just add them as per the number of ions produced. So, that's very simple. Now, what is the mathematical Kohlrausch's law? Definition you have to learn. This is a formula session. So we are just discussing the formulas related to it. Lambda m0 of the electrolyte is equal to lambda plus that and lambda 0 plus, that is how many positive ions into its molar conductivity, that particular ion's molar conductivity, plus lambda minus into nu minus into lambda 0 minus. I'll just take an example to illustrate it. Okay, let us take magnesium chloride. You know, magnesium chloride is an electrolyte. It will dissociate to form what? To form magnesium ions and 2 chloride ions. Clear? That is how it is dissociating. So how will you apply Coloradius law here? Lambda, capital lambda 0 m of magnesium chloride is equal to small lambda 0, because this nu plus is 1 here, only 1 magnesium ion. So lambda 0 then of Mg 2 plus. Now there are 2 chloride ions, that is this nu minus is 2 here, 2 into small lambda 0 of Cl minus. This is how we can illustrate Colrash's law. Clear? So this stands for how many positive and negative ions, accordingly you have to substitute, but very important in recent board papers. Now next one is alpha is equal to lambda m by lambda m at a particular concentration by lambda m 0, limiting molar conductivity, and Ka is equal to C alpha square by 1 minus alpha. We have used it in a previous numerical. So hope that's also clear. Then Faraday's law, we have already used it. Okay, mass of metal deposited is mm into I into T by Nf. This time has to be second, and this I is capital I. It is the current in amperes. Okay, we have used it already. You are well aware of these formulas. Then Faraday's second law. What is Faraday's second law? When different solutions are connected in series and the same quantity of electricity is passed through them, then the mass of metal deposited in each one, mass of substance deposited in each one, they bear a relation. And what's the relation? Mass of metal deposited in first one by its equivalent mass, E1, is equal to mass of metal deposited in the second one by its equivalent mass, is equal to mass of metal deposited in the third one by its equivalent mass, and so on, depending on how many cells you are connecting in series. And what is equivalent mass? Equivalent mass is nothing but molar mass by valency of that metal. For example, if you take copper, you know copper's molar mass is 63.5 divided by copper's valency is 2. So this will be the equivalent mass of copper. Clear? Molar mass is 63.5 divided by its valency, that will be the equivalent mass. Right? And now see, I have accommodated important proportionalities wherever possible, because that is very important in doing application questions in higher order thinking skill. So what are the important proportionalities here? Reduction potential, that is the E0 value, reduction potential, directly proportional to oxidizing power. What do you mean by that? Higher the reduction potential, higher will be its tendency to get reduced. So it will be a very good oxidizing agent. So higher will be its oxidizing power. Clear? Similarly, reduction potential, inversely proportional to reducing power. Higher the reduction potential, higher the tendency to get reduced, lesser the tendency to get oxidized. So lesser will be its reducing power. That's how you have to relate it. Okay. And then this is also very important in latest board papers, applications. This area, be very careful. E cell directly proportional to concentration of R. This concept was asked in 2022 board paper. Okay, in Chem 2. So more the concentration of the reactant. Suppose you have a galvanic cell and its redox reaction is given. if you increase the concentration of reactant in that equation, that is, if you increase the concentration of the reactant, E cell also will increase. If you decrease the concentration of the reactant, E cell also will decrease. Clear? Similarly, when you come to product concentration, it is opposite. It is inversely proportional. So, more the product concentration, lesser will be the E zero cell, or lesser the product concentration, more will be the E zero cell. I'll take an example. Suppose I am using the Daniel cell equation. Zinc plus Cu2 plus gives zinc 2 plus Cu. You know, this is the reaction happening in Daniel cell. Here, this is the product and this is the reactant, right? So, think in terms of this. If copper concentration increases, if reactant concentration increases, E cell will increase. Clear? This is the product. If product concentration increases, E cell will decrease. This is how they make questions in the paper. Like they may give you an equation like this and ask you to apply this. So if you don't know the proportionality, you will not be able to do it. Hope that is clear. Then some important units, they are also sometimes 1 markers in board papers. SI unit of conductivity is Siemens per meter. SI unit of molar conductivity is Siemens meter square mole inverse. You know, many students, when we ask SI unit of molar conductivity, they write Siemens centimeter square mole inverse because we are using it very frequently in our work. But that is not the SI unit. It is a commonly used unit. But SI unit, you know, SI unit of length is meter, right? So, SI unit of molar conductivity is Siemens meter square mole inverse. Keep it in mind. Then, this relationship is also very important. 1 Siemens centimeter square mole inverse is equal to 10 raised to minus 4 Siemens meter square mole inverse. Because 1 meter square is what? 1 meter into 1 meter. That is 100 centimeter into 100 centimeter. So 1 meter square is 10 raised to 4 centimeter square. From there only we get this relation. Clear? Okay. And now, master this. I would say master this because this is the latest trend in Cbse class 12 chemistry board examination paper. You can see those who have done the previous board papers, you might have come across this very frequently. So, let's see what it means. A negative E0 value. I'll just take an example and show you. I told you, master this, revise this even before you enter the board examination hall. It's very important. Okay. So, a negative E0 value. For example, you know E0, zinc 2 plus bar zinc is minus 0.76 volt. You know this by heart because we are using it very frequently in numericals. So we can say a negative E0 value. Okay. If you are not getting it properly, take an example and try to do it. No, fuck it. No. I'm just. Oh, you വീടല്ലേ
ചുമ്മാ ഓണാക്കി ഓഫാക്കിയാൽ മതി.
Yeah, hope you can hear me. All right, look here. So, I told you if you are not thorough with this area, just think about an example. You can easily master it. E0 zinc 2 plus bar zinc is minus 0.76 volt, right? So, you can see here it is less than 0. That is a negative value. So, it means that its reduced form is less stable than hydrogen gas. What is the reduced form? Reduced form is zinc. This is the oxidized form. This is the reduced form. It is more stable than hydrogen gas. That is, zinc is more stable than hydrogen gas because E0 H plus bar H2 is 0.00 volt. You know that standard hydrogen electrode. So compared to this is less. So it has less tendency. This one is more, this one is less. Think like that. This is more, this value 0 is greater than this. So H plus has more tendency to get reduced to H2 compared to Zn2 plus getting reduced to Zn. That means this is more stable than this, or this reduced form of zinc is less stable than hydrogen gas. This is more stable because its value for getting reduced is more. Clear? Similarly, suppose I take copper. Coming to the second one, positive E0 value greater than 0. E0 Cu2 plus bar Cu is plus 0.34 volt. You know that. This is more than 0. So what does that mean? This value is higher than 0 means Cu2 plus has more tendency to get reduced to Cu than H plus has to go to H2. So copper is more stable than H2, or its reduced form is more stable than hydrogen gas. So learn these two values which you are expected to know from Danielson. Use them to deal with such questions. Don't come to a conclusion. Just take an example, then do the trick and try to answer. Clear? Okay. Now coming to batteries. I don't think I have to go in depth with batteries. You know, it's a very important area. Normally they will ask you one battery, either from primary or secondary area. In each battery, you have to know what is the anode, cathode, electrolyte, reaction at anode, reaction at cathode, overall reaction. If given, whatever is given in the textbook, go accordingly. Okay, but it is very important. Now, primary and secondary batteries are there. What are primary batteries? In primary batteries, reaction occurs only once. And after use over a period of time, battery becomes dead and cannot be reused. Means it cannot be recharged and reused again. That is called primary battery. The best example is dry cell. Dry cell is also known as Leclanché cell. You know that. It's very important. You know, there is a 2 marker in the previous board papers. Name the cell used in dry cell, then car battery, then which one? The hydrogen oxygen fuel cell in Apollo space program, then hearing aids, mercury cell. All these were carrying half mark each and they made a 2 marker out of the batteries. Okay, so practice. So primary battery, best example is dry cell, which is also known as Leclanché cell after the discoverer, and it is used in transistors and clocks. Name the cell used in transistors and clocks. Which one? Dry cell or Leclanché cell. Coming to secondary cell, it can be recharged and reused again and again. Okay, by passing current in the opposite direction. You know, the car batteries we recharge and reuse, right? Isn't it? So it is coming under secondary battery and it can undergo a large number of discharging and recharging. Most important secondary cell is the lead storage battery, which is used commonly in automobiles and inverters. It was used in one of the previous papers. Name the cell used in automobiles and inverters. That is the lead storage battery. Okay. Now, I have just taken the abstract from your NCERT book and you can see primary battery. Here they have explained what is the anode, cathode, electrolyte, etc. and what are the reactions. Please go through that area properly. Go through this area in the textbook. And then, what about mercury cell? you know, in mercury cell, this is the overall reaction. Mercury cell also you have to know what is the anode, cathode, then electrolyte, reaction at cathode, anode, then overall reaction, etc. This is the overall reaction in mercury cell. But look at this. You can see mercury cell, it is used in hearing aids. It's used in watches, isn't it? Then hearing aids. We use mercury cell in hearing aids. Why? Because it produces a steady voltage of 1.35 volt. A steady voltage is produced. And why it produces a steady voltage? Because you can see the overall reaction. There is no ion. There is no ionic species present in the overall reaction. If ionic species is present in overall reaction, what will happen? They will change their concentration every time. So it will lead to fluctuation in voltage. But that will not happen in the mercury cell. You know, suppose we have hearing aid in our ear and it is always fluctuating the voltage, then you will become more deaf, right? Then it is getting corrected. Clear? So it is compulsory that it should produce a steady voltage, and mercury cell is the best. No ions in the overall reaction. So two give reasons here. Why mercury cell produces a steady voltage? You should know. Second, why it is used in hearing aids? Why? Because it is very small, compact in size, and it produces a steady voltage. Clear? Then lead storage battery. You should know what is the anode, cathode, overall reaction. Then during discharging, that means when the battery is in use, what is the reaction? When the battery is recharged, what is the reaction? This was used, these equations were used in 2023 board paper, the latest board paper. They have used this in one set. So practice the equations and be aware of what is the reaction, what are the reactions during discharging, means when the battery is in use and when it's getting recharged. Clear? Okay, practice well, very important, practice by writing. Then coming to the fuel cells, master this area. That's why I have taken it like this, so that you will come to know which all areas of your textbook are important for your preparation. If you haven't done it, this is the time to do it. Okay. You can see what is meant by what is meant by fuel cell. Galvanic cells that are designed to convert the energy of combustion of fuels like hydrogen, methane, methanol, etc. directly into electrical energy. They are called fuel cells. And the best one is, the most common one is the hydrogen oxygen fuel cell, where we are bubbling hydrogen gas at the anode and oxygen gas at the cathode. The electrolyte is there at the center, that is NaOH solution, and it is compulsory to know this figure. Other cases figure is not required, but here it is compulsory to know the figure. And it is compulsory that you are giving hydrogen at the anode, because hydrogen is undergoing oxidation. You know, H2 plus O2 gives H2O. H2 is getting oxidized, and H2O, H is plus, O is minus, O2 minus. So hydrogen is getting oxidized and it should be given in at the anode, because anode is the electrode for oxidation, and oxygen is getting reduced to oxide ion. So that should be given in at the cathode. Clear? So what is the reaction of the anode, cathode, overall? All these things are very important, and these are porous electrodes, carbon electrodes. So you can go through all those things in detail. Very important. And what is the advantage of this fuel cell? What is the advantage? Two main advantages. Number one, it is more efficient than the conventional cells. This is a 70% efficient versus only 40% in the other types of cells, okay, types of galvanic cells, other types of energy providers. And then this one doesn't produce any pollutant, okay, no ash, no smoke, nothing, but that is, it is pollution free, unlike the conventional methods of producing electricity. Clear? Okay. Now coming to corrosion, this is a 3 marker commonly asked in papers. Even this figure you are expected to practice, okay, they have done it in the past. So you should know what is the explanation of electrochemical theory of corrosion. So it starts from here. Electrochemical theory of corrosion starts from here. It is considered essentially as an electrochemical phenomenon, at a particular spot made up of iron, then oxidation takes place. Starting from there, you have to do it completely, including the equations. And the figure also you have to practice. I don't think you need my help in that area, just practice it. But it is very commonly asked. Then how to prevent corrosion? We can prevent corrosion by, covering the surface of iron by oil, paint, or by another surface, another metallic surface like galvanization. We can coat the surface of iron with zinc. That is called galvanization. Zinc is more reactive than iron. So zinc will get oxidized. Iron will be in the reduced format. Clear? Then there is tin plating. But when you coat iron article with tin, what will happen? Tin will be in the reduced form. Iron will get oxidized, but iron is inside the tin coating. So if there is a break or the coating is broken, I'll show you one example here. Suppose I have an iron object. It is coated with the zinc. So this is galvanized iron object. Next one, I have an iron object. It is coated with the tin. This is called tin plating. Now, if you look at this, zinc is more reactive than iron. So zinc will get oxidized, iron will get protected from oxidation. So it will not get corroded. So this is getting protected. But tin, as long as there is an intact coating of tin, it will protect iron. But the problem is, if there is a break anywhere on the coating, through that broken area, through that area which is exposed, iron will get exposed to the corroding factors and it will undergo corrosion, whereas tin cannot do anything about it. But here, even if there is a break on this coating, what will happen? Through the broken area, iron will get exposed, but still it will not get corroded because zinc is still there on the surface. It is more reactive than iron. So it will, till the last atom of zinc is there, it will prevent iron's corrosion. Clear? And that's all from electrochemistry. You can take a break for 5 minutes and come back for kinetics. Okay. Can you hear me? All right. So we are going to start with kinetics. First of all, average rate. What is average rate? Rate of a reaction is change in concentration of the reactant or product divided by change in time. So if C1 is the initial concentration, C2 is the final concentration, then T2 is the final time and T1 is the initial time, then what is the average rate? C2 minus C1 divided by T2 minus T1. So this can be used for reactant as well as product. Normally we use it for reactants. Okay. Then coming to the rate equivalence, that is we are going to equate rate with the rate of disappearance of the reactants and rate of appearance of the products. So let us see this reaction, that is 2N2O5 gas gives 4NO2 gas plus O2 gas. We can equate the rate with the rate of disappearance of the reactant. Here what is the reactant? Reactant is N2O5. So delta N2O5 by delta T. That is change in concentration of N2O5 by change in time. But you can see there is a minus sign here. What does that minus sign indicate? Minus sign indicates that the concentration is decreasing with respect to time. Clear? Now, rate is, and whatever is the balancing coefficient here, you can see 2 is the balancing coefficient of N2O5. So that 2 is coming in the denominator. That's how you have to do. So rate is equal to minus 1 by 2 delta N2O5 delta T is equal to. So this is called this minus delta N2O5 by delta T. That is called rate of disappearance of N2O5. That means here we will not take this number. This area will not come in rate of disappearance. Okay, that is only when you equate with rate. Is equal to plus 1 by 4. Why it is plus? Because it is product and its concentration increases with the time. As time passes by, its concentration increases. So plus 1 by 4 delta NO2 by delta T. So what is the rate of appearance of NO2? It is plus delta NO2 by delta T. This is called rate of appearance of NO2. It is equal to plus delta O2 by delta T. Because balancing coefficient is 1, so it is delta O2 by delta T. Clear? So we can equate the rate of the reaction. This is the average rate. So we can equate the rate of the reaction to decrease in concentration of the reactant or increase in concentration of the product. That is rate of disappearance of the reactant, any of the reactants, or rate of appearance of any one of the products. Clear? So practice this area well. And this type of question is there in recent board papers. We will be doing one such kind soon. Now, what is integrated rate equation? For zero order, what is the integrated rate equation? R0 minus R by T, where R0 is the initial concentration, that is concentration when time is 0. R is the concentration when the time is T, and T is the time period. Okay. Then, if it is integrated rate equation for first order, then it is K is equal to 2.303 by T log R0 by R. R0 means that is the concentration of the reactant when time is 0, when you start the reaction. And this R is when time is T. You know all these things. Now, suppose you are doing gaseous phase reactions and it is first order gas phase reaction. Then K is equal to 2.303 by T log Pi by Pa. That is instead of concentration we are using partial pressure, right? So Pi means the initial pressure and Pa is just like R0 it is Pi, just like R it is Pa. That is pressure, partial pressure of the reactant when the time is T. We will be doing one such question from this area also. Then what is the half-life for zero order reaction? T half is equal to R0 by 2K. Here you can see T half is directly proportional to R0. It's coming in the numerator, right? So T half is equal to R0 by 2K. That is the relationship between T half and R0 for zero order. It depends on the initial concentration and it is directly proportional. When you come to the half-life of first order, then T half is equal to 0.693 by K. Here, nowhere the R0 comes in the picture. So that means T half is independent of the initial concentration. Clear? For first order reaction. And you know, most of the, that is the natural radioactivity or artificial radioactivity. All radioactivity situations come under first order. Whereas the decomposition of HI, then ammonia, etc. on metal surfaces, they follow zero order reaction. Because once the surface of the metal gets completely saturated with the say ammonia gas or HI gas, now even if you pass more ammonia or more HI onto the metal surface, the rate of the reaction doesn't change. That means it is independent of the concentration of the reactant. So it will become zero order. Clear? By the way, it would be great if you could tell me my video is fine for you, because this is my first live and I'm still learning. Okay, so please do let me know if it's fine or if you have any recommendations. Thank you. Right. Okay, now what is the Arrhenius equation? Arrhenius equation for activation energy, to calculate activation energy. What is it? Log K2 by K1. You learn this formula by heart. Okay, very, very important. Log K2 by K1 is equal to EA by 2.303 R into T2 minus T1 by T2 T1. Now, what is this K2? K2 is the rate constant when the temperature is T2. What is K1? K1 is the rate constant when the temperature is T1, right? Now, one trick. It is always better to take the higher value of temperature as T2 so that the difference will become positive, okay? So, out of the two temperatures given, take higher value of temperature as T2, lower value as T1. So, T2's corresponding K will be K2 and T1's corresponding K will be K1. Clear? Right. Now, this is an application area. It is not there in the text, but a few years back, there was one question based on this in the board paper. So, I thought I'll discuss this also. You know, when you use a catalyst, in the absence of catalyst, activation energy will be high. When you use a catalyst, what will happen? It will lower the activation energy. So, activation energy is lesser or lower in the presence of catalyst, right? So, they will ask you how many times the reaction rate increases when you use a catalyst. How many times it becomes faster. So, this is the formula to calculate that how many times it becomes faster. Log K2 by K1 is equal to EA1 minus EA2 by 2.303 RT. You can see it is EA1 minus EA2. EA1 is the activation energy which is higher in the absence of catalyst. EA2 is the activation energy in the presence of catalyst. So, EA1 minus EA2. Make sure, one more thing, you know the unit of activation energy is joules per mole. Or they might give you in kilojoules per mole. If they give you in kilojoules per mole, you have to convert it into joules per mole. Otherwise, what will happen? We are using R, universal gas constant. Its value is 8.314 joules per Kelvin per mole. You can see we are using joules here. So, if the numerator is in kilojoule and this is in joule, you will go wrong in terms of power of 10, right? The entire answer will go wrong. So, take care. This is joules. This is joules. So, this has to be converted into joules if given. Mostly they will give you in kilojoules only in the paper. Okay. So, convert it into joules. Now, I have given the hint, EA1 is in the absence of catalyst, this is in the presence of catalyst. So, you will calculate log K2 by K1 first. Once you get log K2 by K1, then what is K2 by K1? Antilog of that. So, suppose you got K2 by K1 is equal to X. You got K2 by K1 value as X. So, you can say K2 is X times K1. Suppose you got 25. X is 25. So, we'll say K2 is 25 times K1. That means it becomes 25 times faster in the presence of catalyst. I think there is very less chance for you to get this calculation because nowadays their Cbse is not giving you logarithmic book or logarithmic table in the examination hall. They give you the log values which you have to use manually. So, if you use log K2 by K1 is something, to calculate K2 by K1 they have to give you the anti-log. Okay, let's see. I don't think they will give you any anti-log value. Not anticipated. Anyway, practice it. Okay. Just explained that area also. If it comes, how to deal with it. Now, the next one is fraction of reactant molecules having energy equal to or greater than EA. You know, when you increase the temperature, the rate will increase. When you increase the temperature by 10 degrees centigrade or 10 Kelvin, the rate almost gets doubled, right? You have studied it. What is the reason why it is getting doubled? Because when you increase the temperature by 10 degrees centigrade, the fraction of molecules having energy equal to or greater than EA also gets doubled, nearly doubled. That is why the rate gets doubled. Now, here the question is fraction of reactant molecules having energy equal to or greater than EA. How to calculate? What is that fraction? Let us assume that fraction is X. This is a derived formula. I am not going to the derivation. Let us assume that that fraction is X. Then log X is minus EA by 2.303 RT. This is derived from Arrhenius equation. The original Arrhenius equation. What is that? K is equal to A into E raised to minus A by RT. That is the original equation. From that we have derived this. So, if log X is this, then what is X? Anti-log of minus A by 2.303 RT. And that answer what you get will be the fraction of molecules because X is the fraction what we have assumed. Clear? Now, some points to be remembered. Number 1, so these are some tricks actually. First one, T3/4, that is time taken for 3/4 of a reaction to get completed is 2 times T1/2. Or we can say T75% is 2 times T50%. T3/4 means time taken for 3/4, that is 75% of the reaction to get completed, that is 2 times T1/2. Clear? So, you have to keep that in mind. Remember, you might have come across a question. A reaction is 50% completed in 2 hours. What is the time taken for 75% completion? See, time taken for 75% completion is what? T75%. They are asking you what is the time taken for 75% completion. If time taken for 50% completion, that is T1/2, is 2 hours. So, it will be 2 into T1/2. So, it will be 4 hours. So, you can use these tricks if they come in the paper. Okay, that's why it is discussed. Then similarly, EA is equal to, that is activation energy we can calculate from the graph. Not from the Arrhenius equation, from the graph we can calculate. Okay, if you are given the graph format. So, EA is equal to minus 2.303 into R into slope. This is the formula if we use this graph presentation, that is log K versus 1 by T, 1 by capital T, temperature. Okay, if it is like this, then we can use this formula to calculate EA. Then, if you are given log R versus T, log R versus T, that is time, log R versus time, here this time, then slope is equal to minus K by 2.303 and slope is equal to minus K if R versus T graph or ln R versus T graph is taken. So, just go through this. Then K2, this is very, very important. Another trick. Okay, that is K2 by K1. You know, in Arrhenius equation, K2 by log K2 by K1 is equal to EA by 2.303 R into T2 minus T1 by T2 T1. So, in such questions, we are going to discuss one question of that kind also, which is there in one of the recent board papers. So, there we can use K2 by K1 is equal to K2 by K1, 0.693 by T half. K is equal to, this is about first order what we are discussing. K is equal to 0.693 by T half. Right? So, K and T half, they are inversely proportional, you know that, for first order reaction. So, K2 by K1, so K2 by K1 is equal to, because they are inversely proportional, if you write K2 by K1, it will be T half 1 by T half 2, because it is inverse proportionality. We need it in one of the forthcoming board question numerical. We will be discussing it shortly. Now, this question, for a first order reaction, show that time required for 99% completion is twice the time required for completion of 90% of the reaction. There is one more question like this in the solved example area. So, either that one or this one you can expect in the paper. So, I thought I will discuss one out of the two. So, whenever such questions are given, you are given two percentages. One is 99%. One is 99% and one is 90%. So, the best way is take them as case 1 and case 2. Okay. So, what is case 1? Just discussing the method, that's all. What is case 1? It is time taken, right? So, T is equal to, it is first order reaction. So, let us take the integrated rate equation. So, T is equal to 2.303 by K into log R0 by R. Integrated rate equation. So, what we will do here? If it is T 99%, I think you people know and remember, whenever you deal with percentage questions, let R0 be taken as 100. If it is fraction questions, you take R0 as 1. Okay. So, here it is percentage. So, I am taking R0. Let R0 is equal to 100. Then what is R here? What is R here? It is 99% completed. Out of 100, 99% completed. So, remaining will be 1. So, 100 minus 99, that is 1. Clear? So, you will write it here. T 99% is equal to 2.303 by K, then log 100 by 1. So, that will be log 100 and log 100 it is 2. You know 100 is 10 square. So, log 10 square is 2. 2 log 10. So, it is 2. So, this part it will become 2. Similarly, what is case 2? If you take case 2, then it will be, it is 90%. So, I am straight away writing it to save time. Okay. So, if it is T 90%, how will this change? It is 2.303 by K, then log, now R0 is 100 itself. Why? Because it is percentage. By it is 90% completed. So, what is R? You will show 100 minus 90, that is 10. So, this will become log 10. Log 10 means it is 1. Now, what you can do? Divide. T 99% by T 90% is equal to, when you divide, these two will get cut, right? When you divide, these two will get cut. So, you are getting T 99% by T 90% is equal to 2. So, you are getting T 99% is equal to 2 times T 90%. Hence proved. Clear? Practice such questions well. Highly expected. I hope this is clear. Thank you. Okay, now, yes, this is an exercise question. I know I'm not that much visible when it is white background. Okay, bear with me for this session. I told you I'm just learning. Okay. So, the following data were obtained during the first order thermal decomposition of SO2Cl2 at constant volume. Now, this question is very commonly asked in recent board papers. Make sure to practice it. So, I'll just show you how to do it. SO2Cl2 gives SO2 plus Cl2. We have discussed gas phase reactions which are first order. So, this is one such question. Let's see how to do it. Okay. You are given a table. When time is 0, it is 0.5. Pressure is 0.5. When time is 100 seconds, the total pressure is 0.6. Okay. You are asked to calculate the rate of the reaction when the total pressure is 0.65 atm. So, first of all, we have to calculate K. Okay. And we have discussed, just listen well because some students have a difficulty in this question. That is what is seen. But it is too simple actually. So, you know K is equal to 2.303 by T. You know this is gas phase reaction. Is into log Pi, that is just like R0 by R. I have told you it is Pi by Pa. Right? So, first of all, because you have to calculate total pressure, rate of the reaction when the total pressure is this, for rate is equal to K into partial pressure of SO2Cl2 where you need K. So, we are going to calculate K. 2.303 by T log Pi by Pa. This Pi is the pressure when time is 0. You know it is 0.5. Pa is when time is 100. But here it is written total pressure. There are some students, they will write 0.5 here and 0.6 here. Absolutely wrong. Because initially when the reaction starts, there is only reactant, no products, they are 0. But when time passes by, this is getting converted into this. So, once time is 100 seconds, this will be there, this will be there, this will be there. And all are gases. So, the total pressure, this 0.6 will be including partial pressure of this and this. So, but in the original formula, we need only for the reactant, we need only for SO2Cl2. But this 0.6 includes all these. So, how to get what is Pa? We are going to do it in a tabular form. Actually, there is a shortcut formula. I'll show you. That is, but I don't encourage you using that. There is a reason. 2.303 by T log Pi by this Pa is 2 Pi minus Pt. But you have to understand that this Pi by 2 Pi minus Pt, that is applicable only when they are in the ratio 1:1. It will not work every time. That is an issue. So, don't go for it. And moreover, if you check the marking scheme of this question, they need the tabular form. Okay, they need the chart. So, if you don't draw the chart, you will not get full mark even if your final answer is correct. So, we are going to discuss the chart format solution. Clear? Let's see how to do it. So, look. Okay, I'm going to draw a chart. You know it is SO2Cl2 giving SO2 plus Cl2, right? Now, this is the chart required. If any of you have not practiced this yet, try to do it along with me. Okay, it is very, very important. Now, first of all, let us take initial pressure. Initial pressure. Then change in pressure. And then pressure at time t. Okay. Initial pressure of SO2Cl2. What is the initial pressure of SO2Cl2 given? Initial pressure of SO2Cl2 means when the time is 0, it is 0.5. I told you initially only this is there, these are not there. Okay. So it is 0.5. It is 0.5. This is 0.5. This is 0. This is 0. Because there is no product when time is 0. At the starting of the reaction, there is no product. Now change in pressure. Here comes a trick. Easy. You just go by the balancing coefficient. 1:1:1. So this is minus 1x because balancing coefficient is 1. It is minus because it is reactant and decreases. Concentration or pressure decreases with respect to time. Here it is plus 1x because it is product, its concentration or pressure will increase. Here it is pressure because these are gases. And here also it is plus x. Clear? Now, what is the pressure when time is t? Here time is 100. So, it was 0.5. Just like equilibrium table what you have done last year. Same thing. 0.5 minus x. It was 0.5. Change in pressure is minus x. So, now when time is t, here 100 seconds, it is 0.5 minus x. This is 0 plus x, 0 plus x. Clear? Now, what we are going to do is, when time is t, here it is 100. So, what is P total? P total means at time t, what is a P total? At time t, all these are present in the system. So, they will all exert pressure. So, the total pressure will be 0.5 minus x plus x plus x. Clear? 0.5 minus x plus x plus x. And what is the P total given to you? P total given to you at 100 is 0.6. Okay. So, we are going to see the substitution. So, P total is 0.6 is equal to, now this minus x and plus x will cancel. So, you are getting 0.5 plus x. So, P total is equal to 0.5 plus x. So, what is x? 0.1, right? You are getting x as 0.1. Okay, I'll write it here. You are getting x as 0.1. Now we can put it here. Okay. But first of all, let me take you to the chart as well. So what is the partial pressure of SO2Cl2 when time is t? It is 0.5 minus x, right? That means partial pressure of SO2Cl2 when time is t is 0.5 minus x. So what is that PA in the formula? PA in the formula is partial pressure of the reactant. Reactant is SO2Cl2 when time is t. Just like R0 by R, the R is PA. So that is 0.5 minus x. X you got what? 0.1. So 0.5 minus 0.1. 0.5 minus 0.1, you are getting 0.4. Okay. So PA, you are getting it as 0.4. I think you got it clearly. Okay. X is 0.1. So you got it as 0.5 minus 0.1, which is 0.4. Okay, now let us substitute it into this formula. So what is K? You are getting K is equal to 2.303 by T. So K is equal to 2.303 by T. T is 100 here. Okay. 2.303 by T log. Then Pi. What is Pi? It is 0.5. Right. Then what is Pa? What you got right now? Pa was 0.5 minus x, so 0.5 minus 0.1. You got it as 0.4. I hope you are doing along with me. So this will be log 5 by 4. 0.5 by 0.4 is 5 by 4. So log of 5 by 4 it will be 1.25. So when you substitute 2.303 by 100 in the log 5 by 4 or log 5 minus log 4, it will be given to you in the paper, question paper. Then when you solve it, you will get this answer for K. Clear? So the K value you will be getting 2.23 into 10 raised to minus 3 second inverse. That will be the value for K. Clear? I hope you got it. But it is not completed. The work is not completed. You can see, calculate the rate of the, sometimes they will ask only till K. They will not ask you what is the rate when the pressure is 0.65 atm. They have done it in the past. But in this question, you have to calculate the rate of the reaction when total pressure is 0.65 atm. So here, the total pressure is 0.65 atm. So let us see. Close it. Sorry for the interruption. Let's continue. Can you hear me? Right. Okay, so here you are given P total. You have to calculate the pressure when P total, rate of the reaction when P total is 0.65 atm. But what was P total? P total was 0.5 plus X, right? That is 0.5, previous case, 0.5 minus X plus X plus X was P total, if you remember the last row of the chart. So, it was 0.5 plus X, that is 0.5 plus X is, that is P total, right? Here the new P total is 0.65. So, what is X? 0.65 minus 0.5, that is 0.15. Okay. So, this is the new X. Clear? Now, you know rate is equal to K into partial pressure of SO2Cl2 raised to 1, because it is first order reaction you are given. So, rate is equal to K into partial pressure of SO2Cl2 raised to 1. K you have already calculated. Now, what is PSO2Cl2? PSO2Cl2 is, it was 0.5 minus X, right? The last row of the chart. It was 0.5 minus X. So, here 0.5 minus, what is the X for you in this new situation? It is 0.15. So, you are getting it as 0.35. Clear? So, that is the new X in this new total pressure. So, use the previous K here, previously calculated K here, into partial pressure of SO2Cl2 is 0.35. So, whatever you get, atm second inverse, that will be the answer. Okay. So, practice this well. That is the rate of the reaction when the total pressure is 0.65. You have to go this way long, okay, to get the correct answer. So, I'll show you what is the expected answer. The expected answer for the rate is 7.8 into 10 raised to minus 3 atm second inverse. Make sure to practice this question well. Okay, now the next question. Again, such questions are also important. I have just taken a sample. A reaction is second order with respect to a reactant. How is the rate of the reaction affected if the concentration of the reactant is doubled and reduced to half? Make sure to practice such questions well. So, we will just do this quickly. This is very simple. You also can try. So, a reaction is second order with respect to the reactant. You are given the order. So, you will write let the rate low. What is the rate low? Rate is equal to K into concentration of A. Let it be A, or we can write R. For reactant, you can write R, whatever. Or you can write X, we don't mind. So, it is second order with respect to a reactant. So, let this be equation number 1. Okay, doing it fast. Then, how is the rate affected if the concentration of the reactant is doubled? Let this be taken as R1 is equal to K. That is the initial rate is A raised to 2. Let this be equation number 1. Okay. Now, what is R2? R2 is equal to K into concentration of the reactant is doubled. So, this will become 2A square. So, that means R2 is equal to K into, this is A square into 2 square. Let this be equation number 2. Then equation 2 by equation 1. That is R2 divided by R1 is equal to K into A square into 2 square divided by K into A square. This will get cancelled. So you are getting R2 by R1 is equal to 4. So R2 is equal to 4 times R1. Similarly, you can do this when it is reduced to half. So if it is reduced to half, A will become what? A by 2, right? It is reduced to half. Then you will write R2 is equal to K into A by 2 raised to 2. That is R2 is equal to K into A square divided by 2 square, that is 4. Okay, let this be equation number 2. Here also you can do R2 by R1, or if you want you can write this as R3, doesn't matter. So what is R2 by R1 here in the new situation? It is equal to K into A square into 1 by 4 divided by, this is K into A square into 1 by 4 divided by K into A square. So cancel this. You are getting R2 is equal to 1/4 of R1. That means the rate becomes 1/4 of the initial rate. Clear? Practice such questions also well. Another format. Okay. Yeah, this is 2023 board papers question. Okay, this is like that rate equivalence, like rate is equal to rate we can express in terms of disappearance of reactants or appearance of products. It is from there. A chemical reaction 2N2O5. 2N2O5 gives 4NO2 plus O2. In gas phase was carried out in a closed vessel. Concentration of NO2 was found to increase by 5 into 10 raised to minus 3 moles per liter in 10 seconds. Calculate rate of formation of NO2, rate of consumption of N2O5. So, how to do it? You are given concentration of NO2. Concentration of NO2, just a second. Concentration of NO2 was found to increase by 5 into 10 raised to minus 3 mole per liter in 10 seconds. So, what will be the rate? We have discussed rate is equal to change in concentration by change in time, right? So, what is the change in concentration? It was found to increase by. So, that is a change in concentration. So, 5 into 10 raised to minus 3 moles per liter by 10 seconds. So, you are getting 5 into 10 raised to minus 4. Okay, this will become 10 raised to minus 1. So, it is moles per liter per second. This is the rate. So, we calculated the rate, but that is the rate of the reaction, not rate of formation of NO2. Clear? Now, what you have to do? Based on this, you have to write the rate equivalence. So, what is it? Rate is equal to minus 1 by 2 delta N2O5 by delta T is equal to plus 1 by 4. See, it is 4. So, plus it is product. So, plus 1 by 4 delta NO2 by delta T is equal to plus delta O2 by delta T. This is the expression in terms of rate of appearance of the rate of appearance of the product and rate of disappearance of the reactant, expressing rate. Okay, now let us substitute. You calculated rate as 5 into 10 raised to minus 4, right? So, let us see. So, we can write rate, that is 5 into 10 raised to minus 4 is equal to, yes, You are asked to calculate rate of formation of NO2. So express in terms of rate of formation of NO2. This is the plus delta NO2 by delta T. That's the rate of formation of NO2. So let us take that. Is equal to plus 1 by 4 delta NO2 by delta T. Is equal to plus 1 by 4 delta concentration of NO2 by delta T. Now, how will you calculate the rate of formation of NO2? Rate of formation of NO2 is this one, okay? Therefore, you will write rate of formation of NO2. So, that is plus delta NO2 by delta T is equal to what? 4 times. That is 4 into 5 into 10 raised to minus 4. Whatever you get, so and so moles per liter per second. That will be the answer for part 1. And what about the second one? Second one, the rate of consumption of N2O5. So rate of consumption of N2O5 means you have to take this, okay? Rate is equal to minus 1 by 2. That is, you have to take this area. That is, rate is equal to this one. So rate of consumption means what? Consumption means rate of disappearance. So it is minus this much. So rate of disappearance of N2O5 is 2 times rate. So 2 into 5 into 10 raised to minus 4. So you'll be getting these answers, okay, for A and B. Clear? Okay. So we'll have a break for 5 minutes. I just have to change the battery pack. Okay. Hi dears, can you hear me? Can you please comment? Can you hear me? Please comment. Okay, thank you. Okay, listen. So we were discussing this question before the break. That is the concentration of, let us rediscuss once more. Chemical reaction, because we stopped in between, okay. So chemical reaction 2N2O5 gives 4NO2 plus O2. In gas phase was carried out in a closed vessel, concentration of NO2 was found to increase by 5 into 10 raised to minus 3 moles per liter in 10 seconds. Calculate the rate of reaction of rate of formation of N2 and rate of consumption of N2O5. Now, the first one we already calculated. I have written the rate equivalence, that is rate is equal to minus 1 by 2 delta N2O5 by delta T is equal to plus 1 by 4 delta NO2 by delta T is equal to plus delta O2 by delta T. Clear? Now, the rate of formation of NO2. Rate of formation of NO2, how we calculated it? Rate is equal to, we have used this format, and rate of formation of NO2 means what? Delta NO2 by delta T. This is called rate of, I have told you, we don't include the coefficients for rate of appearance and disappearance. So, rate of formation of NO2 means delta NO2 by delta T. So, what is that? 5 into 10 raised to minus 3 mole per liter by 10 seconds. So, 5 into 10 raised to minus 4. So, this 5 into 10 raised to minus 4 mole per liter per second is delta NO2 by delta T. That is where we stopped, right? I think so. So, delta NO2 by delta T, rate of formation of NO2, answer is 5 into 10 raised to minus 4. Now, second part is rate of consumption of N2O5. Rate of consumption of N2O5 we can do in multiple ways. First one, you can calculate the rate first. Rate is equal to 1 by 4 into delta NO2 by delta T. Okay, calculate rate first. 1 by 4 into the delta NO2 by delta T is 5 into 10 raised to minus 4. So, you can calculate rate and then you can equate rate with this and calculate rate of consumption of N2O5, that is minus delta N2O5 delta T. Or the shortcut is, you can avoid calculating rate. What you can do? You can take these two. Okay, that is minus 1 by 2 delta N2O5 delta T is equal to plus 1 by 4 delta NO2 by delta T. So, what you can do? Minus 1 by 2 delta N2O5 by delta T is equal to plus 1 by 4 delta NO2 by delta T. You can use this relation. So, what is the rate of disappearance of this? It will be 2 into 1 by 4. Therefore, minus delta N2O5 by delta T is equal to, that is this into 2. So, it will be 2 by 4 into delta NO2 by delta T. What is delta NO2 by delta T? I think you got it as 5 into 10 raised to minus 4. So, you will be getting 10 by 4, which is 2.5 into 10 raised to minus 4. That is moles per liter per second. This is the answer for second part. So, in this relation, I have avoided calculation of rate and we have saved that much time. So, this will be better, I feel. Or if you are comfortable by calculating rate first and then going to rate and this relation, that's up to you. Okay. So, this is the answer. So, the second part answer is 2.5 into 10 raised to minus 4 moles per liter per second. Hope that's also clear. Now, this is another repeated board question. The rate constant for a first order reaction is 60 second inverse. How much time will it take to reduce the initial concentration of the reactant to its 1/16th value. Let's see how to do it. Very, very commonly asked and very easy to score. Rate constant is 60 second inverse. So it will be K is equal to 60 second inverse. I know it is little difficult to write with the left hand, but please bear with me. And if it is not readable, legible, please do let me know. Okay. So K is 60 second inverse. How much time will it take? T. How much time will it take to reduce the initial concentration of the reactant to 1/16th value? It's 1/16th. I have told you before, if you deal with percentage, you use R0 as 100. If you deal with fraction, sum of all the fractions is unity. So take R0 as 1. This is a fraction question. So we are going to use the initial concentration as 1. Okay. Now, so what is T? T is equal to, you are told that it is a first order reaction. So T is equal to 2.303 by K log, then it is R0 by R, integrated rate equation. Now 2.303 by K. K is 60 second inverse. Log, then R0. I told you we are going to use R0 as 1 here because it is fraction. So 1 by. What is R? That is a bit tricky here. What is R? It is reduced to, look at the preposition used. It is reduced to 1/16th of the original value. It is reduced to that value, means that is the present concentration. So reduced to means it is not 1 minus 1/16. If it was reduced by 1/16, then 1 minus 1/16. But if it is reduced to, that is the present amount. So R will be 1/16. Please take care. It is not 1 minus 1/16. It is 1/16. So when you do this, log 1 by 1/16, this will become log 16. The value will be given to you in the bracket. They may not give you log 16. They might write log 4 in the bracket. Then students wonder, how can I use log 4 when it is log 16? Come on, 16 is 4 square, right? Log 4 square. So log 4 square is 2 log 4. So it will be 2 times log 4. So 2 times whatever is given for log 4.6021, you can substitute that and get the answer. Clear? So that is how we can use log 4 in the case of 16. So when you do that, you are getting this answer. Time is 4.6 into 10 raised to minus 2 second inverse. Clear? Okay. Similarly, there are questions where time taken for 3/4 completion. 3/4 completion. So 3/4, it is a fraction. So R0 will be 1. 3/4 completion means 1 that is completed. So what is remaining? 1/4 will remain. So 1 minus 3/4. So see the play of prepositions in the question. Okay. Otherwise you might go wrong. Now, next one, the rate of a reaction quadruples. Doubles, triples, quadruples means it becomes 4 times. When the temperature changes from 293 to 313 Kelvin, calculate the energy of activation of the reaction assuming that it doesn't change with temperature. Activation energy is not influenced by temperature. It will be influenced only by the presence of catalyst. Okay. So, here it is written it quadruples. Quadruples means you will take K2 is 4 times K1. That's the meaning of getting quadrupled. Now, this is T1, this is T1, this is T2. I told you higher temperature should be taken as T2. So, this is T2, this is T1 and calculate the activation energy. So, what will you do? Use the activation energy formula. Log K2 by K1 is equal to A by 2.303 R into T2 minus T1 by T2 T1. So you just use this formula. I don't think I have to show you the calculation. This K2 by K1, this part alone, log K2 by K1. So K2 will be 4K1. So this will be 4K1 by K1 is equal to this. So it will become log 4. Log 4 value will be given to you. So 0.6021 is equal to EA by 2.303 into 8.314 into 313 minus 293 by 313 into 293. When you do that, you will get EA value, which is 52.8 kilojoules per mole. That is 52.8 into 1000 joules per mole. That will be the answer what you get. You can try. Okay. Unit is very important. Unit carries half mark. If you don't write the unit, you will lose half mark. Clear? Yeah. This is a trendy question nowadays. This is an exercise question. So we are going to discuss the method. The rate constant for the first order decomposition of H2O2 is given by the following equation. Log K is equal to 14.34 minus 1.25 into 10 raised to 4 K by T. Calculate EA for this reaction and at what temperature will its half-life period be 256 minutes. Exercise question. Commonly seen in papers. So I am going to show you how to do it. Many students have a doubt in this question how to deal with it. You can see. Log K is equal to. So this is in a formula format which you are getting from Arrhenius equation. You have the equation log K is equal to log A minus EA by 2.303 RT. This is a formula what you get from Arrhenius equation, what you derive from Arrhenius equation. So you can see log K is equal to log A. So this is log A minus EA by 2.303 RT is this one. So I am going to compare and take it. So you're getting minus 1.25 into 10 raised to 4 K by T is equal to EA by 2.303 R. R is 8.314 into T. Okay. Now cancel like terms. T and T will go. Now you can see this 8.314 unit is joules per Kelvin per mole. Right. Now this Kelvin and Kelvin inverse will get cut when you calculate. So what is EA? There minus and minus is also getting cut. This minus and minus also getting cut. So what is EA? EA is equal to 1.25, just cross multiply, into 10 raised to 4 into 2.303 into 8.314. Then 1.25 into 10 raised to 4 into 2.303 into 8.314. Then what is the unit? Joules per mole. Whatever you get, so and so joules per mole will be the answer. And the answer is, expected answer is 239.339 kilojoules per mole or into 10 raised 3 joules per mole. Clear? So that is the first part. Calculate EA for this reaction. Mostly it is seen that they can ask you to calculate only EA. But in the exercise question of kinetics, this is the question. At what temperature will its half-life period be 256 minutes? How to do it? Very simple. At what temperature will its half-life period be 256 minutes? So T half is 256 minutes. That should be converted into seconds. So we are going to multiply it by 60. So whatever you get, so and so seconds. That is T half. Then use the formula T half is equal to 0.693 by K. Do you get me? T half is equal to 0.693 by K. So K is equal to 0.693 by T half. So 0.693 by T half. What you get will be K. So first you calculate K. Clear? Once you get K, put it into this formula given to you. This expression. That is log K. What you get is equal to 14.34 minus 1.25 into 10 raised to 4 K by T. And just calculate T. And that T will be 668.64 Kelvin. Clear? That's what you have to do. Now, yeah, this is a very, very, very tricky question. That is seen in many of the latest board papers. This is where we are going to use that shortcut. Okay? Just read the question. A first order reaction is 50% completed in 40 minutes at 300 Kelvin and in 20 minutes at 320 Kelvin. Calculate the activation energy of the reaction. You are given log 2, log 4 and R. Okay. Let's see how to do it. You are given two temperatures. So, and activation energy. So, definitely this is the original Arrhenius equation. So, what is that? Log K 2 by K1. It is log K2 by K1. Just practice this question. Very, very important. Okay. Make sure to practice. Is equal to EA by 2.303 R into T2 minus T1 by T2 T1. So, I will show you the application area. Now, K2 by K1, you are not given, it is getting double, quadruple, triple, nothing or halved, nothing. Okay. So, you are just told that it is 50% completed in 40 minutes at 300 Kelvin. So, 50% completed means it is T half. So, you are given T half at 300 Kelvin. And again, the same reaction is 50% completed in 20 minutes when the temperature is 320 Kelvin. So, you are given two T halves at two different temperatures. So, I have given you a shortcut formula when we discussed the formulas. And what was that? K2 by K1. This is where you are going to use this trick. K2 by K1 is equal to T half 1 by T half 2. I have told you T half and K are inversely proportional. So, it is 2 by 1 means this will be 1 by 2. Inverse proportionality. Clear? So, T half 1 is 40 by T half 2 is 20. That means you are getting it as 2. So, K2 by K1 you got 2. Just substitute into the formula. Log K2 by K1 is 2. So, log 2, that's why you are given log 2 here. So, log 2 is equal to A by 2.303 into 8.314 into T2, that is 320 minus 300 by 320 into 320. This is the application area in this question. Very simple, right? Isn't it? If you know the trick, it is simple. Otherwise, there are many students, they make the process very lengthy. How they will calculate K2 from the given data, they will calculate K1 from the given data, then they will use K2 by K1 here. Why to unnecessarily waste time? Just use the trick. Clear? It is a trick which we develop from the original formulas. Clear? So, the answer expected is 27663.8 joules per mole. Very, very, very important practice. Yeah, that's all from kinetics. Now, we are just going to do some graphical questions. Okay, quickly we will discuss some graphs, and after that you can have a break, have your food and come back. We'll be starting with organic chemistry. Come fresh. Okay. We are going to discuss some important graphs. Okay, so let's discuss some important graphs. First one from solutions chapter, we have to do all these graphs, that is Henry's law, ideal solution, positive deviation, negative deviation, elevation in boiling point and depression in freezing point. Very, very important graphs. So quickly we are going to discuss. You can see this is Henry's law graph. Here pressure is given on the y-axis and mole fraction is given on the x-axis. You know P gas directly proportional to chi gas. So we can see this is showing direct proportionality. Okay. When mole fraction increases, mole fraction of the gas increases, pressure of the gas also increases. This is Henry's law graph. Then if you look at this, this is ideal solution graph. So you can see the two components A and B. So you are familiar with this graph also. I don't think I have to explain this in detail to you. Practice ideal solution graph. But when you come to deviations, positive and negative deviations, here you have to be a bit careful. The green area here in this graph, that is the broken line, it is showing the ideality. Okay. But these blue curves, they are showing the deviation. So you can see if you look at component 1, this is expected from ideality, but it is showing positive deviation. Means this is the expected vapor pressure, so vapor pressure is increasing from that expected from Raoult's law. So it is increasing. Vapor pressure of component 2 is also increasing from that what is expected from Raoult's law. So automatically this is the P total and that also increases. So this is positive deviation, that is projecting graph. That is just like convex, right? Like that. So this is like concave, hanging graph. So here again the green part is the ideality, and you know when you come to component 1, this is the expected value or expected one from Raoult's law. It is less than what is expected from Raoult's law. So it is vapor pressure is less. Here also vapor pressure is less for component 2. So total also less. So you have to understand when you come to azeotropes, I'm just telling you, those solutions show positive deviation from Raoult's law. Vapor pressure is more. When vapor pressure is more, boiling point is less. So vapor pressure inversely proportional to boiling point. So those solutions which have positive deviation from Raoult's law, they will form minimum boiling azeotrope. Whereas negative deviation from Raoult's law, they will form maximum boiling azeotropes. Okay, just practice. Now, this is also very important. Elevation in boiling point. This is what I told you when I told about proportionality. Just look here. Here we have vapor pressure. This is the target pressure, that's atmospheric pressure, and temperature in Kelvin along the x-axis. You can see this line, this curve is representing the vapor pressure curve for pure solvent. That is, when temperature increases, vapor pressure is also increasing. And you know, when we increase the temperature, the vapor pressure will keep on increasing, and when it becomes equal to the atmospheric pressure, when it becomes equal to the target atmospheric pressure, it will boil. So for the pure solvent, when we increase the temperature, vapor pressure is increasing. When it becomes equal to the target pressure, atmospheric pressure, it will boil. So that is T0B. Now, when you add a non-volatile solute into it, its vapor pressure gets decreased. Okay, vapor pressure gets decreased. So you can see the solutions graph is below the solvent graph. What does that mean? Because vapor pressure got lowered when you added a non-volatile solute into it. Now, there also when you increase the temperature, vapor pressure goes on increasing. When it becomes equal to that of the external pressure, atmospheric pressure, it will boil. That is TB. So you can see delta TB is, TB is higher than T0B. So when you added a non-volatile solute to make a solution, the boiling point increases. Boiling point of the solution is more than that of pure solvent. That difference is called elevation boiling point. So what I told you before is, I think before I told you, the delta TB is directly proportional to lowering of vapor pressure. This is delta TB. You can see this gap is same as this gap, isn't it? It is like that. Okay. So delta TB is directly proportional to lowering of vapor pressure. Important for assertion reason. And you know, I have done one assertion reason area. One video is there on assertion reason from solutions. Make sure to go through all those videos if you have time, if time permits, you can see all these questions. Okay. So this is the boiling point elevation graph. Now, when you come to freezing point depression graph, you can see I have pure solvent. You know, previous case you were heating. Now you are cooling. So we have to start from here. You are going to decrease the temperature. This is temperature axis. This is vapor pressure axis. When you decrease the temperature, vapor pressure is also decreasing. Okay. So for the liquid solvent, when you decrease the temperature, vapor pressure is decreasing. At a particular temperature, you can see the liquid solvent changes its physical state to solid solvent, frozen solvent. So that point, very, very important. Okay. Even in 2022 term 1 paper, there was a question based on this to label particular area. That is, what is this indicating? Okay. Very important. Each point they will label and ask you to indicate what it means. So this point is when liquid solvent changes into frozen solvent. So that is, you can see it is the temperature at which the solvent freezes. So this is T0F. Okay, this is T0F. Now what happens is, you added a non-volatile solute into it and it became a solution. Decrease the temperature. The solution gets cooled, and when the vapor pressure of the solution, see, when you decrease the temperature, vapor pressure is also decreasing, and when it becomes equal to that of the solid solvent, that is here, when the vapor pressure of the solution becomes equal to that of the solid solvent, it will freeze. So this is TF. This is T0F. This is TF. That means TF, that of the solution, is less than that of T0F. So we say there is a depression in freezing point. And the delta TF will be directly proportional to lowering of vapor pressure. Clear? So these graphs you have to practice very, very well. Clear? Now, when you come to, those were from solutions. Now coming to electrochemistry. In electrochemistry, this is the most important graph. I think all of you know it. This is variation of molar conductivity with concentration. Here the square root of C, and here it is molar conductivity. This is KCl, which is a strong electrolyte. For a strong electrolyte, when you decrease the concentration, the molar conductivity increases. But it is not increasing dramatically. There is a steady increase when you decrease the concentration. This is strong electrolyte. And if it is a weak electrolyte, what will happen? When you decrease the concentration, initially there is small slight increase in lambda m. Okay? ideal. Okay, so if you take acetic acid, which is a weak electrolyte, what will happen? You can see when you decrease the concentration, there is a small and slight, very slight increase from the initial area. So slowly it is increasing. When you decrease the concentration, lambda m is increasing slowly initially. But when it comes to a very low concentration, you can see almost at infinite dilution, that is zero concentration, there is a quick and steep increase in lambda m value. This, if you see such a graph, then it is indicating weak electrolyte. And let us also discuss what is the reason for this. For a strong electrolyte, what is the speciality? It is a repeated board question, graph and associated explanation. For a strong electrolyte, it ionizes completely at all concentrations, means concentrated solution, dilute solution, whatever, it will ionize completely. So when you decrease the concentration, when you increase dilution, number of ions will remain the same because it is ionized completely every time. But when you add more and more solvent into it, the freedom of movement of ions increases. That is why it is showing a steady increase. Okay. But when you come to weak electrolyte, it is special. How does it behave? It will ionize only little in concentrated solution, but it will ionize more in dilute solution. So when it is concentrated, it is ionizing only little, number of ions are less. But when you decrease the concentration, more and more ions are produced. And when you come to infinite dilution, large number of ions are there. Plus the freedom of movement is also increasing. So these two combined, that is number of ions are increasing, then the freedom of movement is also increasing. When they reinforce, there is a quick and steep increase at infinite dilution. So you should know this graph clearly and the explanation also very well. It is a repeated board question. It is highly expected. So refer and learn. Okay. And they have given such questions, such graphs, and they will give you A and B. They will ask you to identify whether A is a weak or strong electrolyte. If you have the concept, you can easily do it. Clear? Then when you come to kinetics, this is the normal, rate graph, that is concentration versus time. This is reactant graph because when time increases, concentration will decrease. But if it is product, when time increases, product concentration will increase. Okay, this is just their representation, that's all. And they have asked one question, I think 2 years back. That is, they have given such a graph and they have given the concentration here and time here, and they didn't give the order of the reaction. You have to calculate, you have to find out the order of the reaction. So it was seen that 10, 20, then 40, 30, 40 like that, and T half, T half is a constant for first order. So you could compare T half, and if it is constant, then you can predict the order as 1. So there are questions like that you can practice. Then when you come to kinetics, the next one, zero order, concentration versus time graph and half-life versus R0. This is concentration versus time graph. Very, very important. If you have practiced the previous year's questions, you would have seen this. Okay. Now, concentration versus time. This is a descending graph. Descending graph. That is why the slope is negative. Okay. Slope is equal to minus k. K is equal to minus slope or slope is equal to minus k. Very, very important. Master it. And what about the y-intercept? This is the y-intercept. Y-intercept is R0. Okay. And if you want to know the half-life versus R0, it is not there in the textbook. I'll show you how to do it. Half-life versus R0. So suppose this is T half, half-life versus R0. For a zero order reaction, T half is equal to, what was that? T half is equal to R0 by 2K. I have told you before when we discussed the formulas, T half, this is R0 is coming in the numerator. So T half is directly proportional to R0. T half and R0 are directly proportional means you'll be getting a graph like this. Clear? This is not there in the textbook. If you want to note it down, please do that. Hope you noted it down. Okay, now coming to concentration versus time for half-life versus R0 I discussed already. Then coming to first order, concentration versus time graph, log R versus time, then half-life versus R0, log R0 by R versus time. Out of this, these three are there in the textbook. This is not there. I'll show you how to do it. You can see concentration versus time, first order. If you look at this, it is quite similar to the previous graph which we discussed. That is, for zero order, this was just R versus time. But for first order, this is ln R. Understand? ln or log normally comes in first order when you compare 0 and first. Okay. So this is ln R versus time. But the graph looks similar. That is a descending graph. Again, slope is equal to minus k. So how will you identify zero order and first order graphs here in this context? Same graph you will be getting, but if it is concentration here, just R in square bracket. R in square bracket here means it will be zero order. But if it is ln R, it will be first order. automatically slope is also same, k minus k, and here there is a difference. Y-intercept is where the graph cuts the y-axis. Y-intercept is ln r0, whereas for 0 order it was simply r0. Here it is ln r0. Now this graph, on the y-axis it is log r0 by r, and x-axis there is time. Log r0 by r and time, direct proportionality. You can see it is ascending graph, and you know the graph originates from 0, so there is no y-intercept because it is starting from 0. Y-intercept is 0, and slope is k by 2.303. Clear? Then half-life versus R0. Yes, that I will demonstrate. It is not there in the text, so you can note it down. Here we have T half, and here we have R0. And you know for first order, T half is 0.693 by K, right? The formula. So T half is equal to 0.693 by K. There is no R0 coming anywhere in the formula. That means it is independent of R0. It is independent of R0 means T half is a constant, you can see. Okay. So T half is a constant. It does not depend on R0. It doesn't change with R0. So this will be the graph what you get when you get T half versus R0 for first order. Clear? Okay. Now ln k and 1 by t. ln k on the y-axis, 1 by t on the x-axis. You are getting a descending graph. That is why slope is negative. Descending graph, always slope will be negative. If it is ascending, after cutting the y-axis, then it will be y-intercept and slope will be positive. Okay. So this is slope is equal to minus Ea by r. And what about the y-intercept? Where it is cutting the y-axis, it is ln a. Practice. These are all from the textbook, but important. That's why I have quoted them. Then this is log k versus 1 by t. Previous one was what? It was ln. Now this is log. Log k versus 1 by t. Same type of graph. But because it is log, ln and log, they are related through 2.303. You know that. So slope is equal to minus Ea by 2.303 r. Previous one was slope is equal to minus Ea by r. Then here y-intercept is log a. Where it cuts, the y-axis is log a. Previous case, it was ln a. Clear? Yeah. That's all about the graphical questions. I hope it is clear. And you can take a break for your dinner, because some of you will be attending from India. That's your dinner time. And people from Bahrain, you can, have some refreshment and come back. Okay. So next one, we'll be going to organic chemistry. Okay. So come fresh. Okay. Bye. Shubham, for arrangement questions, it is not compulsory to give explanation. You can simply give the arrangement. But if time permits and if you aim perfection, centum score, you can just give a brief explanation in the bracket. Means what is the basis of arrangement. That's all. Otherwise, it is not mandatory. Okay. Otherwise, also you'll get full mark. If you simply give the decreasing or increasing order of arrangement, you can do that. Okay. As I told you, if time permits and if you want perfection, only if time permits, you can just write the basis of arrangement in the bracket. Clear? Next session, how much time you need break? Half an hour to have dinner? Because organic chemistry session will be little longer. And after organic chemistry session, we'll be doing coordination compounds, D and F, and biomolecules. Okay, we'll be covering all these areas today. So you can take half an hour break and come back. Right? Hi dears, are you all back? Yes, now organic. Yes. Please give me a hi if you are back. Great. Okay, so we are going to start with organic, right? You know we have 4 organic chapters. First one, haloalkanes, haloarenes. Then alcohols, phenols, ethers. Aldehydes, ketones, carboxylic acids. Then amines. Okay, 4 organic chemistry chapters. Ready? Ready everyone? Hi. Okay. So we are going to start with, especially for organic chemistry, NCERT textbook is very, very important. The solved example, let it be solved example or in-text question, exercise question, you have to master it very well if you want to score in organic chemistry, class 12. Okay. So we are going to see with special focus to NCERT textbook. Okay. Let's start. First one, haloalkanes and haloarenes. First of all, let us discuss SN1 and SN2 mechanism. SN1 and SN2 mechanism and related arrangements. When you come to SN1 mechanism, SN1 mechanism is shown mainly by tertiary alkyl halides. Tertiary more than secondary more than primary. That is the order of reactivity of alkyl halides in SN1. SN2 is primary more than secondary more than tertiary. So I'll just write it here. If it is SN1, it is tertiary more than secondary more than primary. Whereas if it is SN2, and definitely methyl will come after this, okay? Methyl halide will come after this. Now, SN2 mechanism, the opposite order, that is methyl halide will be the most reactive in SN2 mechanism, more than primary, more than secondary, and more than tertiary. Now, discussing one important area. In SN1 mechanism, in SN1 mechanism, that is substitution nucleophilic unimolecular, in SN1 mechanism, it happens in 2 steps. First step is the formation of carbocation. So, SN1 mechanism proceeds through the formation of carbocation, right? So, it depends on the stability of the carbocation. More stable the carbocation, more will be that alkyl halides reactivity towards SN1 mechanism. Tertiary carbocation is more stable than secondary, more than primary, and methyl is the least. That is why it follows this order in SN1 mechanism. And also please remember SN1 mechanism, this is a clue to be remembered. SN1 mechanism and beta elimination, they follow the same trend. That is tertiary more than secondary, more than primary. Okay, keep it in mind. SN1 and elimination, same trend. Now, when you come to SN2 mechanism is about steric hindrance. You have to think about steric hindrance. Steric hindrance is least, means SN2 reactivity will be maximum. In methyl, steric hindrance about the carbon connected to halogen is least. So that is the most, in methyl it is all small hydrogen atoms, right? All small hydrogen atoms. So these are offering very less steric hindrance to the carbon which is connected to halogen. This is called electrophilic carbon because this is minus and this is plus. So the positive carbon is called electrophilic carbon. Very less very less steric hindrance around the electrophilic carbon. But when you come to primary, okay, let me change this into R. RCS2X, it is primary. Carbon connected to halogen is connected to one carbon. So it is primary. Now this is bulkier compared to previously present hydrogen. So more hindrance around the carbon, steric, electrophilic carbon. More steric hindrance means less reactivity. Now if I replace one more hydrogen by R, it becomes a secondary alkyl halide where the hindrance is more. So the attack of the incoming nucleophile on the electrophilic carbon will be even more difficult. So it will be even less reactive. And in tertiary, this is also R. Maximum steric hindrance, most difficult entry of the attacking nucleophile onto the electrophilic carbon. So it becomes difficult. That is the least reactive. So keep this in mind. Primary SN1 means it is based on stability of carbocation. This is the order. SN2 means it is based on the steric hindrance around the electrophilic carbon, and this is the order. Clear? And SN1 and beta elimination, they follow the same trend. Register it. Now, and one more thing, let me talk about that also. SN1 mechanism is followed by, it's coming up anyway, I am indicating it now itself. SN1 mechanism is followed by racemization, and SN2 mechanism is followed by stereochemical inversion. So keep that in mind. Now, important PYQs. And you know, all these are from textbook. Okay? Just a matter of practice. I will just show you how to do them. I am not going to do all of them individually. I will just tell you what are the important areas, how to do them, because you are already familiar with this. This is an alkene. This is HBr. Nothing is written on the arrow. Means it is simply Markovnikov addition. Markovnikov addition means H plus will go, see these are the two carbons. On this carbon there is only one hydrogen. This carbon there are two hydrogens. What is Markovnikov's rule? The positive part of the addendum goes to the carbon holding greater number of hydrogen atoms. So H plus will come here and Br minus will come here. So you will be getting benzene with CH, Br and CS3. That is the answer. It is a solved example in your text. Please go through. Then here also nothing is written on the arrow means it is again M rule, Markovnikov's rule. And this is not a symmetrical alkene. On this carbon one hydrogen, this carbon two hydrogens. So what will happen? H plus will come to this, making it CS3 by breaking the double bond, and this will come here. So we'll be getting CS3, CS2, CH, Cl, single bond, CS3. Then what about this? Here you can see it is written peroxide. Okay, peroxide. Peroxide means it is anti-Markovnikov addition. Addition happens against Markovnikov rule. So plus and minus. So H plus will come to the carbon holding lesser number of hydrogen atoms. On this carbon 1, this carbon 2. Br minus will come here. So you are getting this product. That is, it will become CS2 single bond CS2 Br. Practice it very well. All are board questions. Then next one, explain why. This is an exercise question but repeated board question. So I have quoted it. Give reason questions. The dipole moment of chlorobenzene is lower than that of cyclohexyl chloride. I have done all these things in my previous videos. So anyway, we will discuss it once more. You know, this is chlorobenzene and this is cyclohexyl chloride, right? Now, in chlorobenzene, chlorine is connected to this carbon, which is a part of the benzene ring. So it is sp2 hybridized. This carbon is sp2. Okay? Whereas the other carbon in cyclohexyl chloride, chlorine is connected to this carbon, which is connected to all single bonded. There are all single bonds on that carbon. That means it is sp3. So this carbon is sp2, this carbon is sp3. You have studied sp2 carbon is more electronegative than the sp3 carbon, more percentages character. So because this is more electronegative, this bond, this electron pair will be pulled closer to it. So making a shorter bond. This is a shorter bond. And due to resonance, there is a partial double bond character also. Okay. But this is a true single bond. So this bond is shorter than this one. So what will happen? You have studied mu is equal to, that is dipole moment mu is equal to the distance and charge product. That is charge and product of charge and the distance between the two charges, opposite charges. Here the distance is less compared to, this is a longer bond, it is a single bond, this is a partial double bond, and it is a shorter bond. So here what happens is, mu is equal to E into D. This D is less here, so this will be less, having mu less compared to this one. Clear? So two reasons. One is sp2 hybridization of the carbon holding the chlorine, making it a shorter bond, more electronegative, and partial double bond character due to resonance. Okay, and mu is equal to D into E. Hope that's clear. Then alkyl halides, though polar, are immiscible with water. You have studied like dissolves like. Alkyl halides are polar, but water to water bonds are stronger. Okay, so it is difficult to break those water to water bonds. So and it is difficult for the alkyl halides to be miscible with water. It is also there in the textbook. We can go through it. Then Grignard reagent should be prepared under anhydrous conditions. Grignard reagent is highly reactive. So if there is moisture anywhere surrounding Grignard reagent, it will undergo hydrolysis. That is, if you have RMgX. RMgX is Grignard reagent. It will combine with water. Water is H plus and OH minus, right? And here this is R minus and Mg is plus. So you will be getting RH. For example, if it is methyl magnesium halide, you will be getting methane. It will undergo hydrolysis to form the corresponding hydrocarbon, alkane, and you will be getting MgXOH. So to prevent this, you won't get Grignard reagent isolated. It will undergo hydrolysis. So to prevent its hydrolysis, because of its high reactivity with water, you have to prepare it under anhydrous conditions. I know you may have prepared all these things, but revise. Okay, all are repeated board questions. Now, this is also an abstract from your textbook. Very, very, very important. Write the structure of the major organic product in each of the following reactions. The first one, CS3, CS2, CS2Cl, alkyl halide with NaI and acetone. So, what is the product? NaI, acetone and heat with an alkyl halide. What is it? It is Finkelstein reaction, right? Okay, halogen exchange. So this Cl will go out and iodine will come here. So we'll be getting CS3, CS2, CS2I plus NaCl, Finkelstein reaction. Then next one, CS3 thrice CBr plus KOH. Ethanol and heat means it is alcoholic KOH and heat. That means it is elimination. So what will happen? It is CS3 thrice CS3 thrice CBr. Then alcoholic KOH means it will undergo beta elimination, right? So this is alpha, halogen connected carbon is alpha, and these are all beta. So from any one carbon, any one beta carbon, you can remove one hydrogen. So if I am removing it from here, you will be getting what? CS3, C, then I removed it from here, so I will put CS2 here, double bond CS2, and here it is CS3. And that is, it is 2-methyl propene, 2-methyl prop 1-ene. And that removed HBr can combine with the KOH to form KBr and water. Okay, this is the major, only major product is asked, so this is the major product. Hope it is clear. Then next one, many students make a mistake in this, though it's very simple. CS3, CHBr, CS2, CS3. It is written NaOH and water. NaOH and water means it is aqueous. So it will undergo a nucleophilic substitution. So what will happen? Replace Br by OH. So it is CS3, CHOH, CS2, CS3. Okay, 1, 2. So butane, 2-ol. It was 2-bromobutane. Now it will become butane 2-ol. It is just nucleophilic substitution. Then what is this one? CS3, CS2Br plus KCN aqueous ethanol. Means alcoholic KCN. So what will happen? You will get CS3, CS2Cn. But if it is AgCN, you will get isocyanide. You know that. This is potassium cyanide. So you get corresponding cyanide, nitrile. And C6H5ONa plus C2H5Cl. This is Williamson synthesis. Just remove NaCl. So you'll be getting 6H5O C2H5. You'll be getting ethoxy benzene. Okay. Then CS3, CS2, CS2OH plus SOCl2, thionyl chloride. Then the OH will get replaced by Cl. Preparation of haloalkane you have studied. So you'll be getting CS3, CS2, CS2Cl. Then this is HBr and peroxide. Peroxide means it is anti-Marconic of addition. So H plus, Br minus. These are the two carbons holding the double bond. Here only one hydrogen, here two. So H plus will go to the carbon holding lesser number of hydrogen atoms because it is against Marconic rule, and Br minus will go to the carbon holding greater number of hydrogen atoms. So we'll be getting CS3, CS2, CS2, single bond, CS2, Br. Now last one, it is just written, CS3, CS double bond, CS3 twice plus HBr. Nothing is written on the arrow, means it is normal Marconic of addition. So H plus will come to the carbon holding greater number of hydrogen atoms. Here there is one, here there is none. So H plus will come here and Br minus will come here. Understand? So whenever peroxide is written on the arrow, think about anti-Marconic of addition. If it is not there, means in such cases, think about Marconic of addition. Clear? So this will be CS3, then CS2, single bond, CBr, CS3 twice. Okay? Now, arrangement questions. Arrange the compounds of each set in increasing order of reactivity towards SN2 displacement. So, we can arrange them in increasing or decreasing order. If a particular order is mentioned in the textbook, you have to strictly follow that. Okay? Otherwise, you can write increasing or decreasing order. Now, how to do it? You know, it is SN2 mechanism, what is mentioned here. SN2 means, I have told you, it is primary more than secondary, more than tertiary. Methyl more than primary, more than secondary, more than tertiary. That is SN2 mechanism. So you just find out 2-bromo, 2-methyl-butane. 2-bromo, just like this, you will write the structure. 2-bromo, 2-methyl-butane. You know how to make the structure. 2-bromo, 2-methyl-butane. You know this carbon holding Br is connected to 3 other carbons. So it is tertiary, right? Then 1-bromopentane. You know when you write the structure, you will be getting it as primary. 2-bromopentane is secondary. So just follow this order. Primary more than secondary more than tertiary. Okay. Similarly, in each case, you find out whether this primary, secondary or tertiary and arrange accordingly after drawing the structure. After making the structure. Clear? So just prepare it. But if there is, if all of them are primary, 1-bromobutane, 1-bromo 2,2-dimethylpropane, 1-bromo 2-methylbutane, then 1-bromo 3-methylbutane, all of them are primary. Okay. In that case, you have to see the proximity or nearness, okay, of the branch to the electrophilic carbon. So just practice. Then what happens when N-butyl bromide is treated with alcoholic AOH? N-butyl bromide means what? It is N-butyl bromide means it is 1-bromobutane, normal butyl bromide. N-butyl bromide is treated with alcoholic AOH. Alcoholic AOH means it will be beta elimination, right? Alcoholic AOH means it is beta elimination. So this is alpha carbon to which the halogen is connected. This is beta carbon. So beta elimination. Beta hydrogen goes with alpha halogen. So the product will be CS3, CS2, CH3, CH2, then CH double bond CH2. You'll be getting but1e. Then bromobenzene is treated with magnesium in the presence of dry ether. Bromobenzene is treated with magnesium in dry ether. It is latest board question. So this is haloarine plus magnesium in the presence of dry ether. You will be getting Grignard reagent. That means you will be getting phenyl magnesium bromide. Phenyl. You can put the ring inside or alternate single and double bonds. That's up to you. But in the textbook, in the question paper, whatever is given, you can follow that. So it is phenyl magnesium bromide, that is Grignard reagent. Then chlorobenzene is subjected to hydrolysis. When chlorobenzene is subjected to hydrolysis, it will form phenol. First it will form sodium phenoxide, then it will form phenol. So that reaction you can take from the text. That is there in the text. Methyl bromide is treated with sodium in the presence of dry ether. Alkyl halide with sodium in dry ether means it is Busch reaction. So what will happen? Methyl bromide plus Na plus next molecule of methyl bromide. So 2NaBr will be removed and you will be getting CH3CH3. That is, you will be getting ethane, Busch reaction. And methyl chloride is treated with KCl. We have already studied a similar question. Methyl chloride with KCN. Alcoholic. So KCl will be removed. Cl will be substituted by Cn. So we will be getting CH3Cn, methyl cyanide. Okay. Simple questions. Then arrange each set of compounds in increasing order of boiling points. Yes, this is also a repeated board question. Increasing order of boiling points. Bromomethane, bromoform, chloromethane, dibromomethane. Bromomethane is CH3Br. Then next one, it is bromoform. Bromoform is CHBr3. Just a second. Then chloromethane. Then dibromomethane. Dibromomethane. Here, how to arrange them in the increasing order of boiling point? You know, here you have to check the molar mass. The more the molar mass, higher will be the boiling point. Clear? So, you have to check, this is chlorine, all others are bromine. Chlorine is less massive, atomic mass of chlorine is less than that of bromine. So, methyl chloride less than methyl bromide, less than means the number of bromines increases means the molar mass also will increase. So, methyl chloride less than methyl bromide, less than dibromomethane, less than bromoform. So, that is the increasing order of boiling points. I hope that's clear. Next one, 1-chloropropane. 1-chloropropane, CS3, CS2, CS2Cl. 1-chloropropane, isopropyl chloride. If you don't know what is isopropyl chloride, you can't proceed. Isopropyl chloride is actually 2-chloropropane. Okay, 2-chloropropane, that is isopropyl chloride. Next one, 1-chlorobutane. 1-chlorobutane. So what will you do in this case? You know, these two are isomers. They have 3 carbons. They have the same molar mass. But you have studied, more the number of branches, lesser will be the boiling point because area of contact will be less. Okay, it assumes the shape of a sphere. You have studied it. So this has more branches. So this will have lower boiling point than this one. So this one, isopropyl chloride less than 1-chloropropane and less than this one because this has 4 carbon atoms. So it will be more massive than the prop. Bute is more massive than prop. So molar mass is more. So this will have the highest boiling point. So what is the increasing order? Isopropyl chloride less than normal propyl chloride, that is 1-chloropropane, less than 1-chlorobutane. Clear? Definitely, I will, okay, I will explain racemization and inversion of configuration. Let's complete this first, okay. After this, yes, biomolecules coming up. After the organic, it is biomolecules, and after that, after this, it is coordination compounds. Then comes biomolecules, then D and F and coordination compounds in a quick session, because I have done one shot on them. You can watch them. All of those topics are covered in that. So I don't think we have to spend a lot of time on those. If you watch those videos, you can easily get almost everything from those two one shots. So today I am focusing on the other areas so that we can cover maximum. Which alkyl halide from the following pairs would you expect to react more rapidly by SN2 mechanism? Again, you know, SN2 mechanism means it is all about what? Steric hindrance. SN2 mechanism is all about steric hindrance. So you have to check whether it is primary, secondary or tertiary. SN2 mechanism, what is the order? Primary more than secondary more than tertiary. This is the order of reactivity in SN2 mechanism. So CS3, CS2, 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 Br, you know it is primary. Br connected to this carbon, it is connected only to one other carbon, primary. Br connected to this carbon, connected to two other carbons, this is secondary. So out of these two, which one will react faster in SN2? Primary. Okay, because less steric hindrance. That also you have to mention better. Here, this is secondary as we discussed, but this is tertiary. You can see Br connected to C, connected to three other carbons. So it is tertiary. So secondary more than tertiary. Secondary has less steric hindrance than tertiary. Then when you come to this, this is primary. This is also primary. This is what I told you in one of the previous arrangements. Both are primary. Then students get confused. Okay, both are primary, then which one? Are they having equal reactivity? No. What you have to do is, when both are primary, you have to check the position of branching. Is it near to carbon holding the halogen or away? Here it is near to the carbon holding Br. So the hindrance, because the nucleophile will be attacking this carbon. So this is closer to that. So the hindrance, steric hindrance will be more. But here nucleophile is attacking this carbon, electrophilic carbon, but the branch is away from that. So steric hindrance will be less. So which one will react faster? This one will react faster because it has less hindrance. This one has more hindrance. Clear? Okay. Now, in the following pairs of halogen compounds, which compound undergoes faster SN1 reaction? You know, for SN1, what is the order? Tertiary more than secondary more than primary, right? So if you look at this, this is the carbon, you know, it's a bond line formula, CS3, CS3, CS3. So this carbon is connected to three other carbons, so it is tertiary. So this tertiary alkyl halide, here this is the carbon connected to Cl, it is connected to two other carbons, so it is secondary. And which one will react faster? Okay, so here this is tertiary and this is secondary. And we are doing SN1 mechanism. So SN1 mechanism, tertiary more than secondary, right? So automatically this will be more reactive than this one in SN1 mechanism. Then what about this? Here this is CS3, CHCl, CS2, 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 CS3. So this is secondary because this carbon is connected to two other carbons. So it is secondary. What about this one? Chlorine connected to this carbon, it is connected to only one other carbon. So it is primary. Which one will react faster? Secondary more than primary. So this will react faster. Reason? If you are asked for reason, make sure to write about steric hindrance for SN2 and stability of carbocation for SN1. Make sure to do that, okay, if reason is required. Now, the last one. This is the latest board question from this chapter, okay, commonly asked and latest asked in 2023. Cyclohexyl bromide, you know, this is equivalent to alkyl halide plus Mg. Alkyl halide or alicyclic or aliphatic or even aryl halide with magnesium in dry ether, you will be getting Grignard reagent. So what is A? Alkyl magnesium halide. The halide is Br. So cyclohexyl magnesium bromide will be A. That is undergoing hydrolysis. As I told you, Grignard reagents are highly reactive. They will undergo hydrolysis. How? This bond will get broken. It will get H here and OH here. So this carbon is positive. This carbon is negative. So it will take up H plus of water. Mg is positive. It will take OH minus of water. So you will be getting cyclohexane. That is corresponding hydrocarbon. Clear? So practice all these questions well. I told you NCERT textbook compulsory. Okay, you have to do all the solved examples, syntax questions, exercise questions from the NCERT textbook if you want that magic score, centum, 70 upon 70. Especially book 2 is very, very important. All the questions, exercise questions, solved examples, index questions, everything, organic chemistry. That's why I am focusing on all these areas. Then, all these questions, why is sulfuric acid not used during the reaction of alcohols with Ki? You know, sulfuric acid is an oxidizing agent. It will oxidize, it will first it will convert Ki into Hi. That is, potassium iodide will be first converted into Hi by sulfuric acid. And that Hi will get oxidized to iodine by sulfuric acid. So, to prevent this, we are not using sulfuric acid. Okay, better to give this. You can see all these are textbook questions, but I have quoted them so that you will understand their significance and practice them. Then, write the structures of different dihalogen derivatives of propane. It's not that commonly asked. Okay, but how will you do it? You know, propane, dihalo derivatives. Dihalo derivatives means, I'll give you the trick how to do it. First of all, put both the halogens on this carbon. So you'll be getting 1,1-dichloropropane. Then put one here, 1,2-dichloropropane. Then put both the chlorines here, 2,2-dichloropropane. And then then if you come here, if you put one chlorine here and one chlorine here, it will be again 1,2-dichloropropane. Both of them here will be 1,1. So it will be similar to the others. So you can substitute hydrogens one by one and check what are the products. But this question is extremely important, highly possible. Among the isomeric alkanes of molecular formula C5H12, identify the one. You know, pentane has 3 isomers. What are they? Normal pentane, isopentane and neopentane, right? So, normal pentane has, you know, CS3, CS2, CS2, CS3. I'll just show you here. Just a second. Okay, I'll write here better. I'll write here, okay. CS3, just to explain it. CS3, CS2, 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 CS3. This is normal pentane. And how many types of hydrogens are there? This and this are same. Whether you substitute here or here, it is same. Equivalent from both ends. This and this are same. Because it will be 2 second carbon's hydrogen substituted from left. If it is here, second carbon's hydrogen substituted from right. But this is different. See. That means there are 3 different types of, 3 different types of hydrogens we can substitute by halogen. Okay. So 3 isomeric monochloride means it will be this one, normal pentane. Then let us see isopentane. I'll show you isopentane. What is isopentane? Isopentane is CS3, CH, CS3, CS2, CS3. This is isopentane, right? 2-methyl butane. Now, these 2 methyls are equivalent with respect to CH. So if this is A, this is also A. Then this is a different carbon and hydrogen, B. This is different, C. This is different, D. So if you substitute here, you will get chlorine here or here, it is same. Chlorine here, you will get something else. Chlorine here, you will be getting something else. You can try the IUPAC names and check. And chlorine here, it will be something else. So you will be getting 4 different monochlorides. So 4 isomeric monochlorides that will be produced from which one? Isopentane, 2-methylbutane. And now let us see who produces only one type of monochloride. So normal pentane, isopentane. Now neopentane. What is neopentane? Neopentane is CS3, C, CS3, CS3, CS3. 2,2-dimethylpropane. That is neopentane. You can see all these 4 methyl groups are equivalent with respect to the central carbon. So if this is A. So all of them are equivalent. Wherever you substitute hydrogen, you will be getting the same product only. So this one will produce only one single monochloride. I hope this is clear. Okay. So this question is commonly asked. See, I would say if you want to get passing mark in chemistry, just practice like what I told you. If you attend this session itself, it is more than enough to get pass mark, guaranteed. Okay, because we are discussing all the possible questions. If you practice them well, not passing mark, you can easily score in 70s or 80s if you are aiming passing. But others, if you give proper attention and practice, very easy to score centum. You have seen the students' frames which I demonstrated. They are the latest toppers. Many of them are 70 upon 70, 69 upon 70. I was waiting for some more photographs. I didn't get it. Okay, so I just posted which all are available. So you can be one among them. Why not? 1 or 2 or 10 among them. Okay? Right. So this question is very, very important. Okay, now let's go to the next question. So make sure to practice this question. Okay? Now, next. This is also a very important question. I have selected only such questions which are highly expected in the forthcoming exam, day after tomorrow. I am pretty sure many of these questions you can see in your papers. Okay? So practice. Draw the structures of major monohalo products in each of the following reactions. You know, this is cyclohexyl alcohol or cyclohexanol with SOCl2. So, you know, when an alcohol reacts with the SOCl2, the OH will get replaced by Cl. Okay? Only major product is asked. So, it will be cyclohexane plus Cl. I think one of you, Sridhar, I think you asked me about coordination compounds. One question I have seen. So, I will be answering your query when we reach coordination compounds, right? Okay. That's why I didn't answer it yet. So, here the product will be cyclohexane with chlorine. Replace OH by chlorine. Then, coming to this one. Yeah, this is a very tricky question. So, it's a commonly asked question. You can see bromine heat or UV light. That means it is substituting hydrogen by bromine. And many students, they will substitute this end hydrogen, that is the end carbon's hydrogen by bromine, which is wrong. This is primary carbon. So these hydrogens are primary hydrogens. This is a secondary carbon because it's connected to two other carbons. And these are secondary hydrogens. And you should know what is the order of ease of replacing hydrogen atoms, substituting hydrogen atoms. And that order is tertiary more than secondary more than primary among these. Tertiary more than, actually allylic, then benzylic, more allylic, benzylic most, then tertiary, then secondary, then primary, then vinyl aryl. That is the order. So you can see this is primary, this is secondary. So which hydrogen can be easily substituted, secondary or primary? Secondary. So one of these hydrogens will be taken out and you will put the bromine here. That is the answer. Not at the end. Keep it in mind. You can expect any of this in your paper. Okay. Now this one, another tricky question. You can see two OH, two hydroxyl groups here, treated with HCl. Which OH will get replaced by Cl? You know this OH is directly connected to benzene ring. So there is a partial double bond character. Cannot be broken easily. It cannot be substituted. But this OH is away from the benzene ring. It is connected to CS2. It can be easily substituted and chlorine will take that place. So the answer will be, what's the answer? It will be, this OH will remain here. Okay. This will remain here. Nothing will happen to it. But this OH will get replaced by Cl. Clear? Then coming to the fourth one. Another tricky question. It is written, this cyclohexene connected to methyl group. HI, you know this is an alkene basically. HI, H plus and I minus. Nothing is written on the arrow, means you have to follow Marconic rule. So what will happen? These are the two carbons holding the double bond, right? Here there is one hydrogen. You can count the valency. 1, 2, 3, 4. Okay. On this carbon, it is 1, 2, 3, 4. On this carbon, 1, 2, 3, 4. There is no hydrogen here. This carbon, one hydrogen. This carbon, no hydrogen. So H plus will go to the carbon holding greater number of hydrogen atoms. And I minus will go to the carbon holding lesser number of hydrogen atoms. So what will be the product formed now? The product formed will be, this will become CH2. So, and double bond is broken. Already CH3 is there. And then I minus is connected to the same carbon. So this is the answer. Highly expected. Very, very, very important. Clear? Now, if they write peroxide on the arrow, it will be anti-Marconic of addition. But this is the most commonly asked question. Sometimes I have seen instead of HI, they may write HBr. Then in the place of I, you have to put Br. Read the question properly. What is the halogen used and then do accordingly. Clear? Then coming to this, very simple. It is Finkelstein reaction, halogen exchange. Take out Br and put I there. This is the answer. And this is another tricky question. You can see cyclohexene. We are adding bromine and we are heat and UV light. You are adding bromine to this, but it is not addition what is taking place. It is substitution what is taking place according to the condition provided, heat and UV light. So, which hydrogen to be substituted? Be very, very vigilant. You know, let us see. These are the carbons, okay? This is how you have to apply. These are the carbons. This is a secondary carbon, secondary carbon, secondary carbon, secondary carbon. These two are double bonded carbons, secondary. But you know, this carbon is connected to a double bonded carbon. So this is allylic carbon, okay? It is allylic carbon. This carbon is also connected to double bonded carbon. So it is allylic carbon. These two carbons are part of the double bond, okay? So they are vinylic. So where? So everywhere there are hydrogen atoms, you know that. When you satisfy the valencies, remaining valence is hydrogen. What is the order what I told you? Order of ease of substituting hydrogen atoms. Allylic, benzylic, tertiary, secondary, primary, vinyl, aryl. So vinyl, no chance. These two are vinyl, no chance. These two are allyl, yes. Allylic is the most. Allylic, benzylic is the most. These are secondary. These two are secondary. Less chance. So what you can do is, here you can substitute any of the allylic carbon. You can put the bromine here or here. Okay. Both are correct. So the answer will be double bond is broken, right? Double bond is present there, not broken, sorry. Double bond is present there. Now I have to put B because it's substitution. So you have to put the Br here, or instead of this you can put the Br here. Both are correct. Just a second. Okay, you can put the Br here. So whether you write it like this or putting in the bromine here, both are correct. Okay, so these are the important questions from that area. Hope that's clear. Okay, now I have just quoted this area for a purpose. You know, this is chlorobenzene's nucleophilic substitution. You know, chlorine is connected to this carbon of the benzene ring through partial double bond character, so it is difficult to get cleaved. Normally, it is haloarine, but under special conditions, chlorine will get substituted by OH, and this is the condition. NaOH, 623 Kelvin, 300 atm pressure, then you will get sodium phenoxide intermediate, which will undergo hydrolysis to form phenol. This is what is happening. But, okay, this is chlorobenzene to phenol. We have done one question before. Okay, chlorobenzene subjected to hydrolysis, you are getting phenol. I told you through sodium phenoxide. Final product is phenol. But here there is one electron withdrawing group NO2 present. When electron withdrawing group is present, what will happen? It will weaken this bond and removal of Cl becomes more easy. So it can be substituted. If there are two electron withdrawing groups, both of them will withdraw electrons. So it will become double weak. It will be weaker than this. More easy substitution. If there are three electron withdrawing groups, this will become triple weak. The most easy situation to replace Cl by OH. So you can see the conditions. Here high temperature, high pressure, etc. Here high pressure is not required. 1 atm is the normal atmospheric pressure, but this is 300 times of the normal atmospheric pressure. High pressure, high temperature. Here normal atmospheric pressure, but temperature is again lesser than the previous one, indicating the ease. The more the number of withdrawing groups, then conditions are getting milder and milder. Finally, when there are three withdrawing groups, just warm water can do the work for you. And this is very important for naming also. 2,4,6-trinitrophenol, commonly asked, whose common name is picric acid. Picric acid. Clear? And as I told you, the purpose of giving this is, they have asked these two commonly in papers. They will give you the LHS, they will write the conditions on the arrow, will ask you to fill the RHS. So I have quoted these from the textbook. Clear? Now just note these things. Yes, here I will be explaining the racemization and stereochemical inversion. Okay, after this. Enantiomers have the same boiling point. You know, enantiomers, they differ only in optical rotation. If one is dextrorotatory, the other one will be levorotatory, right? They have all the other properties same. You know, if you have plus butan-2-ol and minus butan-2-ol, they cannot be separated by fractional distillation. Fractional distillation is based on the difference in boiling point. They have the same boiling point, so they cannot get separated by fractional distillation. Very important, asked in recent papers. Then, allylic and benzylic halides undergo SN1 mechanism due to resonance stabilization of the carbocations. You know, there is a trend in recent board papers. They will ask you out of chlorobenzene and benzyl chloride, which one undergoes hydrolysis easily, or SN1 mechanism easily. Chlorobenzene partial double bond character, it cannot undergo hydrolysis easily. Benzyl chloride, yes, because its carbocation is resonance stabilized. So in the pair, If haloarine like chlorobenzene comes, don't select that, it will not undergo hydrolysis easily. But allylic, benzylic, alkyl, etc. paired with haloarine, that will be undergoing hydrolysis easily. Because allylic or benzylic means their carbocations are stabilized, and the figure is also there in your textbook. Please practice. Then SN2 mechanism is followed by inversion of configuration. I am just going to explain because there is a request. What is meant by inversion of configuration? Suppose I am starting with CH3Br. Okay, CH3Br, methyl bromide. It is being attacked by OH minus. You know, this OH minus will prefer attacking the electrophilic, this is the electrophilic carbon, okay, Br minus and C plus, this is the electrophilic carbon. It is supposed to attack this one, right? So it will try to enter not from this side, instead it will try to enter from this side. What is the reason? Two reasons. One is steric reason and second one is electronic reason. What is it? Here Br minus will repel OH minus. Electrostatic force of repulsion. Okay, like charges repel. It cannot enter easily. Secondly, you know, this is a bulky group. So steric hindrance will be more and it is difficult to get attacked. So instead of coming from this side, it will attack from this side where there are only small hydrogen atoms and there is no repulsion from Br minus because it is away. Okay, so it will attack it from here. So to pave way for attack, this will get, this will get rearranged and you will be getting an intermediate like this. H, then here there will be OH and here there will be Br. This is the intermediate what is formed, like an inverted umbrella, what you have studied in the mechanism. Then this is an intermediate, it is a transition stage actually, that is a better name. And now what happens is, slowly this bond will get broken and it will go, okay. It will go out as Br minus. Now this will become straight. Just see, it will get adjusted like this. Yes, now look at this product. Where is the OH group present? I think you can understand. Where is the OH present? In the original one, it was Br at the right side. Outgoing nucleophile is at the right side and these were at the left side. Now it got inverted. How? The attacking nucleophile came on the left side and the entire stereochemistry arrangement got inverted. That is why we say in SN2 mechanism there is complete stereochemical inversion because it is mainly based on steric hindrance. Clear? Now when you come to SN1 mechanism, I'll show you that also. You know, here everything is happening in one step, right? So this is what is happening. Now suppose we take SN1 mechanism. Yes, in SN1 mechanism, it passes through what? The formation of carbocation. So suppose I have CS3 thrice Br, a tertiary alkyl halide. You know, SN1 mechanism happens through two steps. So first is the formation of carbocation. And carbocation is like this. Okay, once the Br minus goes out, you are getting the carbocation like this. Carbocation, the centrally placed C is sp2 hybridized. So it will be trigonal planar. So just imagine trigonal planar intermediate, carbocation intermediate. It can be attacked from this side or from this side, right? Equal chance of being attacked by the attacking nucleophile. So if it is coming from one side, suppose it is dextro. If it is coming from the other side, it will become levo. So there is 50-50 chance. That is 1:1 ratio. You will be getting both the enantiomers. D isomer and L isomer will be getting in 50-50 ratio. That is why 50:50. That's why we call it as a racemic mixture. That's why we call it as racemization. So SN1 mechanism is followed by racemization. SN2 mechanism is followed by stereochemical inversion. Is it clear? Hope it's clear. Okay, now coming to ambident nucleophiles. What are ambident? That is a sure question. Okay, commonly asked in papers. So better to prepare. Ambident nucleophiles like cyanide, it can bind through C or N. Then nitrite, it can bind through N or O. You have studied all these things, right? So these are all ambident nucleophiles where there is more than one binding site in the nucleophile. Okay, so just go through that. One example compulsory. Okay. And that's all about haloalkanes and haloarenes. Next is alcohols, phenols and ethers. If you have any questions, you can ask me now because it is organic. If you want to clarify something, you can ask me now. Okay, now let's pass on to alcohols, phenols and ethers. All right. First of all, there are some important mechanisms in alcohols, phenols and ethers. And I have mentioned them. It is just a matter of you having a writing practice. Okay, write and practice. Written practice is compulsory for mechanisms. So, ethanol to ethene, 100% sure. Take my word, 100% sure you will get one mechanism. And it can be ethanol to ethene, 3-step mechanism. Ethene to ethanol, ethanol to ethoxyethane. These are the 3 mostly asked mechanisms. That's why I have highlighted them. Okay, normally it is one among these 3. But there are some more mechanisms like nucleophilic addition of Grignard reagent to carbonyl group, then alcohol as nucleophile, protonated alcohol as electrophile, small mechanisms. You please take them from your textbook. Direct questions, no applications. Then important name reactions. You know from organic chemistry, all name reactions are very important because they may make conversions. They will ask you to, okay, write short notes on. Okay, name reactions. Or using name reactions, they will ask you conversions. Using name reactions, they will ask you to complete. Okay, complete and write the major product. So, name reaction compulsory to be prepared. Okay. So, hydroboration oxidation, that is propene to propan 1-ol. Remember, hydroboration oxidation equivalent to anti-Marconic of addition of water to alkene. Then, Kolb's reaction, Remarkman reaction, Williamson synthesis. Practice them well. Kolb's reaction is what? Phenol to salicylic acid. Okay, so Kolb's reaction is conversion of phenol to salicylic acid. Remarkman reaction is conversion of phenol to salicylaldehyde. Then Williamson synthesis is conversion of alkyl halide into ether by reaction with sodium alkoxide through SN2 mechanism. So practice all of them very well. And now this question from alcohols is very important. Solved example. Give the structures and IUPAC names of the products expected from the following reactions. Catalytic reduction of butanol. You know butanol, on reduction you will get butanol. So what is that? Butan 1-ol. Because aldehydes on reduction you get primary alcohol. Clear? So this is aldehyde. On reduction you will get primary alcohol. So butanol is CS3. Listen well. It is CS3, CS2, CS2, CHO. This is butanol. When it is reduced, you know what will happen? The CHO will change into CS2OH. The CHO will change into CH2OH. So what is the product? CS3, CS2, CS2, CS2OH. Register it. Many students think CHO is replaced by OH. That is wrong. CHO will be replaced by CS2OH. Then hydration of propene in the presence of dilute sulfuric acid. If you have propene is CS3. I'll use a different ink better. Okay, it is CH3. What is propene? Propene is CS3, CH, double bond, CH2. That is propene. Hydration of propene means you add water, H plus, OH minus, in the presence of dilute sulfuric acid. So, you know, this is acid catalyzed hydration of alkene. Then you will get corresponding alcohol. That is, it is as per Markovnikov's rule. So, H plus will go to carbon holding greater number of hydrogen atoms. OH minus will go to carbon holding lesser number of hydrogen atoms. So, you will be getting CS3, CH, OH, CS3. You will be getting propan 2-ol. Understand? If it is acid catalyzed hydration of alkene, you will be getting addition as per Markovnikov's rule. But if they tell you according to hydroboration oxidation, then addition of water to the alkene, if they write BH3 twice, then H2O2 bar OH minus, that is hydroboration oxidation, you will be getting propan 1-ol because it is anti-Markovnikov addition. Clear? Then reaction of propanone with methyl magnesium bromide. Okay, propanone is CS3, CO, CS3. I'll show you a trick here. This is propanone with methyl magnesium bromide. Methyl magnesium bromide followed by hydrolysis. You know, when Grignard reagent reacts with a ketone, understand, Grignard reagent plus methanol, you will get primary alcohol. Grignard reagent plus any other aldehyde other than methanol, you will get secondary alcohol. Grignard reagent plus a ketone, you will get tertiary alcohol. Register these things. So this is Grignard reagent plus a ketone. You will get tertiary alcohol. And in tertiary alcohol, OH is connected to carbon, connected to 3 R groups. So this is one R group, this is the next R group, this is the next R group. So what will be the product formed? CS3 thrice COH. Got the trick? You will be getting an adduct intermediate which will undergo hydrolysis to form this product, that is 2-methyl propan 2-ol. Okay, practice it. Okay, now show how are the following alcohols prepared by the reaction of a suitable Grignard reagent on methanol. This is the same thing what I told you now. Grignard reagent plus methanol, you will get primary alcohol. Okay, you know, see the trick what we are going to use. This is a primary alcohol. OH connected to this carbon, connected to one other carbon. So it is a primary alcohol for sure. So suitable Grignard reagent on methanol. So methanol is already there. So methanol plus which Grignard reagent, you will get this alcohol. The trick is methanol is what? HCHO. Okay, you can easily identify what is the Grignard reagent. So XCHO means CS2O. So CS2O I am removing from that. So this is representing methanol. Then that adduct is followed by hydrolysis. So that H plus is coming from hydrolysis. So remove that primary alcoholic part from that. Then remaining part will be your R. So this is the R in RMGX. So what is the Grignard reagent? CS3, CH, CH3, then this is the R, then MgX. That X can be chlorine, bromine, iodine, whatever, except fluorine. So this is the Grignard reagent. Got the trick? Easy, right? Now, similarly, look at this. You try. This is the alcohol. It is a primary alcohol, right? CS2O is coming from methanol. H plus is coming from the hydrolysis area. Basically, you remove the primary alcoholic group completely. Then you have cyclohexyl group. That is your R group. Understand? So, the Grignard reagent will be cyclohexyl magnesium halide. Okay, it can be chlorine, bromine or iodine. Got the idea? This is how you can do it. Then write the structures of the products of the following reactions. This is the same thing but we have done before. You are adding water in the presence of H plus. So, Marconic of addition. Okay, H plus will come here, OH minus will come here. So, you will be getting propan 2-ol. This is a commonly asked question in papers because many students make it wrong. You have a ketonic group and an ester group. It is undergoing reduction. You can see sodium borohydride reducing agent. So, nothing will happen to the ester linkage. Don't touch that area at all. Instead, this ketonic group will change into alcoholic group. So, this double bond O, you will make single bond OH. This will be your answer. Okay, double bond O, replace it by single bond OH. Ketonic group is changing into it's getting reduced to secondary alcohol. Ester will remain like that. Then, in this case, again, sodium borohydride, it is used to reduce the aldehyde group into primary alcoholic group. Aldehyde into primary alcohol. Simple, right? So, it will be CS3, CS2, CH, CS3, CS2OH. That's how you have to do it. Okay. Now, arrange the following sets of compounds in order of their increasing boiling points. Again, among more the number of carbon atoms, higher the boiling point because higher the molar mass, higher the boiling point, stronger the van der Waals forces of attraction. And among isomers, if there is branching, boiling point will be lesser. So, pentan 1-ol, 5 carbons, butan 1-ol, 4 carbons, butan 2-ol. These two are isomers. These two are isomers. Ethanol has only 2 carbons. Propanol has 3 carbons. Methanol has 1 carbon. So, what is the increasing order of molar mass? Methanol lowest. So, it will have the lowest boiling point. So, methanol less than ethanol. Then comes propanol. Then comes butanol. But among butanol, butan 2-ol is branched. So, that will have lower than butan 1-ol. And highest is pentan 1-ol. Clear? Hence the order. Similarly, when you come to the second one, pentan 1-ol, N-butane, pentanal, ethoxyethane. What's the difference? For the first one, all were alcohols. But second one, different functional groups. This is an alcohol, this is hydrocarbon, this is aldehyde, this is ether. You master this arrangement. It will help you a lot in the board examination. Hydrocarbon less than ether, less than aldehyde, less than ketone, less than alcohol, less than carboxylic acid. That is the increasing order of boiling point. Master it, make it by heart. So, hydrocarbon is normal butane, less than ether is ethoxyethane, less than aldehyde is pentanal, and then alcohol is pentanol. So, this is the increasing order. Clear? Not this order. It will help you. The next one, arrange each set of compounds in the increasing order of boiling points. I think, sorry, this got repeated from haloalkenes, sorry about it. Then arrange the following compounds in increasing order of their acid strength. You know, acid strength depends on the strength of the OH bond. If the OH bond is very strong, H plus cannot come out easily. Acid will be weak. But if the OH bond is weak, H plus can come out easily. Acid will be strong. Keep it in mind. So propan-1-ol, alcohol. Alcohol is weaker than phenol and carboxylic acid. So 2,4,6-trinitrophenol, 3-nitrophenol, 3,5-dinitrophenol. So and 4-methylphenol. I will just explain the effect of substituent on the acidity of phenol. Look here. This is phenol, right? If there is an electron withdrawing group on phenol, suppose there is an electron withdrawing group on phenol, what will happen? It will withdraw electrons towards it. That impact will happen here also, here also. So the OH bond will become weaker or will become more polar and H plus can come out very easily. The more the number of withdrawing groups, weaker will be the OH bond and more will be the acidic strength. But when you come to this 4-methylphenol, methylphenols are called cresols, you know that. 4-methylphenol. What is the speciality of methyl group? Methyl group is electron releasing. So it will release electrons here, here also. So the OH bond will become stronger because more electrons are flowing into that area, making it less polar. H plus cannot come out easily. So understand, phenol, nitrophenol, methylphenol. Nitrophenol is stronger than phenol. Why? Because of the presence of NO2 group, making the OH bond weaker and more polar. This one, it is electron releasing group, making the OH bond stronger and less polar. So this is weaker than phenol, this is stronger than phenol. Keep it in mind. And alcohol is weaker than phenol. So if you look at this, this is alcohol. Here there are 3 nitro groups. Here only 1 nitro group. Here 2 nitro groups. So what is the order? Here phenol and here methylphenol. So which is the least acidic? Alcohol. Then among phenols, 4-methylphenol will be weaker than phenol, right? So next one is 4-methylphenol, then comes phenol, okay? Propanol, methylphenol, phenol. Then comes 3-nitrophenol with only 1 nitro group. Then 3,5-dinitrophenol, then 2,4,6-trinitrophenol. The more the number of nitro groups, electron withdrawing groups, stronger the acidity. Stronger the acid, more the acidity. Clear? So it is also very important. Next one, I won't say this is a repeated board question, but it is seen in some board papers. So let us discuss that also. Write the structures of the major products expected from the following reactions. Mononitration of 3-methylphenol. You know, 3-methylphenol is this much. What is 3-methylphenol? 3-methylphenol is this. Okay. Mononitration means you have to introduce 1 nitro group. Then, you know, this OH group is ortho-para-directing. Methyl group is also ortho-para-directing. These two are ortho positions. This is para position. So anywhere NO2 group can come. When you look at methyl, it is also ortho-para-directing. So these two are ortho. This is para. Now, what is the best position? If you put nitro group here, suppose instead of this you are putting it here, lot of steric hindrance. They are close by. So the molecule will not prefer this position. Then only this and this. That is why it can be this way or this way. It can be here or here. So this one and this one are the possibilities. Then what is dinitration of methylphenol? Both here and here you can put NO2 group. That is dinitration of phenol. The third one, there is mononitration of phenyl methanoate. Actually, it is phenyl ethanoate because it is OCOCH3. This is phenyl ethanoate, and mononitration means bring 1 NO2 group. Then one will be para, one will be ortho. Para is more stable than ortho. So that is given there. That's a major product. Then predict the major product of acid catalyzed dehydration. of 1-methyl cyclohexanol butyl malone? This is a very important question. Just a second. Okay. 1-methyl cyclohexanol. What is 1-methyl cyclohexanol? One methyl cyclohexanol. You know, this is cyclohexanol. 1-methyl. 1-methyl means the methyl group is also here. It is undergoing acid catalyzed dehydration. Listen very well. You can see the OH holding carbon. This carbon is alpha, right? Then this carbon is beta. This carbon is beta. This carbon is also beta, right? So acid catalyzed dehydration means it will be undergoing beta elimination. So you can see if this OH is going with this H, means this alpha and this beta hydrogen is going out, then the product will be, you know, the double bond will be created between this alpha and this beta. So it will be double bond CH2. Okay, this CH3 will become CH2, double bond CH2. Next one is, what is the next chance? You can see, suppose this OH is going with, you know, here there are two hydrogens. We are not showing it because it is bond line, that's all. Here also there are two hydrogens. So both are equivalent with respect to the central carbon. So if this OH is going with this H, then a double bond will get created here. Okay. So then it will be, see, CS3 we are not doing anything. It is there, I didn't use it. But double bond is between this alpha and this beta as per my drawing. Or it can be between this alpha and this beta also. So there are two chances, two alkenes possible. Okay, when you do acid catalyzed dehydration of 1-methyl cyclohexanol. Now out of these two, which one is the major product? It depends on Seitz of rule, you know that. Here carbon is connected to two hydrogens, less alkylated. But here these are the two carbons holding the double bond. This carbon has one alkyl group on it. This carbon has only one hydrogen. You should understand terminal alkenes. That is where CS2 double bond is coming. You know that carbon is having both the hydrogen atoms, no alkyl groups. So that will always be the minor product. This one having more alkylated alkene, that is more alkyl groups on carbon holding double bond, that will be the major product. So methyl cyclohexene will be the this is the major product, this is the minor product. Clear? Very important question. Now let's go to butan 1-ol. Butan 1-ol is CS3, CS2, 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 OH. What will happen if it undergoes dehydration? Butan 1-ol using you know, this is alpha and this is beta, right? So butan 1-ol means there is only one beta carbon and its beta hydrogen. So there are no multiple chances, it is only like this. So double bond will get created here. Okay. So the product will be CS3, CS2, then CH, double bond, CS2. You will be getting but 1E. No application of states of rule here. Okay. Now, this is a trendy area in recent board papers. Those who have done recent board papers, you know it very well, right? The following is not an appropriate reaction for the preparation of tertiary butyl ethyl ether. You know here alkoxide is primary, alkyl halide is tertiary. And you know alkoxide plus alkyl halide giving ether, it is SN2 mechanism, Williamson synthesis. Depends on steric hindrance. So here the alkyl halide is highly hindered. So it will not undergo easy substitution. Instead, it will undergo elimination. That means when they register it properly, when the alkyl halide is tertiary, it will never undergo Williamson synthesis easily. It will undergo beta elimination. So this is alpha, these are all beta, 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 beta. So if you are removing HCl, you will be getting what? CS3 thrice, CS3 thrice, CS3 twice, C double bond CS2. You will be getting 2-methyl propene. You will not get this either. Clear? Because it undergoes elimination. So what would be the major product of this reaction? Major product of this reaction will be 2-methyl 1-propene. I have shown you how. And write a suitable reaction for the preparation of tertiary butyl ethyl ether. If you want tertiary butyl ethyl ether, do one thing, make the alkyl halide primary and alkoxide tertiary, no problems. Then it can undergo Williamson synthesis easily. So alkyl halide primary, alkoxide tertiary, you will get the ether. But if it is alkyl halide tertiary, alkoxide primary, you will not get ether, instead you will get alkene. Very, very important. Register it, highly possible even this year. Now, give the major products that are formed by heating each of the following ethers with HI. Tricky area, common question. I will give you some tricks here. Whenever you are doing the cleavage of an ether, breaking of an ether with HI, you see the left side and right side of the ether linkage. Classify them as primary, secondary and tertiary. Work is very simple. Okay. Now, this is primary. This is also primary, you know. This is primary alkyl group. Don't think that because there is branch it is secondary or something. O is connected to this carbon. That carbon is connected to one other carbon. So, it is primary. This is also primary. Now, you are going to cleave it with HI. Now, what happens is, this is a smaller alkyl group. This is a bigger alkyl group. So, when you cleave it with HI, when both are primary, I minus will go with the smaller alkyl group, preferring less hindrance, and H will go with the next one. So, what is the product? CS3, CS2, CS3, CS2, OH plus CS3, CS2, I minus goes with the smaller alkyl group. And coming to the second one, you can see this is primary, whereas this area is tertiary. And understand, if one of them is tertiary, HI's I minus will always go with tertiary and H will go with this part. Okay, because this will be forming a carbocation easily. Tertiary carbocation is highly stable. So I minus will go and get connected to the C plus. Okay, so that is the answer, you can see. And here, you know, this O is connected to benzene ring. There is a partial double bond character here. So it cannot be cleaved. So cleavage is only happening here. So O minus will take out H plus and CS2 will take I minus. So it will be benzyl iodide plus phenol. Very, very important area. Now, this is also a latest board question. Which of the following is an appropriate set of reactants for the preparation of 1-methoxy 4-nitrobenzene? Very simple. Here, halogen is directly connected to benzene ring. there is a partial double bond character, cannot be cleaved. Here there is a partial double bond character. So this area cannot be cleaved. So it will not work. But here it is ONA. So this can go with this easily. CS3 can come there. You can get the required either. Clear? Then predict the products of the following reactions. This is again ether with HBr. You know this is this part is primary. This is also primary. Then when you come to HBr, yeah, after this question, I will take a break to change the battery pack. Okay. So here, you know, this is smaller, this is bigger. So H will go with this, I minus will go with this. So the product will be CS3, CS2, CS2, OH plus, not I minus, sorry, Br, and CS3Br. Second one, you know, this bond cannot be cleaved because it is connected to benzene, partial double bond character. This cannot be cleaved. So it get cleaved here, H here, and I minus here, Br minus here. So we'll be getting phenol plus C2H5Br. Here again, it is not cleavage by HI. It is just nitration of this. You know, either linkage, either group is orthopara directing. So you'll be getting para-nitro ethoxybenzene, and the next one will be orthonitro. Para is the major product, so this will be the answer. And this one, this is tertiary, this is primary. And I have told you, whenever tertiary is there, that bond will be broken because it is plus, I minus will go there, and H will come here. So it will be CS3 tri-Ci and C2H5OH. These are all board questions. Make sure to practice. I'll take a 5 minutes break to change the battery pack. I'm back. Okay. Now, this is another board question. Okay. While separating a mixture of ortho and para-nitrophenols by steam distillation, name the isomer which will be steam volatile. You know, orthonitrophenol has intramolecular hydrogen bonding, para-nitrophenol has intermolecular hydrogen bonding. So, orthonitrophenol will be steam volatile, so it can be easily separated from the mixture. So, which one is steam volatile? It is orthonitrophenol. What is the reason? Because of intramolecular hydrogen bonding in orthonitrophenol. You have to show the intramolecular hydrogen bonding. Then explain why is orthonitrophenol more acidic than orthomethoxyphenol. I have already told you, nitro group is electron withdrawing, makes the OH bond weaker and more polar. H plus can come out very easily, so that will be stronger. In orthomethoxyphenol, methoxy group is electron releasing. Okay. Before we did methyl, now I'll show you methoxy also. This is orthomethoxyphenol. Methoxy is OCS3. You know, methoxy group is electron releasing. So what will happen? It will release electrons here also. It will make the OH bond stronger. So it cannot break easily, giving out H plus, or OH bond's polarity is reduced. Okay. So it is also a board question. Now, how are the following conversions carried out? Number one, this is to be prepared exercise question. Okay. If you haven't done it yet, try to. Propene to propan-2-ol. As I told you, propene plus water on the arrow H plus. As we have done it 2 times already in today's session. Propene plus water on the arrow H plus, you will get propan-2-ol. Benzyl chloride to benzyl alcohol. That I will demonstrate. Benzyl chloride. What is benzyl chloride? Benzene with CS2Cl is benzyl chloride. This is a common question in papers. To benzyl alcohol. Benzyl alcohol is benzene with CH2OH. Benzyl alcohol. Now, you can see the Cl is just replaced by OH. So, use aqueous KOH or aqueous NaOH. That is nothing but nucleophilic substitution. You can use aqueous NaOH or aqueous KOH, anyone. Then next one, ethyl magnesium chloride to propan-1-ol. Yes. Look here. This is also the technique what I told you. I'll show you how to do it easily. Simple ones. Provided you understood it properly, okay? Otherwise, they might be the most difficult ones. So, ethyl magnesium chloride. Look here. Ethyl magnesium chloride. That is Grignard reagent, you know. To propan-1-ol. I'll show you the trick what we are going to use. Propan-1-ol. It is Grignard reagent. By the way, can you all see this ink properly? Otherwise, I will change it into white. Can you respond? Please respond so that. Okay, so this is Grignard reagent. This is primary alcohol. I have told you how to convert Grignard reagent into primary alcohol. Grignard reagent plus methanol, you will get primary alcohol. Remember this trick. Grignard reagent plus methanol. So, this is C2H5. Here, C2H5 is already there. Remaining part what is left out is CS2O, which is methanol. So, you can write it is 1, you add methanol, then you will get an adduct, 2 follow by hydrolysis. H2O bar H plus. That's it. Okay. Now, methyl magnesium bromide to 2-methyl propan-2-ol. methyl magnesium bromide to 2-methyl propan 2-ol. Let's see what's the trick here. Same thing. Methyl magnesium bromide. Methyl magnesium bromide. It is CS3MgBr. Methyl magnesium bromide to 2-methyl propan 2-ol. 2-methyl propan 2-ol means it is tertiary alcohol, right? Grignard reagent to 2-methyl propan 2-ol tertiary alcohol. Grignard reagent plus what is tertiary alcohol? Ketone. So which ketone? The methyl group, one of them is provided by Grignard reagent. Remaining 2 should come from your ketone. So you will write 1 CS3 twice CO, that is propanone. Then you will get these 2 methyl groups. Then followed by hydrolysis. I think you understood how to do it easily. Okay? Yes, practice. And now name the reagent used in the following reactions. Oxidation of a primary alcohol to carboxylic acid. You can use acidified KMnO or acidified dichromate, any of them. Oxidation of primary alcohol to aldehyde. Primary alcohol to aldehyde, that is controlled oxidation. We can use PCC or CrO3. Bromination of phenol to 2,4,6-tribromophenol, aqueous bromine. Okay. Benzyl alcohol to benzoic acid, oxidation, side chain oxidation, KMnO4 bar H plus. Then that is CS2OH changes into COOH. Dehydration of propan 2-ol to propene. You can use concentrated sulfuric acid, which is a dehydrating agent. Butan 2-on, that is ketone, to butan 2-ol, secondary alcohol. So we can use a reducing agent like sodium borohydride, lithium aluminum hydride, H2 bar Ni, any of them. Okay. So exercise question, practice. Then write equations. These ones you can take directly from your textbook, but all of them are board questions, so I just accommodated them in this session, that's all. Okay. This Frelich-Crafts reaction, alkylation of anisole, directly from the textbook, nitration of anisole, bromination of anisole, Frelich-Crafts acetylation of anisole, anisoles reactions, all are board questions. Then write the equation for the reaction of hydrogen iodide with 1-propoxypropane. What is 1-propoxypropane? CS3, CS2, CS3 is propane. You know that. What is 1-propoxypropane? Take out one hydrogen from here and put propoxy group, propyl and oxy group. So this is 1-propoxypropane. You are going to break it with hydrogen iodide. So both of them are primary and both are, it is a symmetrical ether. So whichever CO bond you cleave, it is the same thing. If you cleave it here, give H here, I here. So we'll be getting propan 1-ol and 1-iodopropane. Okay. Next one, methoxybenzene. Methoxybenzene, OCS3, that is anisole, methoxybenzene. If you cleave this with HI, you cannot cleave this CO bond because it is aryl oxygen bond, partial double bond character. You can't do it. You can't cleave it. Break it here, give H here and I here. So we'll be getting phenol and methyl iodide. Understand? Then benzyl ethyl ether. What is benzyl group? Benzene with CS2 is benzyl. Then ethyl ether. And you know benzylic carbocation is highly stable. I have told you today allylic and benzylic carbocations are stable. So because this benzylic carbocation is stable, it will get cleaved here easily. So give I minus here and H here. So we'll be getting benzyl iodide and ethanol. Okay. All of them are board questions, especially these two are repeated board questions. And now Show how would you synthesize the following alcohols from appropriate alkenes. I have told you today that 1-methyl cyclohexane, that question, what is the product of dehydration using sets of rule. Same concept, but you will do the reverse. That is, you want to prepare this alcohol. Okay, if you want to prepare this alcohol, how will you know what is the alkene? You do the reverse. How to do the reverse? Look here, I'll show you. How to do the reverse? You know, this is C, this is alpha, and this is beta, right? Even this is also beta. These two carbons are also beta. So you can think about, doing dehydration. So if I do that, I will be getting, based on what I drew here, it is double bond CS2. This is one alkene, that is between this alpha and beta we created a double bond. Okay, so you are getting cyclohexane double bond CS2. Then what is the other chance? We can remove from the other, that is, here there are 2 hydrogens, here also there are 2 hydrogens, right, on this beta. So suppose I am removing this OH with this H, then it will be between this alpha and this beta. So what is the product? That CS3 will be there, CS3 is there, then between this alpha and this beta there is a double bond. So these are the 2 alkenes which on hydration, acid catalyzed hydration, will produce this alcohol. Got the trick? Just do the dehydration and see what are the alkenes. That will be the answer. Clear? Practice is compulsory, otherwise it won't be easy. Then what about this one? The carbon holding OH is alpha. This is beta, and this is also beta. Okay, so what are the chances? We can remove, and this is symmetrical, this, both are symmetrical. So whether you remove from here or here, you will be getting one product. So what is that? Then it will be like this. Okay, this OH and this one. So this is one alkene, okay, between this alpha and this beta, or it can be between this and this. It will be same only. The next one is, I can remove it from here and here. This is, this is a methyl group. So in that case, I will be getting what? It will be double bond CH2. From this CS3, this is CS3, from that remove one hydrogen. So double bond CS2. These are the 2 alkenes which will produce this alcohol on hydration. Then similarly, come to this one. Next, I hope you are following me in the trick used. Now, next one, here this is alpha carbon, this is beta, this is also beta. Clear? Now remove from here this OH and this H, then you will be getting what? Double bond will be here. Okay, then next one, this OH and this H, you can remove this OH and this H. In that case, you will be getting this OH and this H. It will be this one. So these are the 2 alkenes which will produce this alcohol on hydration. Clear? Now coming to the next one. Yes, biomolecules, we will do it. Sure. Don't worry. Okay, now this one. So I will do one thing. After this, we'll go to biomolecules. Okay, don't worry. Then we come back to the organic chapter 3. Okay, now this is alpha. Then these are beta. Okay. Now if you remove it from here, you'll be getting double bond. Then, okay, it will be like this. Double bond here. Then the next one, if you remove from the next site, that is this OH and this H, then it will be double bond here, double bond CS2. Then there is one more, you can remove from here, this OH and this H. Then you will be getting then double bond will be here and this will remain there. So these are the 3 alkenes which on hydration you will get this alcohol. Clear? Okay, now so you have to practice this. We never know which one will appear in your paper. But I am going to show you one more question from here which is present in one of the recent board papers. Okay, it is similar to this. And that's CS3. Look here. CH3, C, CS3. Okay. Now it is OH here. You want this alcohol. Which alkene can produce this alcohol? You know this is alpha, these are beta. So you know all these are same. Okay, whether you remove from here, here or here, it is same. So any one is enough. You will get only one chance. And suppose I remove it like this, then I'll be getting CS3, C, then double bond CS2, CS3. This will be the answer. Clear? This is there in one of the recent board papers. Okay, so I hope you understood the concept well. Now, finally, to conclude alcohols, phenols and ethers, this is extremely important. Okay, take my word, this is extremely important. You can get application questions from here. That's why I made it into a chart because it is not clearly given in your textbook. Comparison of orthonitrophenol and paranitrophenol. Orthonitrophenol has intramolecular hydrogen bonding and all properties of whatever question you get from orthonitrophenol, write the reason as intramolecular hydrogen bonding. Clear? That is the reason. And if it is paranitrophenol, write it as intermolecular hydrogen bonding. That's it. Okay. So this is intramolecular hydrogen bonding. This is intermolecular hydrogen bonding. Orthonitrophenol is less soluble in water. What is the reason? Intramolecular hydrogen bonding. This is more soluble in water. Intermolecular hydrogen bonding. More volatile. Why? Intramolecular hydrogen bonding. Less volatile. Intermolecular hydrogen bonding. This is less acidic. Reason? Intramolecular hydrogen bonding. And here it is more acidic. It is intermolecular hydrogen bonding. Master this properly. Clear? You can see in orthonitrophenol it has only one thing more. That is volatility. All others are less. Some clues like that you can register. Okay. So that's all about alcohols, phenols and ethers. Okay. Now in 5 minutes we'll be coming back to okay, as per the request we will go to biomolecules. Okay. And I'll clear that doubt about I think Sridhar has asked me about nickel. Okay. That is what is a weak ligand. Actually it is, I think you meant cobalt. Okay, oxalate is a weak ligand normally. But when it comes with the cobalt, it is cobalt 3+, it acts like a strong field ligand. I think you meant that. Okay, please clarify. Okay, then we'll be going to biomolecules after this. For a change. Am I audible now? Can you comment? Am I audible now? Am I audible? Please do comment. Hairani, am I audible? Thank you. Okay, then I will just repeat. I have included only board questions, okay, from Biomolecules chapter. We can have a quick recap. Classification of monohydrates. This classification is very, very important. That is classification of carbohydrates based on the products formed on hydrolysis. They are classified into three: monosaccharides, oligosaccharides, and polysaccharides. Monosaccharides cannot be hydrolyzed further. Mono means single unit like glucose, fructose, all those are, galactose, all these are simple monosaccharides, cannot be hydrolyzed further. But oligosaccharides, they yield 2 to 10 monosaccharide units on hydrolysis. Like sucrose, it produces glucose and fructose. Then lactose produces glucose and galactose. Maltose, glucose plus glucose. All these are disaccharides, they also come under that category. And polysaccharides means they produce many carbohydrate, many monosaccharide units on hydrolysis. That is more than 10. So that is oligosaccharide. Prepare this area very well from your text. That's why I have got the abstract. And it is a repeated board question for 3 marks. Okay. Now, next one is glycosidic linkage. Glycosidic linkage means the oxide linkage joining 2 monosaccharide units. Let it be a disaccharide or polysaccharide, whatever. That oxide linkage connecting 2 monosaccharide units. That is called a glycosidic linkage. And you know, it was H and OH here. This is CS2OH and OH. OH and OH, when they interact, a molecule of water is eliminated. You know, if it is 2 OH groups coming close by, what will happen? OH and OH. Then a molecule of water, H2O, is eliminated. Leftover is oxygen. That oxygen is present there as oxide linkage. So you can see the 2 monosaccharides are joined together by an oxide linkage formed by the loss of water molecule. See, loss of water molecule. Such a linkage between 2 monosaccharide units is called, through oxygen atom, is called glycosidic linkage. It is a repeated board question. And drawing part, it is not compulsory, but if you aim that dream score 70 upon 70, if that is your target, then better to learn this also. Okay. Anyway, you have to know sucrose structure. Sucrose structure is compulsory. So you just try to learn this one, how to label glycosidic linkage. Now, next one, next board question, invert sugar. What is meant by invert sugar? You can see sucrose. In kinetics, you have studied pseudo first order reaction, which is kinetically, actually it is of higher order, but becomes first order due to the presence of excess of one of the reactants. Like normally it is water. There you have studied inversion of cane sugar. Same thing. Sucrose, whose optical rotation is plus 66.5, when put in water, it will undergo hydrolysis to form glucose and fructose. Glucose, you can see D plus glucose. This stands for dextrorotation. It is plus 52.5. And fructose is levorotatory. It is minus 92.4. You can see something very interesting now. Sucrose was dextrorotatory, plus 66.5. But after hydrolysis, levorotation is overtaking dextrorotation. So the mixture becomes levorotatory. This mixture minus 92.4 means rotation to the left is more than that to the right. So this overtakes this one. What will happen? The mixture becomes levorotatory. So there is a change, inversion of optical rotation. That is why this phenomenon is known as inversion of cane sugar, and the product formed is called invert sugar. Clear? Very, very important. Sucrose is dextrorotatory, but after hydrolysis gives dextrorotatory fructose and levorotatory glucose. Dextrorotatory glucose and levorotatory fructose. Then so it is changing from dextro to levo. So it is called, this mixture is called invert sugar, and the phenomenon is known as inversion of sugar. Okay, just prepare it. It is very important. Okay, now the next one. These are two questions in your textbook. Glucose or sucrose are soluble in water, but cyclohexane or benzene, they are insoluble in water. You know, something is soluble in water means it will be making hydrogen bonds with water, right? So glucose and sucrose, they have OH groups which can make hydrogen bonds with water. OH and CS2OH groups which can make hydrogen bonds with water. So they are soluble in water. But cyclohexane, benzene, etc., they are hydrocarbons which are non-polar. So they cannot make hydrogen bonds with water. Okay, like dissolves, like you know that. Then what are the expected products of hydrolysis of lactose? Lactose is made up of glucose and galactose. Okay, beta D glucose, beta D galactose. If it is sucrose, it is alpha D glucose, beta D fructose. How do you explain the absence of aldehyde group in pentaacetate of glucose? You know, glucose undergoes cyclization, and during that cyclization, you know, it is losing its CHO group in that process. So what is happening is there is absence of free CHO group. Okay, so it is due to cyclization. So the reason for the absence of free CHO group is absence cyclization, due to cyclization. Now this is another repeated board question. What is meant by peptide linkage? Peptide linkage means, you know, glycosidic linkage is the oxide linkage connecting to monosaccharides. This is the peptide linkage connecting to amino acids in a polypeptide chain. Okay. So chemically, peptide linkage is an amide linkage or amide formed between COOH group of one amino acid and NH2 group of the next amino acid. You can see NH2, CS2, COH. This is one amino acid. This is also another amino acid. Now OH group of one amino acid, that is OH from the COOH of one amino acid, goes with H of the next amino acid, NH2 group of the next amino acid. Eliminates a molecule of water, so it will become NH2, CS2, CO, NH, CH, CS3, COOH. That CONH group, that new linkage formed is called peptide linkage. If it is polymer, it will be called amide linkage, but in biochemistry, it is called peptide linkage. Clear? It is also, and this drawing is also compulsory. It is a repeated board question. Then, you know, structure of protein classified into primary structure, secondary structure, tertiary and quaternary. What is primary structure of protein? The amino acid sequence present in the long polypeptide chain. The sequence of amino acids present in the polypeptide chain. That is called primary structure. And if there is any change in the primary structure, it will lead to the formation of a different protein. You know, normal HB and sickle cell HB. Just the change of one amino acid, valine and glutamic acid interchange. That is the reason for the HB being sickle cell. Okay. So it will create a completely different protein. So learn the primary structure of protein. It is a board question. The sequence of amino acids in a polypeptide chain, that is called primary structure, and any change in the primary structure creates a different protein. Clear? Then secondary structure of protein. So through the primary structure you got the long polypeptide chain. Once you got the long polypeptide chain, it can coil further in different ways. That is called secondary structure. So the shape in which a long polypeptide chain can exist, that is called secondary structure, and the two varieties are alpha helix and beta pleated. Okay, very important. Then what is tertiary structure? Tertiary structure means, suppose you have got alpha helix. What is alpha helix? Alpha helix is like this, okay, like a right-handed helix. And what is beta pleated? It is like the pleats of cloth, like curtain or Chinese fan, that is like clothes of, that is like the pleats of drapery, cloth, okay. Now, how they can coil further? This is the secondary structure alpha helix. It can coil further. So, it will become tertiary structure. So, it will result in somewhat a globular protein when come to tertiary. But here, they are getting stacked one after the other. Okay. So, it will lead to fibrous protein. Okay. In tertiary. So, tertiary structure means it represents the overall folding of the polypeptide chains. That is further folding of the secondary structure. So, you are getting two varieties, fibrous and globular. Clear? Then, this is a repeated board question. What are the forces stabilizing the secondary and tertiary structure of proteins? Hydrogen bonds, disulfide linkages, van der Waals forces and electrostatic forces of attraction. These are the forces stabilizing secondary and tertiary structure of proteins. It is a repeated board question, learn it by heart. And now, what is the quaternary structure? You know, quaternary structure is normally formed when there are so many polypeptide chains, okay, which are called subunits. So, that is a complicated structure. It is made up of two or more polypeptides. They get entangled and get converted to the quaternary structure. And now, another repeated board question. What is meant by a native protein? What is meant by denaturation of protein? You know, protein found in biological system with a definite 3D structure and its own biological property. That is called a native protein. So, highly important. Protein found in a biological system with a unique 3D structure and biological activity is called a native protein. Definition, learn it by heart. Now, when a protein in its native form is subjected to physical changes, like changes in temperature, okay, or chemical change, like you can change, you know, you do paving of your hair, right? Isn't it? Use chemical. Your hair contains protein. So, when you do paving or heat treatment, what is happening? That protein in your hair is getting denatured. But that is a temporary denaturation. It can be reversed. So, the opposite of denaturation is called renaturation. But if you take raw egg, okay, it has protein inside, the liquid one. And if you boil the hard boiled egg, you know, it is getting denatured. The protein is getting denatured. But do you think you can ever bring it back to the raw egg? No, it is irreversible denaturation. So, it can be reversible or irreversible. Reverse of denaturation is called renaturation. Clear? Okay. Now, so this part you have to learn well. When a protein in its native form is subjected to physical changes, like changes in temperature or chemical change like changes in pH, hydrogen bonds, that is quaternary structure will unfold to become tertiary. Tertiary will unfold to form secondary. Secondary will unfold to form primary. You will get the long polypeptide chain. But once that long polypeptide chain is formed, then there are peptide bonds. They cannot be broken during denaturation. So, quaternary to tertiary to secondary to primary, it will stop there and it will remain in the primary structure. Clear? Okay. So, it is written, due to this, globules unfold, helix get uncoiled and protein loses its biological activity. That is called denaturation of protein. During denaturation, secondary and tertiary structures are destroyed, but primary structure remains intact. Then some examples are also there. This is taken from your textbook. You please refer. Okay? Very important. Then classification of amino acids. There are two types of classifications. First one is based on the relative number of basic amino group and acidic COH group. Based on this, there are acidic amino acids, basic amino acids and neutral. If amino groups are more than acid, then it is basic amino acid. If COH group number is more than amino group, it is acidic amino acid. If COH and NH2 groups are equal, then it is called neutral amino acid. That is one classification. Second classification is essential and non-essential amino acid. That is, out of the 20 amino acids, 10 of them can be prepared in our body. They are not essential in our diet. They are called non-essential amino acids. Remaining 10, they are essential in the diet because they cannot be prepared in our body. There is a controversy about essential amino acid, whether it is 10 or 9, but your textbook shows 10, so I am going with 10. Okay. So there are 10 amino acids which are called essential amino acids, which are essential in the diet because they cannot be prepared in our body. They are called essential amino acids. So I have done videos on that. You can just go through. Okay. So classification of amino acids, you have to go through this. It is taken from your textbook. Then classification of vitamins. Vitamins can be these are all board questions. Okay. Classification of vitamins. They can be classified into two: water soluble vitamins and fat soluble vitamins. The vitamins which are soluble in water, they are called water soluble vitamins. They are vitamin B complex and C, vitamin C. Whereas fat soluble vitamins, they are soluble in fats or fat solvents. Okay. And they are vitamin A, D, E and K. Very, very important. Okay. Repeated board question. I don't think I have read it for you. You please go through the textbook. Okay. Very important. Then this is also taken from a textbook. That is name of vitamins, sources and deficiency disease. Very, very important. Even in 2023 paper, deficiency of vitamin C was asked in one set. Then vitamin D was asked in another set, and vitamin K was asked in another set. Okay. So please make sure to go through this chart. It is extremely important. Then these questions. Why cannot vitamin C be stored in our body? I have already told you it is water soluble. So if we take excess of vitamin C in our body, what will happen? Body will absorb whatever it can. Then it cannot be stored in our body. Any excess taken will be excreted through body fluids like urine, sweat, etc. So they will not get deposited in our body. It will not lead to hypervitaminosis. Okay. Then what products would be formed when a nucleotide from DNA containing thymine is hydrolyzed? Nucleotide is sugar plus base plus phosphate. Okay. That is sugar plus nitrogenous base plus phosphate. That is called nucleotide. Sugar plus base is called nucleoside. That is also very important. We are coming up to that. And DNA containing thymine is hydrolyzed. So sugar. What is the sugar present in DNA? Deoxyribose sugar. Beta D 2-deoxyribose. That is the sugar. Then phosphate is there. Then nitrogenous base. What are the nitrogenous base present in DNA? Adenine, guanine, cytosine, thymine. Okay. These are the 4 bases present in DNA. If it is RNA, in the place of thymine, it will be uracil. Okay. And sugar will be beta D ribose. Then when RNA is hydrolyzed, there is no relationship among the quantities of different bases obtained. What does this fact suggest about the structure of RNA? It means that RNA is single-stranded. If it is DNA, it is double-stranded. So A will make hydrogen bond with T, adenine with thymine, and cytosine with guanine. A double bond T, hydrogen bond. G triple bond C. So that is called specific base pairing. So when you hydrolyze, A will be equal to T and G will be equal to C because they are paired like that, specific base pairing. But there is no such base pairing in RNA because it is single stranded. In DNA, the 2 strands are connected through these specific base pairings. Okay. So it means that RNA is single stranded. And now this is what I told you, nucleoside and nucleotide. What is nucleoside? You can see it is the pentose sugar. This much is the pentose sugar. You can see this much is the pentose sugar. Okay. And there is a nitrogenous base connected at 1' position. 1 with a slash is called 1'. Why we are giving this prime symbol because there are carbons in the base as well as in sugar. So to identify the carbon present in sugar, we are giving prime, okay? And what is there in the base, we are not giving the prime symbol, just to distinguish between the two. So the pentose sugar plus base, nitrogen base connected at 1' position, that is called nucleoside. What is nucleotide? You know, this much is nucleoside, okay? That is, it was OH, okay? This was nucleoside. Now it is combining with a phosphoric acid, that is, this is OH. So water molecule is getting removed from here. So sugar plus base at 1' position plus phosphate at 5' position. This combination is called nucleotide. So nucleoside, nucleotide, very, very, very important. And these nucleotides are the monomers of DNA and RNA, nucleic acids. They are polynucleotides. You know, for carbohydrates, what are the monomers? Monosaccharides. They are linked through glycosidic linkage. For proteins, the monomers are alpha amino acids. They are connected through peptide linkages. Similarly, in DNA and RNA, in nucleic acids, the monomers are nucleotides. They are connected through something called phosphodiester linkage. Okay. So this topic is extremely important. Prepare it. Now, this is about secondary structure of DNA. You know what is the secondary structure of DNA? That is the double helical structure. Okay, this is called the secondary structure of DNA. And if there is A here, it will be connected to T in the next strand through double hydrogen bond. If there is C, it will be connected to G through triple hydrogen bond. So this double helical structure, it's called Watson-Crick model of DNA, and they were awarded Nobel Prize for elucidating this structure. Okay, so you can go through this area in the textbook. Okay, this is called secondary structure of DNA. The polynucleotide chain is the primary structure, but when it is coming like this, it is called secondary structure of DNA. And what about RNA? You know, RNA is single stranded, right? So RNA, suppose this is the primary structure of RNA. What is the secondary structure of RNA? If there is a strand, it may roll back on itself to get the helical structure because it is single stranded. Okay, so it will come like this. It will roll on itself. That is called secondary structure of RNA. Clear? Now, classify the following into monosaccharides and disaccharides. What question? You know, ribose, it is a monosaccharide. Ribose, deoxyribose, all those are monosaccharides. Okay, so this is monosaccharide, this is monosaccharide. Maltose, maltose is made up of two glucose units, glucose plus glucose through glycosidic linkage connection. That is maltose, it's a disaccharide. Galactose is a monosaccharide. Then fructose is a monosaccharide. But lactose is a disaccharide, it's glucose plus galactose. Clear? It is a repeated board question. Next one, what are the hydrolysis products of? Sucrose. There are some students who simply write glucose plus fructose. But I prefer you writing alpha D glucose plus beta D fructose if you aim perfection. Okay. Similarly, what is lactose? Alpha beta D glucose plus beta D galactose. That is lactose. So learn with the specifications. Okay. Then these exercise questions are very important. Please take it from the text. What happens when D-glucose is treated with the following reagents? D-glucose with HI forming normal hexane, with bromine water forming gluconic acid. It is a mild oxidizing agent. Even with Tollens reagent, it is gluconic acid. With HNO3, you will be getting saccharic acid because it is a strong oxidizing agent. This is asked in 2023 also. Then enumerate the reactions of D-glucose which cannot be explained by its open structure. There are 3 points given which cannot, 3 properties of glucose, 3 reactions of glucose or properties of glucose which cannot be explained by the open structure of glucose. You have to take it from the textbook and learn. Very important. Then What are essential and non-essential amino acids? I have told you what are they and take examples from the textbook. Define the following as related to proteins. That is peptide linkage, we discussed the definition. Primary structure, denaturation, we have already discussed. What are the common types of secondary structure of proteins? Alpha helix and beta pleated. Then what type of bonding helps in stabilizing alpha helix structure? We have discussed secondary and tertiary structure of protein. That is in alpha helix especially, you can note it down, it is intramolecular hydrogen bonding. Note it down please. Alpha helix, it is intramolecular hydrogen bonding. If it is beta pleated, it is intermolecular hydrogen bonding. Alpha helix, intramolecular hydrogen bonding, beta pleated, inter. Then differentiate between globular and fibrous proteins. We are coming to that. Then how do you explain the amphoteric behavior of amino acids? Amino acids have basic amino group. I will just write it here. C, it has basic amino group and acidic COOH group. This is alpha amino acid. One is H and one is R. This is the structure of amino acid. Alpha amino acid, because carbon connected to the functional group is alpha, amino group is on that carbon, so it is alpha amino acid. Now, because this has a lone pair of electron, this H plus can get shifted to that, making it NS3 plus, okay, and this one O minus. You know that. So, it will be forming a structure like this. This will become NS3 plus and this will become COO minus. Okay, so you can see after shifting H plus from here to the NS2, it will become NS3 plus and COO minus. So what will happen here? It has negative charge here and positive charge here. So it becomes a dipolar ion, which is called Switter ion. So why it is amphoteric? This can accept H plus showing basic character. This can donate H plus showing acidic character. Or you can say amino group is basic in nature, acidic COH group is acidic, showing amphoteric behavior. Okay, that's the reason. Then what is the effect of denaturation on the structure of protein? We have discussed globules unfold, helices uncoil, but quaternary to tertiary to secondary, but when it comes to primary, it will remain intact. So you have to talk about that. How are vitamins classified? You know, fat soluble and water soluble, which we discussed. Name the vitamin responsible for coagulation of blood. That is vitamin K. Okay. This was asked in 2023. Why are vitamin A and vitamin C essential to us? Give their importance. Why are they essential means you have to, from the chart which I said, you have to know what are their deficiency diseases. So if you don't take them, our body will be deficient in those and it will lead to deficiency diseases. That's what you have to write. Then what are nucleic acids? Definition. Mention their two important functions. If it is DNA, it is a genetic material. If it is RNA, it takes part in protein synthesis. Then the two strands of DNA are not identical but are complementary. Explain. The two strands are not identical but complementary because there is specific base pairing happening between A and T and G and C. That is why we say they are complementary. The two strands are complementary. Then what are the important structural and functional differences between DNA and RNA? It is coming up. I think so. Yes, differences are coming up. You know, if you come to DNA, it is double-stranded, whereas if it is RNA, it is single-stranded, right? Then in DNA, you know, the pyrimidine base is present as thymine, whereas in RNA, it is uracil. Then functionally, DNA contains genetic information, whereas it is a genetic material, whereas the other one takes part in protein synthesis. Okay. Then what are the different types of RNA found in the cell? Messenger RNA, transfer RNA, and ribosomal RNA. That is mRNA, tRNA, and rRNA. Then remember this, monomers and linkages of these polymers. In carbohydrates, the monomers are monosaccharides and they are linked through glycosidic linkage. Proteins, monomers are alpha amino acids linked through peptide linkage. In nucleic acids, the monomers are nucleotides linked through phosphodiester linkage. Okay, learn them by heart. Then differentiate between amylose and amylopectin. You know, amylose and amylopectin, they are two components of starch. And what are the differences? Amylose is water soluble component in starch, whereas amylopectin is water insoluble component. Then amylose is 15 to 20% of starch, remaining 80 to 85% of starch is amylopectin. That is why basically starch is insoluble in water, because the major component present in it is amylopectin, which is insoluble in water. Then amylose is unbranched chain of alpha D glucose, whereas amylopectin is branched. So you can go through this. Okay, it's very important. Then differentiate between polypeptide and protein. Polypeptide means when the number of one amino acid plus next amino acid plus amino acid, you are getting a dipeptide. Okay. Then with the third amino acid, you will be getting a tripeptide. Then tetrapeptide, pentapeptide, like that you are getting polypeptide. So when the number of amino acids is more than 10, that is more than 10 amino acids are combining one after the other through peptide linkage, then the product is known as a polypeptide. But a polypeptide with more than 100 amino acids, okay, more than 100 amino acids and having molar mass greater than 10,000 U, that will be called a protein. So clearly mark difference between polypeptide and protein, but there are exceptions. Insulin has only 51 amino acids, but it is considered to be a protein because of its complex structure. Okay. Then differentiate between fibrous protein and globular protein. Another very important question. What is fibrous protein? Fibrous means fiber-like. Our nail, hair, etc. contain fibrous proteins. Okay. So when the polypeptide chains run parallel and are held together by hydrogen and disulfide bonds, then fiber-like structures are produced and they are called fibrous proteins. They are generally insoluble in water. Remember, if your hair is soluble in water, fibrous protein, then when you take bath, there won't be hair on your head, right? At least remember like that. Okay. So fibrous protein, insoluble in water. Then examples are given: keratin present in hair, wool, silk, etc. and myosin present in muscles. What about globular proteins? This structure results when chains of many polypeptide chains coil together and make a fibrous structure. Okay. Globular structure. This structure results when the chains of polypeptides coil around to give a spherical shape. These are generally soluble in water. Okay. Insulin and albumins are common examples of globular proteins. You know, diabetic patients, they take insulin solution, right? Isn't it? So it is soluble in water. Clear? Then DNA and RNA, I have just given a tabular form, the same things what I told you. You can just go through it quickly. That's all about biomolecules. Hope it's done. Okay. And one abstract is not included here. That is, what are the three properties of glucose which cannot be explained by open structure of glucose. Please take it from the textbook. It is also very important. Okay. Now after 5 minutes break, we'll be starting aldehydes, ketones and carboxylic acids. Okay. I am back. Okay, I'll do one thing. I will just tell you what are the important areas of D and F because we are already in that area. So D and F and coordination compounds which are important areas in that. Okay. So D and F I have mentioned refer one shot because I have done a detailed session or one short session on D and F covering everything what is required from D and F. But I'll just tell you what are the important areas. Just properties of transition elements and related give reason questions. Like, transition metals act as alloys. Okay, they can act as alloys, they form complexes, they act as catalyst, they show variable oxidation state, all those things you will have to learn. So if you watch that video, you will get answer for all these things. Then all solved examples are index questions and board questions. I have mentioned there, so you can just watch it. I don't think you have to spend time on that, already done area again. So you can easily get them. Preparation and properties of K2Cr2O7 and KMnO4. Important. Then lanthanoid contraction, definition, cause and consequence. Lanthanoid contraction means it is a steady decrease in size of lanthanoid elements and their ions with increase in atomic number. That's the definition. Steady decrease in the atomic and ionic size of lanthanoids with increase in atomic number. That is called lanthanoid contraction. And what is the cause? Cause of lanthanoid contraction is filling of 4f orbitals before 5d and poor shielding of 4f electrons. That is the cause. And what are the consequences? There are many consequences. Important ones, number one, densities of post-lanthanoid elements are very high. That is, densities of elements which come after lanthanoids, they are very high. Second, basic strength decreases from LaOH thrice to LuOH thrice, lanthanum hydroxide to lutetium hydroxide. Then third one and very important one, similarity in size of 4D and 5D elements. For example, zirconium and hafnium, they differ by only 1 picometer in size. So what is the after effect of this? When they have a similarity in size, they will exist together in nature and they will have similarity in size means similarity in properties and difficult to separate. Okay. So this is a very important area. Lanthanoid contraction, highly expected question for 3 marks. 1 for definition, 1 for cause, 1 for consequences. Then uses of lanthanoids. There is a paragraph in your textbook where uses of lanthanoids are mentioned, but special reference should be given to mish metal. What is mish metal? That is lanthanoid element plus, normally students learn it like this. A lanthanoid element which is approximately 95%. Then iron is there and then Skal, that is sulfur, carbon, calcium, aluminium. So you can just take it from there. Mish metal, its composition and uses, very, very important. Then actinoid contraction, it is similar to lanthanoid contraction, steady decrease in the atomic and ionic size of actinoids with increase in atomic number. But cause will be, here it is filling of 4f before 5d, here it will be 5f before 6d. Then consequences not required. And actinoid contraction is only very less from element to element compared to lanthanoid contraction because 5f elements are poor shielders compared to 4f. Okay. And there is a question, actinoids show more number of oxidation states. Lanthanoids show +2, +3, +4. Actinoids show +3, +4, +5, +6, +7. Why there are more oxidation states shown by actinoids? Reason, very small difference in energy between 5f, 6d and 7s orbitals. So they all those electrons can take part in bonding. Then actinoids are bigger in size and they have lower IE compared to lanthanoids. I have explained all these things in that one shot. Please do watch. Then coming to coordination compounds. Coordination compounds also I have uploaded a one-shot video, and you can get everything related to coordination compounds. So you can refer one shot. I'll tell you what are the important areas. Werner's theory regarding primary valency, secondary valency, etc. Then differentiate between double salt and complexes. Then important terms definition like coordination entity, coordination complex, then ligand, ambidentate ligand, unidentate ligand, then what is meant by homoleptic complex, heteroleptic complex, all those things, all the definitions you can get from the one shot. Then IUPAC nomenclature I have done in great detail and writing structures from names, isomerism, then salt examples, index questions, all those, then BBT, crystal field theory, then bonding in coordination, bonding in metal carbonyls, all those you have to practice. But I am not spending time on that because we have 2 chapters of organic left. We are going to conclude that area. So these ones, that is CFT, spectrochemical series definition, very important, and you have to learn the series also. Then CFSC definition. Then how to write configuration for D4, D5, etc. like delta O greater than P, delta O less than P, that one. It is there. D orbital splitting figures like octahedral field T2 GEG splitting, then tetrahedral, then it is T2 and E. Then bonding in metal carbonyls, very important, that figure and explanation. Then index questions and exercise questions, what all are important, I have mentioned in the one shot. Please go through it. Okay. And that's all. Now we are going to code the organic chemistry continuation, aldehydes, ketones and carboxylic acids. Okay, so let's start with aldehydes, ketones and carboxylic acids. These are the most important namings from aldehydes, ketones and carboxylic acids. First one, CS3, CS2, CO, CS2, CHO. This is aldehyde group, this is ketonic group. Aldehyde group is more important than ketonic group. So 1, 2, 3, 4, 5. And when ketonic group is not the principal functional group, it is called oxo. Okay. So it is called 1, 2, 3, 4, 5. So 3 oxo, total 5 carbon aldehyde, pentanal. Then this one, its condensed formula is this one. This is the expanded formula and expanded structure. It is also commonly asked. Sometimes it will be asked like this in the paper. That's why I have included that also. So it is 1, 2, 3, 4, 5. So 2, 4 dimethyl, total 5 carbons and third position ketonic group. So 2, 4 dimethyl, pentan trione. Then en and al. So it is enal. We can see. So it is 1, 2, 3, 4, 5. So it is pent 2n 1al. Okay, pent 2enal. Then this one, when you expand, CS3 twice, CH, COOH. So how it is? CS3 twice. Then C double bond, CS3 twice, C double bond, CH, COOH. How to name it? 1, this is a principal functional group here, 3, 4. So what's the name? 3-methyl but 2N1-oic acid or but 2-enoic acid. 3-methyl but 2-enoic acid. Very important. And this one, Basically, it is benzaldehyde, 1, 2, 3, 4, fourth position nitro group. So, 4 nitro, benzaldehyde, or latest name for nitrobenzene, carbaldehyde. Okay. Then, this is, I told you I have selected only the questions which are expected in any board paper. So, questions are selected in that way. Now, this is, they might ask you to label the electrophilic center in an aldehyde group or carbonyl group. You can see it is C double bond O. Aldehyde or ketone will contain C double bond O. O is more electronegative. So, O will become negative and C will become positive. So, if you are asked to label the nucleophilic and electrophilic center, the electrophilic center means positive center. So, that is C plus and nucleophilic center is O minus. Clear? And this is the related area. Okay, so this is C plus and O minus. You can go through this area in your textbook. It's taken from the text. Then, index question. Write the structures of products of the following reaction. All of them are board questions. Let's see how to do it. You know, this is benzene with C2H5COCl. So, this is acylation of benzene. So, any one corner H will go with Cl. So, this will get connected here. So, you will be getting what? Benzene with here, here or here. Okay, I don't have spaces, so I am writing it here. CO, C2H5. So, this is the product form when you do this. This is Friedrich-Crafts acylation. Now, what about this one? This is dialkyl cadmium. Okay, dibenzyl cadmium with 2 CS3COCl. So, CdCl2 will get removed, 2 Cls, and the CS3CO group will get connected to this. So, what will you be getting? C6H5 CS2, then twice, then COCS3, that is CdCl2 is removed. So, COCS3. So, sorry, just a second. CS3CO, CS3CO, CS2, 6H5, 2 of them. Okay, so CS3, just a second. CS3, after removing CdCl2, CS3CO, then CS2, C6H5. CS2, C6H5. How many of them? 2 of them. Okay. So, CS3, CO, CS2, C6H5. This is twice, this also twice. So, 2 molecules of this ketone you will be getting. Okay. That is preparation of ketone using dialkyl cadmium. Then this one, yes, very important. This one you have done in class 11 also. You have propine. It is written Hd2 plus and sulfuric acid on the arrow. That is nothing but addition of water. It is acid catalyzed hydration of the alkyne. Now you have to follow what? Markovnikov rule. So H plus will go to the carbon holding greater number of hydrogen atoms. OH minus will go to the carbon holding lesser number of hydrogen atoms by breaking one out of the 3 bonds. So you will be getting what? CS3, then C, then OH, double bond CS2. That means you are getting an enol. So it will undergo tautomerization now or isomerization. This H will get shifted to CS2. This double bond will come here. So the product formed will be CS3, C double bond O, CH3. That means you will be getting propanone. Very, very important in the board paper. Now this one, this is paranitrotoluene, CrO2Cl2 and followed by hydrolysis. When you see this condition on the arrow with toluene or its derivative, you can see that it is a name reaction, etard reaction, and there the CS3 will change into CHO. So this will be the product formed. Clear? So practice these questions very well. Now arrange the following compounds in increasing order of their boiling points. I think I have already given you an order, increasing order of boiling point. Hydrocarbon less than ether, less than aldehyde, less than ketone, less than alcohol, less than carboxylic acid. So just apply it here. This is aldehyde, this is alcohol, this is ether, this is hydrocarbon. So hydrocarbon less than ether, less than, then aldehyde, less than alcohol. So hydrocarbon, then ether, then aldehyde, and then alcohol. Okay, I have asked you to note that arrangement down. I hope you have done it. So if you know that arrangement, you can do any question like this. Then this mechanism is very important. It is not as important as previous three mechanisms what I told you, ethanol to ethene, ethene to ethanol, ethanol to ether. But this is also asked sometimes in the board paper. This is nucleophilic addition onto carbonyl carbon. You know carbonyl carbon is sp2 hybridized, so it is trigonal planar. When nucleophile is attacking it, it will change into tetrahedral alkoxide intermediate, which picks up H plus from the medium and forms this final product. And its explanation is given here. It was sp2, now it's changing into sp3. Okay, just go through this area in the textbook. This is almost like a sure question in the paper. Aldehydes are more reactive than ketones in nucleophilic addition reaction. I am just going to explain it. Mark it as a highly expected sure question in the paper. Okay. Aldehydes are more reactive. What is aldehyde? Aldehyde is RCHO. This is aldehyde, right? Then what is ketone? R 2 times CO. We are going to see how aldehydes are more reactive than ketones towards nucleophilic addition. So nucleophile is going to get added. Look, O is more electronegative, so it will become negative and this carbon will become positive. If nucleophile is attacking this, where will the nucleophile attack? The electrophilic carbon. So the bulkiness of groups surrounding electrophilic carbon matters, and the positive charge on electrophilic carbon also matters. If it is highly positive, nucleophile can attack it easily. Opposite charges will attract easily. And if it is less bulky, then also the entry of nucleophile will be easy. So in this case, only one bulky group. So the hindrance is less versus two bulky groups here. So steric hindrance is more, steric reason, electronic reason. Steric hindrance is more here versus only less in aldehyde. Now, when you look at the positive charge on carbon, R group is having electron releasing plus psi effect, inductive effect. So when it is releasing electron, that is plus psi effect, it will reduce the positive charge on carbon slightly. But when you come to this, here also this carbon is positive. So there are two R groups which will be releasing electrons. So it will reduce the positive charge on this carbon dramatically. So this carbon is very less positive. So attraction towards Nu minus will be less because it is less positive, and lot of bulkiness, lot of hindrance, steric hindrance. So this makes aldehyde more reactive than ketone or ketone less reactive than aldehyde. Sometimes the question will be general like this. Sometimes they will make it specific like ethanol and propanol. Then you will just change this into CS3 if it is ethanol, and propanol means both of them will be CS3. CS3 twice CO. That's all. But matter will remain the same. Learn it by heart. Very, very important. That is, Aldehydes are generally more reactive than ketones in nucleophilic addition reactions due to steric and electronic reasons. Steric and electronic reasons. Sterically, the presence of two relatively large substituents in ketones hinders the approach of nucleophile to carbonyl carbon than in aldehydes having only one such group. And electronically, aldehydes are more reactive than ketones because two alkyl groups reduce the electrophilicity of carbonyl carbon more effectively than in the former. Okay. So it is very, very important. Then this is a solved example. Please make sure to go through it. Would you expect benzaldehyde to be more reactive or less reactive in nucleophilic addition reactions than propanol? So you can see benzaldehyde is less electrophilic than carbon, that is carbonyl group, and you can see it is less reactive than propanol. Just go through this. It is also a board question. Then this mechanism also you have to learn. It is similar to what you have done generally. That is, this is your carbonyl group attacked by CN. So you are getting tetrahedral alkoxide intermediate and which is picking up H plus from the medium, making cyanohydrin. This is specific, that's all. Practice this area also. This is another area from this chapter commonly seen. It is a trendy question nowadays in recent board papers. That is aldehyde with alcohol in the presence of HCl gas. First you will get hemiacetal. That with more alcohol in excess you will get acetal. If it is a ketone, you will get ketone with ethylene glycol, you are getting ketal. This is very important. Okay? Prepare it. Then this is another sure question in the paper. That is the hydrogen present, that is aldehydes and ketones, they undergo number of reactions due to the acidic nature of alpha hydrogen. So you will be getting the question, why alpha hydrogen is acidic? And take my word, this is a highly expected question. That is, alpha hydrogen atom present in carbonyl compounds are acidic alpha hydrogen atoms. Reason. The acidity of alpha hydrogen atom of carbonyl compound is due to the strong electron withdrawing effect of the carbonyl group. Because, this carbonyl group, O is more electronegative, right? You can see O is more electronegative. Making it negative, this carbon is positive. So automatically when this carbon becomes positive, it has a tendency to withdraw electron from here. So hydrogen is lost. So, this carbon is becoming negative now. So that negative and positive will make a bond. So it is getting resonance stabilized. That is, acidity of alpha hydrogen atom is due to strong electron withdrawing tendency of the carbonyl group and resonance stabilization of this is the conjugate base, it is getting resonance stabilized. Conjugate base in the sense, when hydrogen goes out from the species as H plus, remaining entity, when hydrogen goes out, that carbon becomes negative. So that is the conjugate base of this. It is getting resonance stabilized. Okay. Practice it well. Then this is solved example in your text. So I'll just give you the hints. Compound A with molecular formula C8H8O forms an orange red precipitate with 2,4-DNP reagent. Orange red precipitate with 2,4-DNP reagent indicates that it is an aldehyde or a ketone, means it is a carbonyl compound. Gives yellow precipitate on heating with iodine in the presence of NaOH, means it is giving positive iodoform test, indicating that the presence of CS3CO group, that is methyl ketonic group, is confirmed. Okay. Then it neither reduces Tollens reagent or Fielding's reagent. That means it is not an aldehyde, means it is a ketone, because already you proved that it is an aldehyde or a ketone through DNP. So it is not an aldehyde. Nor it decolorizes bromine water or Bayer's reagent. You can see the formula C8H8O suggests high degree of unsaturation. If it is highly unsaturated and open, you should decolorize Bayer's reagent and bromine water. But it is not happening, means it is cyclic, means a benzene ring is indicated. So benzene ring is there. Then on drastic oxidation with chromic acid, it gives a carboxylic acid having molecular formula C7H6O2. C7H6O2 is nothing but benzoic acid. So see how we are arriving at the product. It's detailed reactions you can take from the text. I'll just tell you how to arrive at the structure. So this group is confirmed. Benzene ring is confirmed. And you can see that only one COH group is side chain is there on oxidation. That means only one side chain is there on this benzene ring. That means we will try to fix this COCS3 and try whether it is satisfying all the conditions. Let us see. It is a ketone. So okay, I'll get back to you, Utkarsh, okay, after this. So you can see benzene with COCS3. We are trying whether it's satisfying all the conditions. So you can see it is a ketone. Benzene ring is also confirmed. And you know, because there is a methyl ketonic group, it will answer iodoform test. And you know, this side chain is getting oxidized to COH. So it is satisfying all those areas. But let's see whether it's satisfying the molecular formula. It is C8H8O. 1, 2, 3, 4, 5, 6, 7, 8. C8. Always you have to check like this, okay? Then hydrogen. 1, we are not showing it because it is bond line, but we know it is hydrogen, okay, at each corner. 1, 2, 3, 4, 5, plus 3, 8. And O. So that means it is satisfied. So this is, that is acetophenone is the structure of A. You go through this solved example in your textbook for reactions. Then this is another very, very important area. Solved example, index question 8.4 and 8.5 in your textbook. Make sure to master it. It is highly expected. Arrange the following compounds in increasing order of the reactivity in nucleophilic addition reactions. You know, ethanol is an aldehyde, propanol is aldehyde. These two are ketones. Few minutes back I told you aldehyde is more reactive than ketone. And if it is more bulky, reactivity will become lesser, whether it is aldehyde or ketone. So, ethanol and propanol will be more reactive than propanone and butanone. Now, increasing order means least. So, these two, propanone and butanone are ketones. So, they will be less reactive. Out of that, but has 4 carbons. So, it is more bulky. So, butanone less than propanone. Okay. Then, out of this ethanol and propanol, prop has 3 carbon, this has 2 carbons. So, this is more bulky when you write the structure. So, butanone less than propanone, less than propanol, less than ethanol. So, ethanol will be the most. Clear? Then, benzaldehyde, para-tolualdehyde, para-nitrobenzaldehyde, acetophenone. Here you can see the only ketone is acetophenone. So, that is the least. Okay. Now, out of these para-tolualdehyde and para-nitrobenzaldehyde, I'll show you the structure. What is para-tolualdehyde? Okay, this is CHO and this is CS3. What is the speciality? This is an electron releasing group, right? So, it will decrease the positive charge on carbon, right? That impact will go here also, right or not? So, it will decrease the positive charge. So, when the positive charge is decreased, it will decrease the electrophilicity, positive charge. So, decrease the reactivity towards nucleophile. But if it is para-nitrobenzaldehyde, what will happen? Para-nitrobenzaldehyde means it is CHO here and nitro here. What is the speciality of nitro group? Nitro group is electron withdrawing. So it will withdraw electrons. So carbon's positive charge will increase. When it is becoming more, when the charge is becoming more, what will happen? It will become more positive. So it will have more attraction towards the incoming nucleophile. So this is the least. Then para-tolualdehyde will be less than benzaldehyde, and this will be the most. That is para-nitrobenzaldehyde. Clear? These are index questions. Now, when you come to predict the products of the following reactions, this is a ketone, this is hydroxylamine. What will you do? You just remove O with this one. So, you will be getting, that is remove, it is double bond NOH. Double bond NOH. So, that will be the oxime, double bond NOH. That is the oxime. I will just erase this area to make space. So, you know, this is cyclopentanone. So, you will be getting, I will make it clear here, cyclopentanone oxime. Okay, double bond NOH after removing water. Then here this is cyclohexanone. This is 2,4-DNP, 2,4-dinitrophenylhydrazine. Remove this O with this NH2N. So it will be cyclohexane double bond NH, then this structure. So cyclohexane 2,4-dinitrophenylhydrazine connected. Then this is an aldehyde. This is here you have to be very careful. This is aldehyde. This is semi-carboside. You can see there are two NH2 groups in semi-carboside, but only one will take part in this addition. The NH2 which is close to C double bond O, you should not touch it at all. It will not undergo removal of water. Instead, this double O will go with the H2 of the NH2 which is far away from the C double bond O. So what will you be getting here? R, then CH, then double bond CH, RCH, double bond CH, then CH, then this is actually C double bond O. So you can write double bond N, then start right from there, NH, that is from here you write backward, NH, CO, NH2. This is how you have to write it. I hope that's clear. Okay. Then next one, this is acetophenone. This is also a ketone. Remove this O with this is ethylamine. So remove this. Then it will be C double bond N CS2 CS3. That will be the product. So practice this very well. Okay. This is also very important area from the textbook. I am going little fast so that we can cover the remaining topics immediately. Aldehydes are more easily, this is another trendy question nowadays. Aldehydes are more easily oxidized than ketones. Give reason. You know, in aldehydes, there is a hydrogen atom connected to C double bond O, which can go out as H plus. In ketones, and they have CH bond. In ketones, it is CC bond. So we are talking about that. The cleavage of the CH bond, you know, if you come to aldehyde, R, C, double bond O, H. So we are talking about this CH bond. Okay. But if it is a ketone, it is R, C, double bond O, R. So there will be C to C bond or C to C bond. There is no CH bond. We are talking about that. So the presence of hydrogen attached to, presence of hydrogen attached to carbonyl carbon makes the oxidation easy. Ketones do not have hydrogen atom attached to the carbonyl carbon. So the cleavage of CH bond in aldehyde is easier compared to the cleavage of CC bond in ketone. Learn it as such, very, very important, possible in your paper also. A trendy question nowadays. Trendy question in the sense, it is present in recent bond papers. I have seen it. So that's why I told you, just prepare it very well. One is this one, then acidic nature of alpha hydrogen atom. Both of them are trendy questions. Then this is there in 2023 board paper. That is, the carboxylic carbon is less electrophilic than carbonyl carbon. Carboxyl group is, or carbon is carboxyl carbon. Carbon present in the carboxyl group is less electrophilic, means less positive than the carbon present in carbonyl carbon. Let's see how. You know, this is carboxyl carbon. So when it is getting shifted like this, this is becoming positive. So here, because this OH group is there, OH group is also there in this COOH, the lone pair on O can help in, minimizing the plus charge on carbon. That is why it becomes less electrophilic. Clear? But if it is carbonyl group, this OH group is not there. So there is nobody to cancel the plus charge like this on carbon. So you can see the carboxylic carbon is less electrophilic than carbonyl carbon because of the possible resonance. This is the resonance what we specify. Clear? Okay, now this is also a trendy question nowadays. I have selected only such areas. Side chain oxidation of toluene. Toluene to benzoic acid. Fixed question in conversion area. Toluene, side chain oxidation with KMnO for KOH and heat, you will get potassium benzoate. On hydrolysis, you will get benzoic acid. Then, if it is methyl, ethyl, propyl, whatever, the side chain, if it is primary, it can be easily oxidized to benzoic acid. Irrespective of the length of the side chain, it will change into COOH only. You please refer this area in the textbook. Then, next one. Carboxylic acids do not show the reactions of carbonyl and hydroxyl group. Same thing. In carboxyl group, why it is called carboxyl? Carboxyl, carbonyl and hydroxyl together in carboxyl. So you can see there is carbonyl group and hydroxyl group. That's why it's called carboxyl. Question is, even though both these carbonyl and hydroxyl groups are there in carboxylic acid, they don't show properties of carbonyl compounds or alcohols. They don't show properties connected to carbonyl group or hydroxyl group. Why? Because they are close or they are nearby, close proximity or nearness of these two groups, they will undergo resonance like this. Because they are undergoing resonance, there is no true or pure carbonyl group or pure hydroxyl group in carboxylic acid. That's why they don't show the properties of these individual groups. Clear? Because of the resonance, then you have to show the resonance also. Okay. Now, carboxylic acids are more acidic than phenols. You know, alcohol is less acidic than phenol, but carboxylic acid is more acidic than phenol, right? So, you can see what is the reason. Conjugate base of carboxylic acid is carboxylate ion. It has two equivalent resonance structures. But conjugate base of phenol is phenoxide ion, which has 5 non-equivalent resonance structures. So, where is resonance more prominent? Carboxylic acid. That is why it is having, means its carboxylate ion is more resonance stabilized compared to phenoxide ion. That is why carboxylic acids are more acidic than phenols. So, this paragraph is taken from your text. You have to learn it by heart. Okay. That is the conjugate base of carboxylic acid. A carboxylate ion is stabilized by 2 equivalent resonance structures in which the negative charge is at the more electronegative oxygen atom. The conjugate base of phenol, which is a phenoxide ion, it has non-equivalent resonance structures in which the negative charge is at the less electronegative carbon atom. Therefore, resonance in phenoxide ion is not as important as in carboxylate ion. Further, the negative charge is delocalized over 2 electronegative oxygen atoms in carboxylate ion, whereas it is less effectively delocalized over one oxygen atom and less electronegative carbon atom in phenoxide ion. Thus, the carboxylate ion is more stabilized than phenoxide ion. So, carboxylic acids are more acidic than phenol. Just learn this by heart. Very, very important. Yeah. Another trendy area from the textbook. You learn this by heart. That is, these are all electron withdrawing groups. And the power of their electron withdrawing nature is in this. This is the most electron withdrawing, less, like that. So, if you have watched my previous videos, I have included one question there, okay, from Aldehydes and Ketones, the latest videos. There they have used these three in one question. That is, acetic acid, they have replaced one hydrogen by these and asked you to arrange them in the increasing order. So, this is the increasing order of the acidic strength. Similarly, in this area also, you have to know this one, this is the board question, okay, this one, then this one. Actually, these three were taken in 2023 paper for arrangement. Then you should know this, you should know benzoic acid, you should know acetic acid, propanoic acid. These circle ones, make sure to know their order, how they are arranged. Clear? Decreasing order of acidic strength. Clear? Okay. Next one, aromatic carboxylic acids do not undergo Friedel-Crafts reaction. Why? Friedel-Crafts alkylation and acylation, they are not shown by, they use anhydrous aluminum chloride, which is a Lewis acid. So, the aromatic carboxylic acids, they don't undergo Friedel-Crafts reaction. Why? Because the carboxyl group is deactivating. It means it is electron withdrawing, and the catalyst anhydrous aluminum chloride gets bonded to the carboxyl group. I'll show you how it is electron withdrawing. Look here. You know, this is C double bond O OH. Look here. This is carboxylic acid, aromatic carboxylic acid. Now, it is like this, minus and plus. Because O is more electronegative than carbon, it's shifting the pi bond like that. So, carbon becomes positive. When the attached atom becomes positive, it has a tendency to pull electron from here. So, that is the meaning of COOH group is electron withdrawing, that is deactivating. Then the anhydrous AlCl3 catalyst used in Friedel-Crafts reaction will get bonded to the carboxyl group. Okay, that is the reason why it is not undergoing Friedel-Crafts reaction. Clear? Then this question, which acid of each pair shown would you expect to be stronger? Here this is CS3COOH, that is just abbreviated, don't think it is carbon dioxide, okay. It is CS3COOH or CS2FCOH. You know there is an electron withdrawing group here. You can see there is an electron withdrawing group here. So when there is an electron withdrawing group, it will increase, it will pull the electron density more towards it, making the polarity more in OH bond, and OH bond will get weaker. So this will be stronger. Here one is fluorine, one is chlorine. Which is more electronegative? Fluorine is more electronegative than chlorine. So it will have more pulling power. So more weakening of OH bond. So this will be stronger. In this case, it is fluorine. Here also it is fluorine. Then what will happen? You see the nearness of fluorine to the COOH group. Here it is far away from COOH. Here it is closer to COOH. So this will have more pulling power closer to the target. So this will have higher acidic strength because it will have more impact on the COOH group, electron pulling. Then here we have seen this is the most powerful electron withdrawing group, and here this is electron releasing group actually. So this will withdraw electron, weakening the OH bond. So this will be more acidic. Clear? Important. Now important name reactions. Just to indicate, just practice. One is Rosenman reduction, where acyl chloride is reduce, Rosenman reduction. It is reduced to benzaldehyde. Very important for conversion also. Then Stephen reaction, that is conversion of cyanide into aldehyde. Practice. Then PYQ questions. This is a commonly asked question in recent papers. Look here. This is, there is a double bond here and a cyanide. We are using DiBalech, diisobutyl aluminum hydride. When we use DiBalech, the double bond is maintained there. The CN just changes into CHO. The same question was given for complete the reaction in recent board paper. That is, they have given this on the arrow, you have to fill the RHS. So, double bond should be retained, just change the CN into CHO. Similarly, here, ester part onwards, the entire thing is changing into CHO. Practice these two questions, they were recent board questions. Then, next one, etard reaction. What is etard reaction? Toluene to benzaldehyde through the intermediate chromium complex. Its explanation, you please take all these name reactions, you have to learn the explanations also. The next one, Gattermann-Koch reaction, that is toluene to, no, sorry, there is a mistake here, it's wrongly uploaded. So Gattermann-Koch reaction is what? This is another reaction for benzene to toluene to benzaldehyde. Gattermann-Koch, sorry about it, wrong upload. So it is benzene to benzaldehyde. Benzene with carbon monoxide in the presence of anhydrous AlCl3 and carbon monoxide and HCl. You will be getting benzaldehyde. So Gattermann-Koch reaction also you please refer. This is not Gattermann-Koch reaction. Okay. Then aldol condensation. What is aldol condensation? Aldehydes and ketones having alpha hydrogen, they will undergo addition. Okay, that is 2 molecules of aldehyde, 2 molecules of ethanol. They undergo condensation. First, you get 3-hydroxybutanol, and which undergoes elimination of water to form enal. Okay. The first step is called aldol reaction. If you continue till here, it is called aldol condensation. So, this is self-aldol, ethanol plus ethanol. This is also self-aldol, propanone plus propanone. And this is a recent board question. That is, they have given LHS, you have to fill the RHS. Okay. Practice. Then next one, Cannizzaro reaction. That is a counterpart of aldol condensation. So, what is Cannizzaro reaction? We use it as the counterpart of aldol condensation. Aldol condensation is applicable for aldehydes, aldehydes having alpha hydrogen atom, whereas Cannizzaro reaction is for aldehydes not having alpha hydrogen atom. Note it. So, in aldol condensation, aldehydes and ketones are treated with dilute alkali. Here, these are treated with concentrated alkali. You can see the 2 important aldehydes which we use under Cannizzaro reaction are methanol and benzaldehyde. Both don't have alpha hydrogen atom. So, when 2 molecules of methanol react with concentrated NaOH in the presence of concentrated NaOH and heat, one will undergo oxidation, one will undergo reduction. So, it is a disproportionation reaction, isn't it? Self-oxidation and reduction. Methanol oxidizes to methanoic acid. That methanoic acid will react with potassium hydroxide to form potassium methanoate, because methanoic acid is acidic, potassium hydroxide is basic, it will form the salt. Then 1 molecule of methanol gets reduced to methanol. Similarly, benzaldehyde, when treated with concentrated NaOH, you will be getting the reduced form, that is CHO changes into CS2OH, benzyl alcohol. Oxidized form is this changes into COOH, benzoic acid, which reacts with NaOH to form sodium benzoate. Practice properly, very, very important. Then, next one, decarboxylation. You know, sodium salt of carboxylic acid react with soda lime when heated to form corresponding hydrocarbon, not corresponding hydrocarbon. It is, just a second. Suppose this is CS3. Then it is CS3COONA and you will be getting CH4. In that way, it is corresponding hydrocarbon if you check with R group. But corresponding, when we say total number of carbons should be same. That's why I said totally there are 2 carbons here. Okay. But when you come here, only 1 carbon. Just showed you an example. That's all. So carbon dioxide is going out. That's why it's called decarboxylation. So basically, if you use the 2 carbon acid, you are getting 1 carbon alkane. Understand? So that's why we say it is not corresponding. It is 1 carbon less. The alkane produced is having 1 carbon less because that 1 carbon is going out as carbon dioxide or as carbonate because that carbon dioxide is reacting with NaOH to form carbonate. Clear? So practice this decarboxylation also very well. As well as Kolb's electrolysis, which is given under decarboxylation. Now, Hell-Volhard-Zelinsky reaction. Very, very, very important. HVZ reaction. What is that? If you have a carboxylic acid containing alpha hydrogen atom. What is meant by alpha hydrogen atom? The carbon connected to COH is called alpha carbon. And hydrogens connected to alpha carbon, they are called alpha hydrogen atoms. So, if you have an alpha hydrogen atom containing carboxylic acid, make it react with the halogen. This halogen can be chlorine or bromine only in the presence of red phosphorus followed by hydrolysis. Then that 1 alpha hydrogen will get replaced by X. That is, that alpha hydrogen will go with the remaining X to form HX byproduct. Okay. And this reaction has a lot of innovations. Means we can use it in many statement questions, conversions, etc. For example, I'll just mention some. Suppose it is reacted with the NaCN or KCN. This will change into CN, right? X can be replaced by CN. Then that CN on hydrolysis, you will get COOH. So we can create different products which are there in some statement questions. Just mention few, that's all. Okay, keep them in mind. Then, name the following compounds according to IUPAC system. Just mentioned, I think we have already done these two. That is 1, 2, 3, 4, 5. So it is pentane 1, 2, 3, 4. Pentane 2, 4 dione. You can expand it and see. Okay. This is CS3 tri-C CH3 thrice CS3 thrice C, then CS2 COOH. So number 1, 2, 3, 4. So what is it? 3,3-dimethyl butanoic acid. Okay, 3,3-dimethyl butanoic acid. That's the name. These are also taken from board papers. Then draw the structures of the following. This is exercise question. 2,4-dinitrophenylhydrazone of benzaldehyde. I'll just show you how to do it. This is present in one of the 2023 board papers. Benzaldehyde. What is benzaldehyde? Okay, I'm drawing it like this. C double bond O H. This is benzaldehyde. 2,4-dinitrophenylhydrazone you have to make. So benzaldehyde plus 2,4-dinitrophenylhydrazine will give you 2,4-dinitrophenylhydrazone. What is 2,4-dinitrophenylhydrazine? NH2, NH. Then draw the benzene ring. Then NO2, NO2, right? I'm just showing you how to deal with such questions. You need 2,4-dinitrophenylhydrazone, which is the product of reaction between benzaldehyde and 2,4-DNP, 2,4-dinitrophenylhydrazine. Remove H2O. Okay? Then when you remove that, what you get? Okay? Double CH, it was CH double bond O. So, it is double bond N. Okay, CH double bond O, it was that O went with H2. So, this is the 2,4-dinitrophenylhydrazone of benzaldehyde. Clear? This is how you have to do it. And then, next one, cyclopropanone oxime. What is cyclopropanone? Cyclopropane is this one, you know. Okay, cyclopropane. Cyclopropanone means it is like this. So this is cyclopropanone. Cyclopropanone plus. So how you get cyclopropanone oxime? Oxime is the product of a carbonyl compound's reaction with the hydroxylamine. So what is hydroxylamine? NS2OH. This is hydroxylamine. So O you remove with this. So what will you be getting? Double bond NOH. So this is cyclopropanone oxime. Got an idea? So this is how you have to do it. Then these are all exercise questions. I'll just give you a hint. Okay. How will you convert ethanol into the following? Ethanol to butane 1,3-diol. Ethanol plus ethanol. That is, you can write it like this. Ethanol, 2 molecules of ethanol. That is self-aldol condensation. This is aldol, okay, butane 1,3-diol. So 2 molecules of ethanol, you can write dilute NaOH. You will get CS3, CH, OH, CS2, CHO. But this is 3-hydroxybutanol. But what you need is butane 1,3-diol. That is where the twist is. So you can see ethanol plus ethanol, aldol condensation. Then you are getting 3-hydroxybutanol. But if it is butane 1,3-diol, what should happen? This CHO should be changed into CS2OH. Then it will become 1, 2, 3 butane 1,3-diol. So what you have to do? You just change this into, that is, this is CHO. You just reduce that into CS2OH. So we can use a reducing agent, which is sodium borohydride. Then the CHO will change into CS2OH and you will get butane 1,3-diol. Clear? So understand it properly. Then but2-enol, same thing. 2 molecules of ethanol, you will get this one, okay? But. That is 3-hydroxybutanol. You got that in the first step. This is aldol reaction. Continue to aldol condensation. That is, heat it. When you heat it further, minus H2O. Here you don't have to write heat, okay? Here you don't have to write heat because you are writing this product. If you write heat, it will go to the aldol condensation product. Then this is alpha, this is beta. So it will undergo alpha beta elimination of water. So a double bond will get created there. So it will be CS3, CH, double bond CH, CHO. So it will be but2-enol. That's how you get it. And last one, butyenoic acid. Till here you reach the same way. Ethanol, aldol reaction, you get this, condensation, you get this, then you oxidize it. That is, this CHO oxidation, you can get COOH. So you'll get butyenoic acid. Clear? Now, here again, an organic compound with the molecular formula C9H10O forms 2,4-DNB derivative, reduces Tollens reagent, undergoes Cannizzaro reaction, and on vigorous oxidation, it gives benzene 1,2-dicarboxylic acid. Identify the compound. How to do it? It's also exercise question. So I'll show you how to arrive at the compound. C9H10O is the molecular formula. Forms 2,4-DNB derivative. That means it is an aldehyde or a ketone, carbonyl compound. Reduces Tollens reagent, means it is an aldehyde. Undergoes Cannizzaro reaction. That means it is an aldehyde without alpha hydrogen atom. And on vigorous oxidation, it gives benzene 1,2-dicarboxylic acid. So the compound on vigorous oxidation, you are getting benzene 1,2-dicarboxylic acid, right? So that means on benzene there are two attachments. That is the clue. Now, so a benzene ring is definitely there due to two reasons. First of all, this is the oxidation product, and moreover, the molecular formula suggests high degree of unsaturation. Now, so one is here, branches. Now, according to the clues, we will check. You know it is an aldehyde without alpha hydrogen atom. So, benzaldehyde we have fixed. Okay. Now, what is to be substituted here? That we will see from the formula. The formula is C9H10O. So, here 1, 2, 3, 4, 5, 6 plus 1, 7. So, 2. Pending because 7 plus 2, 9. Hydrogen 10. 1, 2, 3, 4, 5 plus 1, 6. So, 4 more. Because it is 10 there, we have only 6 here. Now, O is already there. Now, C2H4 is pending. But you know, when I take out one hydrogen, I didn't count this. When I take out this hydrogen, that hydrogen will get added here. Then I have to attach this C2H5 over here. Understand? So it is 2-ethyl benzaldehyde. That is your compound A. Clear? This is how you have to arrive at the answer. Then next one, an organic compound A with molecular formula C8H16O2 was hydrolyzed with dilute sulfuric acid to give a carboxylic acid B and an alcohol C. Oxidation of C with chromic acid produced B. C on dehydration gives 1-butene or but1ene. Write equations. I will just give you the hint for this also exercise question. I'll tell you how to arrive at the compound. C8H16O2. 2 oxygens are there, means it can be carboxylic acid, ester, etc. When it is hydrolyzed with dilute sulfuric acid, it gives acid and alcohol. Acid and alcohol are the hydrolysis products, means that parent compound is an ester. This is very clear. Okay. So A is an ester and indicated by 2 oxygen atoms also. Then, so A, it is an ester. It on hydrolysis produces carboxylic acid B and alcohol C. Now, oxidation of C with chromic acid. Oxidation of C is alcohol. Oxidation of C with chromic acid, H2CrO4, chromic acid produces B, or it is producing B. So now let's use the hints. You know, A is an ester. It, when broken down, you are getting alcohol and acid. And you know, there are total 8 carbon atoms. So 1, 2, 3, 4, 5, 6, 7, 8. But where is the ester linkage to be placed? How will you know? This alcohol C on oxidation produces carboxylic acid B. Alcohol on oxidation, you will get corresponding carboxylic acid. So, it indicates that this alcohol and carboxylic acid, they have equal number of carbon atoms. That means the ester linkage will be almost at the center. So, 1, 2, 3, you will write it like this, COO. Okay. So, this is that is CS3, CS2, CS2, then here, I'll just make it fair. So, A will be total 8 carbons, right? So, it is 1, 2, 3, 4. So, double bond O. Then again 4. 1, 2, 3, 4. So, it will be CS3, then CS2, CS2, then CS2, 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 CS3. So, you can see if you break it here, you are getting butanoic acid and butanol. So, C is butanol and B is butanoic acid. And butyl butanoate, that is the ester. Okay, just practice. Then arrange the following compounds in increasing order of the property indicated. Acetaldehyde, acetone, ditertiary butyl ketone, methyl tertiary butyl ketone, reactivity towards HCN. Towards HCN means it is a nucleophilic addition. Here, this is an aldehyde, this is a ketone, this is a ketone, this is a ketone. But, aldehyde is the most reactive. So, this will be the most reactive. Now, out of these two ketones, ditertiary butyl ketone, what is that? C double bond O. This is CS3 tri-C, tertiary butyl. Here also tertiary butyl. Ditertiary butyl ketone, it is heavily hindered. So, that will be the least reactive. Okay, this will be the least reactive. Methyl tertiary butyl ketone means one is methyl group. One is methyl group. So, it is less hindered. Okay. So, compared to previous one, this is less hindered. So, this is the least reactive. Then comes this. Then comes acetone because it is both are CS3 and this is the maximum. Okay. So, ditertiary butyl ketone less than, methyl tertiary butyl ketone less than, acetone less than acetaldehyde. That's the answer. Then, here, these are all carboxylic acids. This is alkyl group, electron releasing. This also two alkyl groups are there which are electron releasing. When it is electron releasing, it will decrease the acidic strength. Electron withdrawing will increase the acidic strength. So, this one with two methyl groups will be the least. With one alkyl group will be more than that. Then when you come to these two electron withdrawing groups, this is away from the COH group. This is closer. So, this will be lesser acidic than this one. So, least, then this, then this, then this. Okay, that will be the increasing order. Answers are all given in your textbook. I am just explaining it. Then here, benzoic acid, nitro, 3,4-dinitro, 4-methoxy. Nitro groups are electron releasing, methoxy group is nitro groups are electron withdrawing, and methoxy group is electron releasing. So, 4-methoxy benzoic acid will be the least because it is electron releasing. Then comes benzoic acid, then comes 4-nitrobenzoic acid, then comes 3,4-dinitro. The more the number of electron withdrawing groups, more will be the acidic strength. Then these chemical test to distinguish between, very, very important from this chapter. Propanol and propanone. This is an aldehyde, this is a ketone. So we can use tolerance test. This will answer, means add tolerance reagent to both the compounds and warm. This will give a bright silver mirror, this one will not. Or we can use iodoform test. Because propanone is CS3CO CS3, it will give yellow PPT of iodoform when heated with NaOH and I2, whereas this one will not. Anyone, your choice. Then acetophenone and benzophenone. You know, acetophenone is benzene with COCS3, whereas benzophenone is benzene with COC6H5. So here in acetophenone there is a methyl ketone group, so it will answer iodoform test positive, this one negative. Okay, add NaOH plus I2 and heat, then this will give yellow PPT of iodoform, this one will not. Phenol and benzoic acid, neutral ferric chloride test, add neutral ferric chloride to both, this will give violet complex, this one will not. Or sodium bicarbonate test, this will give evolution of carbon dioxide gas, this one will not. Benzoic acid and ethyl benzoate. Benzoic acid will give you the sodium bicarbonate test. Add sodium bicarbonate, this will give brisk effervescence of carbon dioxide gas, whereas ethyl benzoate will not. Then pentan 2-on and pentan 3-on. Pentan 2-on means CS3CO, CS2, CS2, CS3. So methyl ketone group, you will give positive iodoform test? No. Benzaldehyde and acetophenone. Acetophenone is still there on the board. Positive iodoform test? This one, no. Ethanol and propanol, both are aldehydes, so we cannot use tolerance test or anything. But ethanol is an aldehyde which gives positive iodoform test. Understand? Let's see why ethanol undergoes positive iodoform test. Ethanol has CH3, C double bond OH. Here you can see, though it is an aldehyde, it has that methyl ketonic group structure present in its formula, right? CH3CO. Because of this presence, it can undergo positive iodoform test. So this will give positive iodoform test, whereas propanol will not. Then this is exercise question from aldehydes ketones. Make sure to practice all these questions. Okay, any one of them can come in your paper. For example, this is, here it is side chain oxidation. It is written KMNO for KOH and heat. They haven't written H3O plus. So the product will be benzene with COOK. Understand? Don't write COOH because hydrolysis is not shown. Only step 1 is shown. Then here SOCl2 means take out this and put Cl, take out this and put Cl. COCl, COCl. This one, this is benzaldehyde with semi-carbazide. Take this O with this H2 because it is away from that. Then CH double bond N, NH, CO, NS2. Here benzene with what? That is, you have to fill this area. Gives benzophenone. So this is Friedel-Crafts acylation. So here you have to write C6H5COCl, benzoyl chloride and anhydrous aluminum chloride. This is representing tolerance reagent. So what will happen when you add tolerance reagent to an aldehyde? Just change this into COO minus, that's all. Okay, that will be the answer. Then this is an aldehyde with NaCN and HCl. NaCN and HCl, when you mix them together, you will get hydrogen cyanide. So it is nothing but addition of hydrogen cyanide. So what will be the product? Here this CH will become CHOH and CN, cyanohydrin. This one will remain intact, same. So CHO will change into CHOH and CN. It will change into cyanohydrin. Then this one, it is the aldol condensation. So you'll have to show the aldol condensation between these two. Here, this is sodium borohydride. this will not suffer any change, but the CO will change into CHOH. Here CrO3, that is a mild oxidizing agent, so this OH will change into, because it is a secondary alcoholic group. See, OH connected to this carbon, connected to two other carbons, so it is a secondary alcoholic group, so it will change into ketone. Then here the double bond part is changed into CHO. So first it will change into alcohol. So hydroboration oxidation, that is BS3 twice, H2O2 bar OH minus, and the alcohol what is formed will change into CHO. So you have to do the oxidation also. You can take the answer from the text. One BS3 twice, then H2O2 OH minus, and then oxidize the alcohol what is formed. And then this is what on ozonolysis followed by zinc dust hydrolysis forms this one. You have done in 11th standard 2 molecules of this. So this is one double bond and next one ozonolysis. So 2 molecules of cyclohexanone. Now remove them together, okay, then connect them together. Remove 2 O's like this and connect them together. So what will you be getting? I'm just drawing it here. Double bond, then here also same thing. Okay, that's it. That's the answer for the last one. Practice all of them very well. I know this session is a bit lengthy, but we have to cover all these questions. And plausible explanation, that is give reason. Cyclohexanone forms cyanohydrin good yield. Cyclohexanone means what? Cyclohexanone is this one. Then what is 226 trimethyl cyclohexanone? 226 trimethyl cyclohexanone is 226. So this is cyclohexanone 2, 2 and 6. Now why this is more reactive than this? Steric and electronic reason. This carbon C plus of the C double bond O group is hindered by 3 bulky methyl groups, whereas such hindrance is not there in this one. Then all these 3 will release electrons here, reducing the positive charge on carbon dramatically. So this will be less reactive than this one, sterically and electronically. Clear? Then there are 2 NS2 groups in semicarbazide, but only one is involved in the formation of semicarbazole. I told you, one is close to the C double bond O group, it will get involved in resonance, so that will not take part in removal of water. Then during preparation of esters from a carboxylic acid and an alcohol, in the presence of catalyst, acid catalyst, water or ester should be removed. You know it is a reversible reaction. So when you remove one of the products, according to Lee-Shalt's principle, it will trigger the product formation. Means equilibrium will shift to the right side. Okay. So to enhance product formation, we are doing it. Then this question, actually you have to make the chart like what you have done in class 11, percentage of carbon, percentage of hydrogen and the rest oxygen. That means add these two and subtract it from 100, you will get percentage of oxygen. Then you make the chart, find the empirical formula, molar mass is given, then find the molecular formula. Once you get the molecular formula, you will be getting it as C5H10O. Okay. The molecular formula will be C5H10O when you do it. And then does not reduce Tollens reagent. That means it is not an aldehyde. It forms an addition product with sodium bisulfite. That means it is a carbonyl compound. Means it can be an aldehyde or a ketone. But already you are told that it does not reduce Tollens reagent, so it is not an aldehyde. Then it gives positive iodoform test. So methyl ketonic group is, it is confirmed. On vigorous oxidation, it gives ethanoic and propanoic acid. So when you apply this, you will be getting the structure. Methyl ketonic group is there then CS2, CS2, CS3. So it will be pentan 2 on. This is one structure. There is one more possible structure, CS3, CO. Then this part can be isopropyl. We are thinking about it. So we have to confirm. Okay. Both contain methyl ketonic group. But if it is this one, you will not get ethanoic and propanoic acid. So we are on oxidation. So because it is branched. So we are ruling this out. This is the answer. So check. Does not reduce Tollens reagent. It is a ketone. So it will not. Then it will form sodium bisulfite addition product because it is a ketone. Aldehyde and ketone both will do that. Then gives positive iodoform test, methyl ketonic group. And when you oxidize this, it will get broken here. We will be getting ethanoic acid and propanoic acid. So it is pentan 2O. Then write the structure of 4-oxopentanal. 4-oxo means it is ketonic group, right? So 1, 2, 3, 4, 5. Pentanal. So it is 4-oxo. Oxo means ketonic group. Then satisfy the remaining valencies. This is also a commonly seen board question, so thought of doing it. So this is 4-oxopentanal. Clear? Yes, that's all about aldehydes, ketones and carboxylic acids. Now after 5 minutes, we will be moving on to amines and concluding this session.
audible.
Okay, thank you. Forgot to unmute, sorry. So when you come to amines, this is the last session, last chapter of this marathon session. Though I named it as bullet session, it has become like more than like a marathon session. Okay, anyway, I'm happy about it if you made use of it. Okay, Arpana, I think you can hear me now. Okay. Now, this question, this naming question is very common in papers and many students get it wrong. So, I selected this. You can see NS2, CS2, CH double bond CS2. This contains two functional groups. One is amino group, one is double bond. So, which one should be given preference? Students have a confusion. So, this is carbon number 1. Amino group is more important than ene. It is given preference to ene. So, 1, 2, 3. So, it is prop. Between 2 and 3, it is 2. So, prop 2N 1 amine. You should not put this ENE because it is followed by amine. Only one amine is coming after that. If it is di, tri, etc., you can put this E. You already know the basics. So, prop 2N 1 amine. So, practice this question well. Can come in the paper. Now, you can see some important name reactions from this chapter. First one is ammonolysis of alkyl halides. Alkyl halides, when treated with ammonia at 100 degrees centigrade, first the H will get replaced by, it is, you are getting RNS2, that is Rx plus ammonia. First you will get RNS2, primary amine. That RNS2 will combine with more Rx if available in the system to form secondary amine. It will combine with more Rx to form tertiary amine. It will combine with more Rx to form quaternary ammonium salt if more Rx is available. So, there is a question, what is the disadvantage of ammonolysis of alkyl halides? What is it? Though we say we can prepare primary amine, that prepared primary amine won't be pure. You'll be getting a mixture of primary amine, secondary amine, tertiary amine and quaternary ammonium salt. Clear? So, that is the limitation of this method. So, this is a name reaction which is very important. Next one is Gabriel-Thalamide reaction. Gabriel-Thalamide synthesis. You can see this is thalamide. When it is treated with KOH, then what happens is, I'll just show you how to do this reaction easily. This is thalamide. This is H plus and N minus. So, this is the anion of the thalamide. This is K plus and OH minus. Then what happens is, this H plus and OH minus will go out as water. Okay. It will go out as water. Then that H plus is replaced by K plus. So, you are getting potassium salt of the thalamide, which is potassium thalamide. It is reacting with R plus X minus, that is Rx. R plus X minus. Then what will happen? K plus will go with X minus to form Kx. So, minus Kx. Now, you are getting that K plus replaced by R. That is, this R is plus, you can see R is plus and this is minus, right? So, it is converted into N-alkyl thalamide. So, it was thalamide, changed into potassium thalamide, changed into N-alkyl thalamide. Now, that N-alkyl thalamide is treated with aqueous NaOH. Now, what happens is, this bond is broken, one H here and ONA here. So, suppose I am using NaOH. Here also H here and ONA here. So, you are getting disodium phthalate, okay, disodium salt of phthalic acid and RNS2. You got the aliphatic primary amine. So, certain questions with respect to this. What is the advantage of this Gabriel-Thalamide synthesis? We can get pure primary amine, unlike ammonolysis. Clear? Number one. Second, what is the limitation of this Gabriel-Thalamide synthesis? That is, it can be used only for the preparation of aliphatic primary amine, not for aromatic primary amine. What's the reason? Because if this is to be AR, suppose instead of R, it is supposed to be AR. Suppose this is supposed to be AR. That is ARNS2. AR means it is Say it's containing a benzene ring. I want aniline. So benzene with NS2. In that case, then Rx, this R should be AR. Then only I'll get ARNS2. For that, this should be ARX. Okay? ARX. That is, instead of RX, it should be ARX. Do you think this potassium thalamide will undergo easy reaction with this? That is, will this K plus go with this X minus so that this can get connected here in the place of R? Will not happen because of partial double bond character of the CX bond. It is undergoing resonance. So it is aryl. So there is a partial double bond character here. Cannot be cleaved, or the aryl halide cannot undergo nucleophilic substitution. See, actually it is a nucleophilic substitution with anion of the thalamide. Only if it is undergoing nucleophilic substitution with anion of the thalamide, you can get N-aryl thalamide, which will lead to the formation of aryl amine, primary amine. That will not happen. So, it is not applicable for the preparation of aromatic primary amines. Clear? Okay. Now, next one is Hofmann-bromamide degradation reaction. Very important. There you use an amide. You can see we use an amide. It is treated with bromine and NaOH. Then what happens is the CO is knocked out. Okay, it is knocked out. CO is knocked out. So R migrates from CO to NS2. So we are getting RNS2. That means the formed primary amine is having one carbon less because it went out as CO. It is knocked out. So you are getting one carbon less. That is why it is called Hofmann, after the name of the chemist, Hofmann bromamide. You can see bromine and amide are used. Degradation, because one carbon less in the product form. So it is stepping down or degradation. So we can use this. It is a very useful reaction in conversion. That is, if you want a primary amine with one carbon less, starting from a carboxylic acid, then carboxylic acid you convert into amide by heating with ammonia and then do Hofmann bromamide degradation reaction, you can get the primary amine. Clear? With one carbon less. Very, very important. Stepping down or degradation. And then, here also there is an overlap. Carbylamine reaction, this is Hofmann bromamide degradation reaction by mistake. So, carbylamine reaction is what? Carbylamine reaction is aliphatic or aromatic primary amine when heated with chloroform and alcoholic AOH. You will be getting alkyl cyanide, isocyanide, that is carbylamine and KCl and water. So that carbylamine what is produced or isocyanide what is produced, it is having a foul smell. That is, it is a nauseating odor. You can easily identify its presence. So that is carbylamine reaction. And carbylamine reaction is used for identification of aliphatic and aromatic primary amines. Only aliphatic and aromatic primary amines will give carbylamine test positive or isocyanide test positive. So this is not carbylamine, sorry about it. It is Hofmann bromamide degradation reaction itself. And next one, acetylation. Acetylation means, suppose we have an amine. We have an amine. Okay, it can be aliphatic or aromatic. Okay, and then, Okay, acetylation. Okay, suppose we have an aliphatic or aromatic primary amine. You add CS3COCl, that is an acyl chloride, into it. Then, in the presence of a base, actually this reaction is reversible. Then you get the intermediate, which changes into an amide, that is N-ethyl ethanamide. So what is happening here actually? It was C2H5 NH2. N C2H5 NH2. I'm just writing it like this, okay? NH2. This was primary amine. Now, what we are doing, we are just removing one H, okay? And in that hydrogen's place, what we are doing, we are introducing the acetyl group. CS3CO group is called acetyl group. If it is R here, we can call it as acylation. Since it is CS3CO group, it is called acetylation. So we say it is acetylation, introducing the acetyl group into an amine. That is called acetylation of amine. And what is the product of the acetylation? It is you are getting an amide. And how to name the amide, that also I will tell you. You see which R group is connected to CO. That will be the parent amide. So it is 1, 2. So it is, suppose this was H here. It would have been CS3CONS2. It would have been ethanamide. Now, you replaced the H and put ethyl group. So what is it? N-ethyl ethanamide. Clear? So don't think this is the parent amide. No, it is not connected to CO. This is connected to CO. So this part is the parent amide. So ethanamide is the parent amide. So it is N-ethyl ethanamide. So such reactions are called acetylation reaction. Introducing acetyl group into a compound is called acetylation. Okay. Next one is diazotization. In diazotization, we take aniline, that is aromatic primary amine. Normally we take aniline in the presence of NaNO2 and HCl. When you mix NaNO2 and HCl, it will produce HNO2. Okay, it will produce HNO2. And ice cold temperature 0 to 5 degrees centigrade, then you get diazonium salt and byproducts. This reaction, converting aniline into diazonium salt or aromatic amine into diazonium salt, that is called diazotization. Important. Then San-May reaction. In San-May reaction, you take a diazonium salt, CuCl and HCl, you get aryl chloride. CuBr and HBr, you will get aryl bromide. CuCN and KCN, you will get aryl cyanide. These three reactions collectively, it is called San-May reaction. Important. This is Gattermann reaction. Here, diazonium salt, but there it was CuCl and HCl, CuBr and HBr. Here it is copper and HCl, you get aryl chloride, and then copper and HBr, you will get aryl bromide. This is called Gattermann reaction. Then coupling reaction. In coupling reaction, take diazonium salt, couple it with phenol. You know, phenol is acidic, so we maintain the medium basic. Then you get, this is actually how to name it, I'll show you. It is like this, okay? HCl is getting removed and you are coupling them, joining them. So you are getting this product. You know, this is azobenzene, okay, azobenzene. At the para position, there is a hydroxyl group. So it is called para-hydroxyazobenzene, which is, all these are called azodyes, which are colored chemicals. So it is an orange dye. Then here also, if you use aniline instead of phenol, you know, aniline is basic. So we are using medium acidic. Okay. Then couple them, you are getting para-amino azobenzene, which is yellow colored dye. Because they are colored chemicals, they can be used in identification. Okay, azodyes. That's what's called azodye test. Then certain things to be remembered, I have already told you. Disadvantage of ammonolysis, it will yield a mixture of primary amine, secondary amine, tertiary amine and quaternary ammonium salt. Then Gabriel-Thallimide synthesis, it is used only for the preparation of aliphatic primary amines, not aromatic primary amines. Then boiling point of amines, RNS2, 2 hydrogens, extensive intermolecular association through hydrogen bonding. R2NH, only one hydrogen, less hydrogen bonding. R3N, tertiary amine, no hydrogen bonding chance like the others. So maximum hydrogen bonding in primary, so highest boiling point, then secondary, then tertiary. It is important for give reason also. Then amines behave as Lewis base. What question? Because in RNS2 there is a lone pair on N, unshared electron pair on N. So it can act as H plus acceptor or electron pair donor. Okay. It is acting as a Lewis base means it is acting as electron pair donor. H plus acceptor means it is a Bronsted base. Okay. So because it is Lewis base, due to the presence of lone pair of electrons on nitrogen atom, means they can act as electron pair donors. Then basic strength, these are very important. Basic strength of aliphatic amines. You can see in gas phase, it is primary amine more than secondary amine more than tertiary amine. But if it is aqueous phase, the order is different. Secondary more than primary more than tertiary if the R group is methyl, and secondary more than, that is, I ask the students to learn it as 2, 1, 3, then 2, 3, 1. Okay, easy. If the R group is bigger than methyl group like ethyl and onwards. So you have to know this properly. Then pKb is inversely proportional to Kb. You know, for a base, stronger the base, higher the Kb. Higher the Kb, lower the pKb. So all these things. Similarly for acids, Ka directly proportional to strength of the acid, Ka inversely proportional to pKa. Same way here it is Kb and pKb. Then what is Hinsberg reagent? It is a 1 mark question. What is Hinsberg reagent? Hinsberg reagent is benzene sulfonyl chloride. That is C6H5SO2Cl. If you want to draw the structure, it's like this. 6H5 SO2Cl, S double bond O, okay, S double bond O, SO2Cl. This is Hinsberg reagent. And you know, Hinsberg reagent is used to differentiate between primary, secondary and tertiary amines. Add Hinsberg reagent to a primary amine, you will get a PPT which is soluble in alkali. But if it is, then it is primary amine. If it is secondary amine, you will get a PPT which is insoluble in alkali. Okay, because there is no hydrogen on the nitrogen there. And if it is tertiary amine, there won't be any in a precipitate form when you add Hinsberg reagent to it. I'll just take a break to change my battery pack. Okay, just a matter of 2-3 minutes. That's it. Hi, back. So this is Hinsberg reagent, and it is used for the identification of primary, secondary and tertiary amine. I'll repeat, when you add Hinsberg reagent into a primary amine, you will get a white PPT, and which will disappear when you add an alkali into it. That is, it is soluble in alkali. If it is a secondary amine, that white PPT will not be soluble in alkali. It will remain insoluble. And if it is a tertiary amine, when you add Hinsberg reagent, you will not get into precipitate only. Okay. So that is used for identification of primary, secondary and tertiary. But I prefer you writing this test only for differentiating between secondary and tertiary amine. Because if it is primary and secondary or primary and tertiary, we have a better option, that is carboylamine reaction, where the reaction is very simple. If it is Hinsberg reagent, you have to write for primary, secondary, tertiary, primary, secondary, completely you have to write the full set of reactions. So be wise, choose the other one. But if it is secondary and tertiary, no other option, you have to go for Hinsberg test. Clear? Then only aliphatic and aromatic primary amines answer carboylamine test, which I have already mentioned. Then chemical test to distinguish between, this is generally from all organic, chlorobenzene and benzyl chloride. Chlorobenzene means, this is from haloalkanes, haloarenes. I have just included it here. Chlorobenzene is this one. Then benzyl chloride is this one. Just mentioning it. It is nowhere there in the text. Okay. So chlorobenzene and benzyl chloride, how will you distinguish between them? You add aqueous NaOH or aqueous KOH to both. Then followed by silver nitrate. When you add aqueous NaOH or KOH, we think about substitution, but here partial double bond character, it will not get substituted. Chlorine will not come out as chloride. But if it is here, aqueous KOH means you will get KCl, that is benzyl alcohol, and KCl you will get. So that KCl will be present in solution which contains Cl minus. When you add silver nitrate, you will get white PPT of silver chloride. Okay, so this will produce white PPT when you add aqueous NaOH or KOH followed by silver nitrate, whereas aryl will not. So same way we can, aryl and vinyl will not answer this test, whereas alkyl, benzyl and allyl will answer it because they can give out the Cl minus through substitution. Aryl and vinyl cannot. Keep it in mind. It will even help you in your competitive examinations. Then propan 1-ol and propan 2-ol. Propan 1-ol is primary alcohol, propan 1-ol is 2-ol is secondary alcohol. So primary, secondary, primary, tertiary, secondary, tertiary. Among alcohols, we can use Lucas test. What is Lucas test? Add Lucas reagent to both. That is concentrated HCl plus zinc chloride. If it is propan 1-ol, it is primary. You will not get any turbidity or cloudiness at room temperature. You will get it only on heating. But propan 2-ol being a secondary alcohol, you will get turbidity within 5 to 10 minutes. Similarly, if it is N-butyl alcohol and tertiary butyl alcohol, this is primary, this is tertiary. When you add Lucas reagent, this will give turbidity immediately because the order of reactivity of alcohol is tertiary more than secondary more than primary here. So this will respond immediately giving cloudiness or turbidity, whereas N-butyl alcohol will give it only on heating, being primary. Then these exercise questions you can note down and you have to practice them. This is as per the old edition book, so you can see as per the new edition. Question number is 13 and 2. Then solved example. Write chemical equations for the following conversions. CS3, CS2Cl, that is ethyl chloride into propan 1 amine. Next one is benzyl chloride into, this is 2-phenyl ethanamine. Now let's see how to do it. This, especially the first one, is a repeated board question. CS3, CS2Cl, you can use NaCN alcoholic or KCN alcoholic, any one. Then the Cl will change into, this Cl will change into Cn, that is nucleophilic substitution. Once you got the cyanide, then you can do reduction. So cyanide on reduction, 2 hydrogens here, 2 hydrogens here. I have told you cyanide on reduction you will get primary amine, isocyanide on reduction you will get secondary amine. I think I have seen one question here before. That is, I think, was it Aparna who asked me about partial reduction of cyanide? That partial reduction of cyanide, I think you mean into CS double bond NH. I think you have typed CONH. There is no partial reduction like that. It is CS double bond NH. If that is it, it is SnCl2 plus HCl, which is Stephen reduction. Okay. I think that was your query. Okay, so once you get the cyanide on reduction, you will get CS2NS2. That is primary amine. Similarly, CH5CS2Cl, you can see it is stepping up, that is ascending the series. So when you replace Cl by Cn, you are introducing one more Cn. So the product formed is having one more carbon. So stepping up, we can use it in conversions. So here also the Cl is replaced by Cn. We can use NaCN alcoholic or KCN alcoholic and reduce, then Cn will change into CH2NH2. The first one is a repeated board question. Now, write structures and IUPAC names of the amide which gives propanamine by Hofmann-Bromamide degradation. What you need is propanamine. So, I'll show you how. What you need is propanamine. So, CS3, CH2, CH2, NS2. This is propanamine. So, they are asking you which amide on Hofmann-Bromamide degradation will give you this. During Hofmann-Bromamide degradation reaction, CO is knocked out. So, if you want to know the parent amide from which this amine is produced, what you can do? So simple. You can simply put, because from here only you knocked out the CO. Just insert the CO there. So, which parent compound, parent amide? CS3, CS2, CS2, CO, NS2. It was butanamide. When CO is knocked out, you will get propanamine. Clear? So, it is butanamide. Then, next one, the amine produced by Hofmann degradation of benzamide. What is benzamide? Benzamide is benzene with CONS2. That is benzamide. Okay. So, they are asking you the amine produced by Hofmann degradation of benzamide. Hofmann degradation means just remove the CO before NS2. Then NS2 will migrate to the benzene ring. So, you will be getting aniline. Okay. So, this is how you have to use Hofmann-Bromamide degradation reaction techniques. And now, such arrangements are there in solved example, index question and exercise question. Make sure to practice them properly. And I have given here the, the clue, we can say magic clue to know what is the proper arrangement order. Just like what I gave you before, that is hydrocarbon less than ether, less than aldehyde, less than ketone, less than alcohol, less than carboxylic acid for boiling point. This is for basic strength. Keep this in mind. Arylamine means NS2 directly connected to benzene ring is arylamine. Arylamine less than ammonia, less than benzylamine, less than alkylamine. But when you come to alkylamine, if it is gas phase, it is different. Then solution phase, it is different. So keep this in mind to answer it. And this arrangement is corresponding to this. See, decreasing order. It is decreasing order as. So, secondary amine more than primary amine, more than ammonia. See, arylamine less than ammonia, less than alkylamine. Among alkylamine, 3 more than 2 more than 1 if it is gas phase. Unless mentioned, you can take it as gas phase. Okay. So, practice it. Make sure to note this down. Okay. Then, here also, index question answers are given at the back side of your textbook. Use this, magic arrangement trick and see how you can arrange this. Try to do them on your own. and cross check with the answer given at the back. Just see whether you are able to do it. Okay. And in your textbook, they have given according to solution phase and gas phase, I think. Okay. I don't know about the new edition, how it is given. Anyway, you try both in gas phase and solution phase and cross check with your answer. So you can try this. Here, this is aliphatic primary amine. This is aryl amine, ammonia, benzyl amine, secondary amine. So use that technique. You can easily do that. Okay. Then how will you convert 4-nitrotoluene to 2-bromobenzoic acid? It is a conversion from the textbook. 4-nitrotoluene, treat it with bromine. Then why bromine is coming here? This is orthopara directing. So this methyl group is orthopara directing. So Br, this position is ortho with respect to this, but nitro group is meta directing. So this is meta with respect to NO2. That is why Br is fixed here. Then Sn bar HCl, then what will happen? NO2 will get reduced to NS2. Then diazotize, it will change into N2Cl. Then H3PO2, hyperphosphorus acid or phosphenic acid and water. Then N2Cl will be replaced by H, and then you can use Amino for alkaline. Then side chain oxidation, that is CS3 will change into COH. Amino for KOH heat followed by hydrolysis. Okay. Then convert 3-methyl aniline to 3-nitrotoluene, 3-methyl aniline to 3-nitrotoluene, and aniline to 1,3,5-tribromobenzene. Both are index questions. Please refer the back side of your textbook. It is also given there. These two questions you have to practice. Then such questions are very trendy nowadays in the board papers. So these are taken from your exercise, and make sure to practice all these things very well. Ethyl iodide with NaCN. So what will happen? This will change into Cn. So this will be a CS3, CS2, Then partial hydrolysis. See, partial hydrolysis. If Cn undergoes partial hydrolysis, it will change into CONS2, amide. But if it is complete hydrolysis, it will change into COOH. So what will be this be? It will be CS3, CH2. Then Cn will change into CONS2. This is partial hydrolysis. Hope it is clear. If it is not written partial, only hydrolysis, you can go for COOH. But you can see NaOH plus Br2 is there on the next arrow, which is clearly indicating that this is Hofmann-bromamide degradation reaction, and the parent compound before that should be an amide. Okay. So when it is undergoing Hofmann-bromamide degradation, just remove this CO. So the C will be CS3, CS2, NS2. I hope this is clear. Then this is diazonium salt with CuCl. Then what will happen? The Sandmeyer reaction, Cl will get replaced by, N2Cl will get replaced by Cn. So you'll be getting 6H5Cn, right? That is Sandmeyer reaction. Now it is written, so this is 6H5Cn here, A. Now it is written H2O bar H plus. It is not written partial hydrolysis. That means it is complete hydrolysis. So this Cn will change into COH. So this B will be C6H5COOH. Hope it is clear. Okay. Cn will change into COH. Now that is heated with ammonia. When an acid is heated with ammonia, if it is not heated, you will get ammonium salt. If it is heated with ammonia, then you will be getting C6, you will get the corresponding amide. You will be getting CONS2. I hope that's also clear. Then CS3, CS2Br plus KCN. Replace this by Cn. So this is A. Now lithium aluminum hydride, that is reducing agent. So this Cn will change into CS2, NS2. So this B will be CS3, CH2, then CH2, NS2. Cn changes into CS2, NS2. Clear? Now, yes, this is also very, very important. When you have an aliphatic primary amine, when it is treated with the HNO2, if it is aromatic, it will undergo diazotization, aromatic diazonium salt, which is stabilized through resonance. So it is stable up till 5 degrees centigrade. But if it is aliphatic, when you treat it with HNO2, the diazonium salt is highly unstable. It will change into alcohol. So just replace the NS2 by OH. Okay. When it is sometimes written as HONO, I normally say HNO2. We can also write it, remember it as HONO. Okay. HNO2 or HONO, the NS2 will change into OH. So you'll be getting propan 1-ol, that is C. Then this is nitrobenzene. Nitrobenzene, when reduced, that is we can use H2 bar PT, Fe bar HCl, Sn bar HCl, etc. Then NO2 will change into NS2. So A will be aniline. Aniline with diazotization, you will be getting benzene diazonium salt. So B is cis-H5N2Cl. Then undergoing hydrolysis. So you will be getting phenol, diazonium salt undergoing hydrolysis. This heat is actually only 10 degrees centigrade because this is 0 degrees centigrade, you can see it. So that is relatively higher temperature. So you will be getting phenol. Then acid plus ammonia and heat, you will be getting amide. So what is this A? That A will be CS3CONS2. So that is amide. Then you can see NaOBr. What is this NaOBr representing? Br2 plus NaOH. It is same as NaOBr. If you see that, it is Hofmann bromamide degradation reaction. Similarly, NaOI is I2 plus NaOH, that is iodoform reaction. So this is now Hofmann bromamide degradation reaction. Remove this, you will be getting CS3NS2, that is B. And that with NaNO2 and HCl, remove this NS2 and put OH. So CS3OH. Clear? And last one, nitrobenzene plus Fe and HCl, you will be getting aniline. So nitrobenzene, Fe and HCl, you will be getting aniline. So this is aniline. Diazotization, you will get diazonium salt. But this area, you have to be very careful. Diazonium salt with phenol, that is coupling. Okay. So how will you do it? Diazonium salt with phenol. I have shown you the coupling reaction. So this C will be para-hydroxyazobenzene. If you remember. You know, this is azobenzene. So para-hydroxyazobenzene, that is C. This is coupling, representing coupling. Clear? Okay, we are about to wind up. So just few more questions. These are also from exercise. This is aniline plus chloroform and alcoholic AOH. San-May reaction complete. cis-H5N2Cl plus H3PO2 plus water. Diazonium salt with H3PO2, you will be getting benzene. Okay, major product is benzene. Complete the reaction. Then aniline plus sulfuric acid. You will be getting anilinium hydrogen sulfate. So you can take it from the text. These are all direct reactions. You have to complete the reaction. Diazonium salt with ethanol. Diazonium salt with ethanol or H3PO2, both are converting the diazonium salt into benzene. Ethanol will oxidize to ethanol. It is reducing this into benzene. Similarly, H3PO2 will get oxidized to H3PO3. So take it. Then aniline plus aqueous bromine. You will be getting 2,4,6-tribromoaniline. And how will you get it? You know, this is aniline. Okay. So like this, you cannot write it here because it is substitution on the ring. So you have to draw it itself. So it will be 2,4,6-tribromoaniline. And then this is aniline plus acetic anhydride. That is, protecting the amino group. You will be getting acetanilide. Okay. that is CH5NHCOCH3, acetanilide. And this is diazonium salt with HBF4 followed by NON2, copper and heat, you will be getting nitrobenzene. So these are direct reactions from your textbook, but they are all board questions. Make sure to practice. And now give one chemical test to distinguish between the following pairs of compounds. Methylamine and dimethylamine. Primary amine, secondary amine. Go for carbylamine reaction. How? Add chloroform and alcoholic acids to both and heat. This will produce foul-smelling isocyanide being a primary amine. This one will not. Secondary and tertiary amine, go for Hinsberg test as I told you before. Only Hinsberg test will work here. Ethylamine and aniline. You know both are primary amines, right? So we cannot use carbylamine. But this is aromatic primary amine, this is aliphatic. So go for azodite test. That is add NaNO2 plus HCl followed by phenol. Aniline will produce that red orange colored azodite, parahydroxyisobenzene, whereas ethylamine will give bubbles of nitrogen gas. It will not give any dye. Then aniline and benzylamine. This is aniline, which is aromatic primary amine. Benzylamine is not aromatic, but it is also primary amine. Again, go for azodite test. Okay. Aniline and N-methylanilane. Primary amine, secondary amine. Go for carbylamine test. Aniline will answer. N-methylanilane will not. Then these give reason questions are very important. pKb of aniline is more than that of methylamine. What does that mean? pKb is more means Kb is less, right? I told you pKb and Kb are inversely proportional. So pKb is more, Kb is less. That means basically they are asking you aniline is less basic than methylamine. In aniline, benzene connected to NS2. Benzene ring is electron withdrawing. It will take the lone pair away from nitrogen. It is like this. NS2. So I'll just make it alternate single and double bonds to show the resonance. So, you know, it is electron releasing group. So the lone pair will go into the ring for resonance. When the lone pair goes in conjugation with the ring, lone pair will not be available for donation, or it will not be available for donation to a proton. So it will become a weak proton acceptor, weak base. But when you come to methylamine, it is aliphatic amine. Methyl group is electron releasing. Understand the difference. This is withdrawing, this is releasing. So methyl group will release electrons more onto the ring. So it will increase the electron density on the ring. It will become a better proton acceptor. So it is more basic. So electron withdrawing, electron releasing. Ethylamine is soluble in water, whereas aniline is not. Ethylamine, the side chain is, this is ethyl. But aniline, the side chain is ring. So steric hindrance to hydrogen bonding. So it cannot mix well with water because of this bulky benzene ring. Whereas ethyl amine, it is not as bulky as the ring in aniline. Then methylamine in water reacts with ferric chloride to precipitate hydrated ferric oxide. That I will explain. Look here. Methylamine in water. When you put methylamine in water, water is H plus OH minus. Now, there is a lone pair here. So, H plus will get connected there. So, you will be getting CS3, N, H2 and H will become NS3 plus and OH minus. Okay. So, it is producing OH minus ions in solution. Now, we are adding FeCl3. FeCl3 has Fe3 plus. That Fe3 plus will combine with 3 such OH minus ions to form Fe OH thrice or hydrated ferric oxide. That is the reddish brown precipitate what you see. FeOH thrice is same as Fe2O3 dot XS2O, hydrated ferric oxide. Then, although amino group is orthopara directing in aromatic electrophilic substitution, aniline on nitration gives substantial amount of metanitroaniline. Very important. That is, aniline, if you nitrating mixture, it is HNO3 plus H2SO4 which contains a lot of H plus. So what happens is aniline will get protonated. That is, aniline gets protonated. Aniline gets protonated from the acidic medium which is used for nitration to form what? Anilinium ion. Anilinium ion. Now you can see it turned positive. So it will act like an electron withdrawing group because of the presence of plus sign now on N. Electron withdrawing group. Electron withdrawing group is metadirecting. So it will produce substantial amount of metanitroaniline also. There is, nitration of aniline. You can go through that area. Many give reason questions are there. Direct nitration of aniline is not done because of a lot of TARI oxidation products are formed. That is one question. This is the second one. Okay. From nitration area. Then aniline does not undergo Friedrich-Krafts reaction. Why? Because aniline is a base. Okay. Anhydrous AlCl3 used in Friedrich-Krafts reaction, it is an acid, Lewis acid. Aniline is a Lewis base. They will combine to form a salt. So it will prevent further reaction. So it is also there on that particular page where nitration, sulfonation, then Friedrich-Krafts reaction, etc. are given there. So you take that page is very important for your exam. Make sure to go through that page of your textbook. Then diazonium salts of aromatic amines are more stable than those of aliphatic amines. Aromatic diazonium salt, it will undergo resonance stabilization. Then you have to draw the resonance, whereas aliphatic ones do not. So this is more stable than this. Then this one I have already told you, Gabriel thymide synthesis is preferred for synthesis of primary amines because Gabriel thymide synthesis will provide you with pure primary amine, not a mixture of primary, secondary, tertiary, etc. like in ammonolysis. So that's the advantage. Then these arrangement questions from the exercise, make sure to do these also. These arrangement questions, all of them are answered at the back, and use that order what I gave you to do this on your own. Then cross check with the text, but make sure to practice. But here I'll just give you some hint. In decreasing order of pKb values, what is the meaning of decreasing order of pKb? Decreasing order of pKb means what? Highest pKb to lowest. Highest pKb means lowest Kb. Lowest Kb means weakest base. So out of this, weakest base will be aniline. So you will be starting with aniline. See, many students make a mistake here. That's why I'm writing it here. Aniline greater than. Like this you will have to write. Why? Because aniline is the weakest base among them. It will have the highest pKb. Question is decreasing order of pKb. So like that you will have to arrange. Then here aniline, para-nitroaniline, para-toluidine. That also I will explain. Aniline, para-nitroaniline. This is aniline, then para-nitroaniline. Para-nitroaniline and para-toluidine. What is para-toluidine? NS2 and CS3. I am just explaining this. This is also a common question. What's the difference between them? Here nitro group is electron withdrawing. So it will take away the lone pair, decreasing the density. So it will become less basic than aniline. but methyl group is electron releasing. Yes, I'll come to you, okay? So, methyl group is electron releasing. So, this will increase the electron density on nitrogen. So, it will increase the basic strength. So, out of this, this is the least basic, then comes this is the most basic. A very, very important question. And all other amines, like these ones, you can use that arrangement what I gave to answer. Even this you can use gas phase, okay? This you can use that order of arrangement, but this one I will explain because it's a different one. Increasing order of boiling point. Alcohol, then diethylamine, ethylamine. Boiling point. Alcohol definitely has higher boiling point because there is O. O is more electronegative than N. OH bond is more polar than NH bond, you know that, all those things. So, primary amine will be higher than secondary amine, 2 hydrogens, 1 hydrogen. So, this one will be the maximum. Increasing order means this, less than this, less than this. This has the highest, this has the lowest. Then here solubility in water. Solubility in water, this has a bulky benzene ring. It will hinder hydrogen bonding. Then out of these two, this has more hydrogen, so it will have more hydrogen bonding with water. So this is the least, then comes this, same order, increasing solubility in water. Bulky ring, 2 ethyl groups and only 1 hydrogen. Here only 1 ethyl group and 2 hydrogens. Maximum hydrogen bonding, minimum. Same order. Then this question. Aromatic compound on treatment with aqueous ammonia. Aromatic compound A on treatment with aqueous ammonia and heating forms compound B, which on heating with Br2 and KOH forms a compound C of molecular formula C6H7N. Write the structure and IUPAC names of these compounds A, B and C. It is also a very important but very simple question for 3 marks. So, compound A reacts with aqueous ammonia on heating, forms compound B. So, we can make a rough flow chart. Compound A on treatment with aqueous ammonia and heating, you are getting compound B, which on heating with Br2, this is how you can do it easily, Br2 and KOH forms a compound C of molecular formula C6H7N. You should know C6H7N is nothing but aniline. Okay, you should know that. So, this is aniline. C is aniline. Then write the structures and IUPAC names of A, B and C. So, this is benzenamine or aniline. You know this is Hofmann-bromamide degradation reaction condition. So, if this is the product of the Hofmann-bromamide degradation reaction, what will we be? Just insert CO, isn't it? Just insert CO ahead of NS2. Okay. So, benzamide is B. Now, what on heating with ammonia, you will get benzamide? Benzoic acid. Carboxylic acids on heating with ammonia, you will get corresponding amide. So, A is benzene carboxylic acid or simply benzoic acid, benzamide, and this is benzenamine. Very, very important and too simple to score, right? Then why cannot aromatic primary amines be prepared by Gabriel-Thallimud synthesis? I have explained it. Because aryl halides cannot undergo nucleophilic substitution reaction by anion of thallimide because of the partial double bond character we have discussed. Then what about this? Why are amines less acidic than alcohols of comparable molar mass? Look here. Here it is a little different approach. Alcohol is ROH, right? Amine is RNH2. Say, I'm just taking a primary amine, for example. Here, the bond present is between O and H. Here, it is between N and H. You know, O is more electronegative than N. That means OH bond is more polar than NH bond, right? OH bond is more polar than NH bond. If it is more polar, H plus can come out easily. So this is more acidic than this one. That is how you have to answer this question. Clear? Then, why do primary amines have higher boiling points than tertiary amines? Primary amines, there are two hydrogens, extensive intermolecular association through hydrogen bonding, difficult to break those bondings, and high temperature, higher heat energy is required, higher boiling point temperature. Whereas tertiary amines, no hydrogen, so no intermolecular association like primary amines, so it is having lower boiling point. Then why are aliphatic amines stronger bases than aromatic amines? I told you in aliphatic amines, the alkyl group is electron releasing, so it will increase the electron density on N, making a better proton acceptor. In aromatic amines, the aryl ring, the benzene ring is electron withdrawing, with decrease the electron density on N, so it will be a weaker H plus acceptor. And this one we have already discussed. And now, note these things, okay? I told you, certain areas of your textbook are very, very important for the board examination. This is one such page where you have to go through this page. That's why I have taken the abstract. That is, aniline, you know, how can you control? Suppose I want to do bromination of benzene, of aniline, I'll be getting 2,4,6-tribromoaniline because NH2 group is highly activating. So if I want mono-substituted aniline, monobromoaniline, I have to control the activity of the NH2 group prior to the substitution. So how to do it? Aniline, make it react with acetic anhydride, do the acetylation, you will get acetanilide and phenylethanamide. That is, you know, actually you are diverting the attention. You are diverting the attention of the NH2 group. You are cheating the amino group actually. How? You can see this, when this group is present, before its focus was only, you know, releasing electrons into the ring, activating the ring. But now, when you acetylated, this group came here. So this is minus and this carbon is plus. So when this carbon is plus, the lone pair will go here to help that carbon. Okay, it will undergo resonance. So its focus got diverted. Before focus was into the ring, now focus got diverted. Understand? So it will become less activating. So you control the activating effect of that. So when this group is there on the ring, you do whatever you want. So you did the bromination in ethanoic acid. Then once you got what you wanted, then you just break it. Okay, hydrolyze it, H and OH. So you got bromoaniline. Understand? So this is how you are doing the controlling the activation effect of the NH2 group. Okay, so it is very, very important. And this is the resonance what is shown here, like what I told you. C becomes positive, lone pair goes there to help it. So that is how it is getting resonated. Very, very, very important. Then next one is this reaction. Aniline, sulfuric acid, you are getting anilinium hydrogen sulfate. On heating, you will get sulfanilic acid. And here what happens is, it is SO3 minus and H plus. Here there is a lone pair. So the H plus comes here. So it becomes SO3 minus and NH3 plus. So that is the sweeter ion form of sulfanilic acid. Extremely important. Then this is the area which I told you aniline does not undergo Friedel-Crafts reaction, because it is clearly written here. You can go through that. Aniline Lewis base, anhydrous LCA3 Lewis acid, they form a salt, preventing the reaction. Then conversions, toluene to benzyl alcohol. Then these conversions from the exercise you have to practice. You can make a note. benzene to benzaldehyde. This is very commonly asked in papers. That is benzene to benzaldehyde. What is that? Gutterman-Koch reaction. Okay, benzene to benzaldehyde. Benzene to diphenyl. It is what? Do you remember Wurtz reaction? Fittig reaction, Wurtz-Fittig reaction. Those areas are important. Benzene to diphenyl. Benzene you convert into chlorobenzene, chlorination in the presence of FeCl3, then Fittig reaction. Then benzene to acetophenone, Friedel-Crafts acylation, benzene plus CS3COCl, anhydrous AlCl3. There is not time to write all those things, so I am just telling you about it. Then benzoic acid to benzaldehyde, very very important, commonly asked in papers. That I will show you because it is highly expected. Benzoic acid to benzaldehyde. How? Benzoic acid, first you have to convert into benzoyl chloride. How? Make it react with SOCl2 or HCl or PCl3 or PCl5. You will be getting COCl, and once you got benzoyl chloride, then we can do Rosenmund reduction. H2, PD and barium sulfate. Then the COCl will change into CHO. So you will get benzaldehyde. Then propanone to propene. Propanone reduced propan-2-ol using sodium borohydride or lithium aluminum hydride, then or H2 bar PT, then do dehydration, that is concentrated sulfuric acid. Then ethanol to 3-hydroxybutanol. Ethanol. So ethanol, first you use PCC or CrO3 to oxidize to ethanol, then aldol condensation. Okay. Next one, benzaldehyde to benzophenone. Benzaldehyde, you can use Grignard reagent to get the alcohol, and you can oxidize the alcohol to get phenol. Then propanoic acid to ethanoic acid. Prop has 3 carbons, eth has 2 carbons. So propanoic acid you can convert to propanamide. Propanamide, Hofmann degradation, you will get propanamine. With HNO2 you will get propanol, and you can ethanamine and ethanol on oxidation you will get ethanoic acid. Because Hofmann bromide degradation reaction you will knock out one CO, you will be getting ethanamine. Then benzoic acid to aniline. It is very important conversion. That I will explain. Benzoic acid first you make it react with the ammonia and heat. Then you will get benzamide. Okay, benzoic acid to benzamide. Benzamide, Hofmann bromamide degradation reaction, Br2 and NaOH or Br2 and KOH. Then you remove this, you will get aniline. Okay, that is benzoic acid to aniline. Commonly asked questions. Benzoic acid to aniline is very common in papers. Make a note of it. Similarly, previous one, benzoic acid to benzaldehyde is very common. Ethanol to 3-hydroxybutanol, very common. Then toluene to benzyl alcohol, benzene to diphenyl. I have selected only those ones. Okay, make sure to practice them. Okay, that's all. We have completed biomolecules, D and F block and coordination compounds. D and F block and coordination compounds. If you are interested, you can watch the one-shot sessions which I have posted in my channel, uploaded in my channel. So I hope this marathon session helped you a lot. Okay, someone has told me that have a doubt. Yes, I don't know the name. It is written plant addicted. So what is your query? Please write the question. Thank you, Harini. Thank you for the appreciation. So anyway, we have started our session at 5 p.m. IST. Now it is 2:15 early morning IST, okay, next day. So there is no harm in calling this a marathon session, okay. Of course it was a marathon session, and I have tried my level best to cover up all the areas. Actually, I was doubtful whether I will be able to take this session because of this physical condition, but still I wanted to help my students, so I just tried for it. And this is my first live session, so there could be many flaws because I will learn from my mistakes, okay. Anyway, thank you so much for cooperating and making use of this session. I am pretty sure those who attended the session completely, and if you rewatch these things, if you have any doubt, it will be helping you definitely to have a fantastic score in your upcoming board examination. That is 100% sure. I think, Shubham, I have told you that before that it is not necessary to give explanation in arrangement questions, but if you aim centum, that is 70 upon 70, students normally do it, okay. That is not a big explanation paragraph, just like a hint, like, what is the basis of arrangement, what you're doing, that's it. How to score 50? You mean 50 upon 100 or 50 upon 70, Vivek? If you watch this session completely and have given your 100% into it, not 50, you can get 70 upon 70. 100% sure. So I think we can wind up. And tomorrow I might upload a video that is tips and tricks and time management. Okay, that will be uploaded tomorrow. So you can watch that session. Okay, it will be a short video. You can watch that session, and that also will help you to manage the exam properly. Okay, right. Any other doubts or queries? Shubham, yes. If you completed whatever PYQs, I have started uploading the videos bit late. Actually, I was planning to start it from next academic year, but because of some student request, I started earlier. But this time is not enough. But still, I tried my level best again to upload maximum number of videos since when I started. And I'm getting feedback from the students that, they are getting maximum benefit out of it. Oh, Vivek, thank you. Aisha, thank you. Harini, thank you. Yes, I have uploaded some one-shots so that, those tricky questions can be dealt with, which students normally might, skip. So one shot was given for that. And even now you have time, if you have some doubts from D and F block or coordination compounds, I think you can go through the one-shot sessions which I uploaded. Definitely, 100% sure you will get a lot of benefit out of them. And go through the shorts also. Okay, there are some small questions which I have given in the form of shorts. And previously uploaded videos also, if time permits. Okay, if you completed your studies, you can go through them. 100% they will be much helpful. You can see these students, their result is the result of their hard work. Not only me, it is their hard work too. Okay, so you can see a question mark there. It can be any one of you there or more of you. Okay, so shall we wind up? So tomorrow I will upload a video about the tips and tricks, then time management, etc. Okay, you can watch that. All the best and good luck. Okay, you will do the paper really well, and once the paper is out, I'll be discussing the paper too. Okay, okay then, bye, good luck. Shubham, facing problem in batteries and reactions related to it. It is just a matter of by hearting them, Shubham, because it is not application. It is just a matter of, learning the reactions and, the explanation given in the battery area. Simple. There is no application as such. Right. Anyway, if you have any doubt still, you can message me. I have given my number in my WhatsApp number in my channel. So if you have any doubt, you can contact me through that number. Okay. We'll try to help you. Okay. Bye. Good luck.